Hi, data scamps and data champs. Here we'll explore using the Python API for Apache Spark in Big Data with PySpark. You'll learn how to leverage parallel computing to process and analyze big data efficiently. We'll cover data cleaning, feature engineering, and building machine learning models at scale. You'll get hands-on experience creating recommendation engines using real-world datasets like MovieLens and the Million Songs dataset. To explore further, check out the skill track linked in the description below. Please like and subscribe for more.
Welcome. In this course, we'll explore PySpark, a powerful tool for processing and analyzing big data. Designed for data engineers, data scientists, and machine learning enthusiasts, this course will teach you to work with large-scale datasets in distributed environments, transforming raw data into valuable insights. I'm Benjamin, your instructor for this course. I've been a data engineer for nearly a decade, working with big data solutions in PySpark for ETL pipelines, data cleaning, and machine learning. PySpark is one of the most versatile tools for data professionals. Apache Spark is an open source, distributed computing system designed for fast processing of large-scale data. PySpark is the Python interface for Apache Spark. It handles large datasets efficiently with parallel computation in Python workflows, ideal for batch processing, real-time streaming, machine learning, data analytics, and SQL querying. PySpark supports industries like finance, healthcare, and e-commerce with speed and scalability. PySpark is ideal for handling large datasets that can't be processed on a single machine. It excels in big data analytics through distributed data processing using Spark's in-memory computation for faster processing. Machine learning on large datasets leverages Spark's MLlib for scalable model training and evaluation. ETL and ELT pipelines transforms large volumes of raw data from sources into structured formats. PySpark is flexible, working with diverse data sources like CSV, Parquet, and many more. A key component of working with PySpark is clusters. A Spark cluster is a group of computers, or nodes, that collaboratively process large datasets using Apache Spark, with a master node coordinating multiple worker nodes. This architecture enables distributed processing. The master node manages resources and tasks, while worker nodes execute assigned compute tasks. A SparkSession is the entry point into PySpark, enabling interaction with Apache Spark's core capabilities. It allows us to execute queries, process data, and manage resources in the Spark cluster. To create a SparkSession, run from PySpark SQL import SparkSession. We'll create a session named MySparkApp using SparkSession Builder, stored as the variable Spark. The builder method sets up the session, while get or create initiates a new session or retrieves an existing one. The appName method helps manage multiple PySpark applications. With our SparkSession ready, we can load data and apply transformations or actions. It's best practice to use SparkSession.builder.get or create, which returns an existing session, or creates a new one if necessary. PySpark DataFrames are distributed table-like structures optimized for large-scale data processing. Their syntax is similar to Pandas, with the main difference being how data is managed at a low level. To create a PySpark DataFrame, use the Spark read CSV function in the SparkSession with a CSV file. For this example, we'll use a generalized data variable representing any data source and columns to define the schema. To see our data frame, we can use the show method. We'll explore these concepts further throughout this course. Now let's go see these concepts in action. Welcome back. We've already started with DataFrames in PySpark in the previous video, but now let's dive deeper. While we may be familiar with DataFrames from Pandas, the key difference in PySpark is how the data is distributed. Pandas operates on a single compute instance, while PySpark distributes data across multiple instances, affecting processing speed and data scalability. DataFrames are essential in PySpark for efficiently managing large-scale data across clusters. While they resemble Pandas DataFrames, they are designed for much larger datasets. We'll frequently interact with data using PySpark DataFrames, which support various manipulation tasks such as filtering, grouping, and aggregating on distributed data, making them vital for big data analytics. Additionally, DataFrames support SQL-like operations on tables. As we go through this course, you'll probably notice similarities between Pandas DataFrame syntax and PySpark DataFrame syntax. But bear in mind, DataFrames in PySpark operate slightly differently, so be sure to pay attention. Let's start by creating a DataFrame in PySpark. A common method for loading data is using spark.read.csv, which easily reads CSV files into a PySpark DataFrame, allowing us to define headers and automatically infer schema types. This code loads a CSV, treating the first row as headers and inferring data types for each column. We also include header equals true and infer schema equals true, which are true for this particular table. But there are also many other arguments available, so check out your documentation. Using the show method, we can display the first 5 rows of the data frame. While we can also create data frames using the create data frame function, read.csv is generally faster, offering significant speed improvements at scale, especially as we gain real-world experience with big data. To inspect the schema, use print schema to view the data frame structure. Once we've loaded data into a data frame, we can perform basic analytics like aggregations, which summarize data by counting rows, summing values, or calculating averages. These will return an integer or float, typically. For instance, to count the rows in a data frame, use the count method. For more advanced summaries, we can employ the GroupBy and aggregate methods. To group data by a column and calculate the average of another, we can use various aggregation functions like standard deviation, sum, and more that you are probably already familiar with. This approach above groups data by gender and computes the average of salary USD, showing how to combine steps for data summarization and quick insights. Some of the most important methods we'll use with data frames are GroupBy, Agg, Filter, and Select. Let's start with Select, which operates like it does in SQL, where it will take specific named columns. Filter operates like SQL's where. GroupBy is also like SQL's same named keyword. Agg takes a function like sum, and the specific columns we're interested in. In each case, we need to pass the data frame name and the columns as a list. For example, we can filter the data frame for rows where the value in the age column is greater than 50 and select only those columns. Let's practice data frames in PySpark. Welcome back. In this video, we'll work with some basic data frame operations. In PySpark, reading data from various formats allows flexibility in handling diverse datasets, each format offering unique benefits. CSV files, or comma-separated value files, are widely used because of their simplicity and compatibility across many platforms. They store data in a plain text format, making them easy to read and write without needing specialized tools. However, CSV files lack schema enforcement, which means they don't define or enforce data types for each column, leading to potential inconsistencies. We can read the data using the read CSV function. JSON, or JavaScript object notation files, are ideal for representing nested data structures, making them a good choice for data that includes hierarchical relationships or arrays or high compatibility. However, JSON files can become storage intensive when scaled to large data sets. We can load them using the read JSON function. Parquet is a columnar storage format optimized for read-heavy operations, making it a powerful choice for large datasets that require frequent querying. Additionally, Parquet enforces schema definitions, which helps maintain data consistency and supports complex data types, like nested structures, much like JSON. We can load Parquet files using read Parquet. Using these formats, PySpark enables data engineers and data scientists to tailor their storage to the needs of their specific applications. Spark can automatically infer schemas, but sometimes it misinterprets data types, particularly with complex or ambiguous data. Manually defining a schema can ensure accurate data handling. To manually configure a schema, we need to define the data type using the struct field function, calling the right data type method. PySpark DataFrames can support various data types, similar to SQL and Pandas. The primary ones are integer type for whole numbers, long type for large integers, float type and double type for decimal numbers, and string type for strings. We import the specific classes from pyspark.sql.types. To define the schema for our data frame, we use struct type and struct field functions to define the structure and fields of a data frame, filling in the columns and their types. Selecting specific columns and filtering rows are fundamental operations in data analysis. With PySpark, you can perform these operations on large datasets with efficiency using the select, filter, sort, and where methods. Where and filter operate similarly to those in SQL, where we pass a column or columns and a condition to match. Sorting and handling missing data are common tasks. Dropping nulls can clean data, but in some cases may want to fill or input values instead, which Spark also supports. We can use sort for simple, flexible sorting, and order by for complex multi-column sorting methods to sort and order a data frame, similar to the same commands in SQL. We can use the NA drop to drop all nulls in the data frame. Here's a cheat sheet to help you out. Now let's go see these data frames in practice. In this video, we'll cover essential techniques for handling missing data, managing data frame columns and rows, and using PySpark's built-in functions to clean and transform data. Handling null values in PySpark is essential for accurate analysis. Nulls can skew results or cause errors. PySpark offers two primary methods to address this issue. The first approach is to drop rows with null values using NA_drop, either across the entire data frame or in specific columns. This simplifies the dataset but may significantly reduce the size if nulls are common. For column-specific filtering, where and is not null can be used. The second approach is to replace nulls with default values using NA_fill. This method is ideal when nulls are sparse or when removing rows would result in data loss, ensuring the dataset remains complete and consistent. PySpark simplifies creating new columns with the withColumn method, allowing users to define the column name and computation. This is useful for derived metrics or transformations. Renaming columns with column renamed improves clarity, making data frames easier to work with in collaborative settings. Clear descriptive names reduce ambiguity and ensure accurate documentation. Dropping columns with drop removes redundant or irrelevant data, focusing the data frame on essential points. This helps manage large datasets by reducing memory usage and improving efficiency. These operations enhance PySpark data frames' flexibility and clarity, tailoring them to specific analysis needs while maintaining a clean structure. Row operations are central to data analysis. Filtering is for narrowing down a data frame to the most relevant data. By applying conditions to filter rows, we can isolate subsets that meet specific criteria, such as data from a particular time period, geographic region, or category. We use the filter method, providing the column name and the filter criteria. Grouping rows based on specific fields or categories allows us to organize the data by meaningful segments, such as by customer, product, or date. Grouping enables us to analyze patterns and trends within each category, offering insights that would be difficult to see in ungrouped data. We use the GroupBy method, and then the aggregation we would be interested in, with the columns we want to focus on. Here's what the code from the previous slide may look like. And here is a cheat sheet to help you going forward. Let's go practice how data frames work in PySpark. In this video, we'll explore powerful data manipulation techniques in PySpark, including joins, unions, and complex data types. Joins in PySpark combine data from multiple data frames based on shared columns, similar to SQL. This enriches datasets, such as merging customer details with purchase history to analyze buying patterns. PySpark supports inner, left, right, and full outer joins, performed using the join method by specifying the second data frame, join type, and columns impacted. For columns with different names, you must explicitly specify the joining columns, similar to SQL syntax. The union operation in PySpark is a powerful tool that enables us to combine or stack two data frames, as long as they share the same structure, meaning they have the same number and types of columns in the same order. This operation is particularly useful when we're working with datasets that have been split across different sources or time periods, and we want to consolidate them into a single data frame for easier analysis and processing. If the data frames don't have the same schema, a union will not work and create an error. Using union, we can append one data frame on top of another, effectively combining rows from both data frames into a single unified dataset. For example, if we're working with monthly sales data stored as separate files for each month, union allows us to combine all monthly data frames into a single data frame that represents the entire year. This consolidated view simplifies further analyses, as it eliminates the need to handle multiple separate data frames. Here's the syntax for performing a union in PySpark. This operation stacks df2 underneath df1. However, it's important to note that the data frames must have identical schemas for this operation to work correctly. Otherwise, PySpark will raise an error. This schema alignment is crucial because mismatched columns or data types would prevent the rows from being combined accurately and showing the same type of data. Complex data types in PySpark, like arrays, structs, maps, enhance flexibility by allowing nested data within each row. These data types enable PySpark to manage structured data within a single column, providing a way to work with these more complex data relationships and hierarchy directly in the data frame. Arrays store lists within a column, useful for attributes with multiple values. For an array, define the values being passed using the appropriate data type. Here we are using lit for a specific value. Maps store dynamic key value pairs within a column, providing a flexible way to store dynamic data attributes where each row might have different keys. The map method needs to have passed the value, the data type method we've seen before, and a Boolean for requirement of the key value pair. Structs group related fields within a single column. This is valuable for managing hierarchical data within one column. Similar to map, we pass a value with struct field, defining the name and data type. Let's go see these SQL-like actions in practice. Now, we'll take a look at user-defined functions, or UDFs, in PySpark. By the end of this video, we'll have a thorough understanding of what UDFs are and how to create them. A UDF is a custom function we create to work with data using PySpark DataFrames. We'll discuss two kinds of UDFs, PySpark UDFs and Pandas UDFs. The main difference is the size of the dataset they are designed to handle. There are some differences in execution, but they operate very similarly. They are both reusable and repeatable because they are registered directly to the SparkSession. We have the two types of UDFs, Pandas UDFs for large datasets and PySpark UDFs for smaller datasets. This may seem counterintuitive, but it is due to how each type of UDF handles data on a row-by-row basis. It's outside our scope here, but well worth exploring as we get more PySpark experience. Now, how do we create a UDF? Let's see how it's done. First, we create a regular Python function called toUpperCase to convert all strings in a column to uppercase. Next, we register the function as a UDF using PySpark's UDF function and pass the correct data type method. We're doing string operations, so we use string type. Without registering, the UDF would not be available to all the worker nodes of the Spark session. Lastly, we apply it to the DataFrame DF and show the results. While PySpark UDFs are incredibly useful, they can also introduce performance overhead because PySpark has to do a series of inefficient conversions, causing frustrating performance problems. To mitigate this, PySpark has introduced Pandas UDFs. Here's an example of a Pandas UDF, which is defined as a Pandas UDF. Two things to notice here. One, we have to import the Pandas UDF function. Second, we have to use the decorator @ to define the data type using @pandas UDF float, which is a way to take an action at a function as an argument. We also don't need to register it to the Spark session. So when should we use PySpark UDFs and when should we opt for Pandas UDFs? If we are working with small datasets or simple transformations, PySpark UDFs will suffice. We use them on the columnar level and register directly with the Spark session. Registering to a Spark session will make the UDF work with all nodes of the Spark cluster. However, for large datasets, Pandas UDFs are preferred due to their superior performance at scale and incorporate the code outside the Spark session. There are many scenarios where we would consider a PySpark UDF over a Pandas UDF, but they involve a cost-benefit analysis of compute cost, development environment, data size, and data type that are outside the scope of this course. Let's go practice UDFs. Let's explore a foundational component of PySpark, Resilient Distributed Datasets, RDDs. One of PySpark's greatest strengths is its ability to handle large-scale data processing through parallelization, which splits data and computations across multiple nodes in a cluster. Operations defined in Spark are automatically distributed, enabling efficient processing of large datasets. Tasks are assigned to worker nodes that process data in parallel, with results combined at the end. This approach allows for efficient processing at scale, accommodating gigabytes or even terabytes of data. RDDs are the core building blocks of Spark, representing distributed collections of data across a cluster. While RDDs enable fast access and analysis, DataFrames offer greater user-friendliness due to their simpler syntax, although they can be slower. RDDs are immutable, meaning once created, it cannot be changed. But a new RDD can be created using operations like map and filter. They also support actions like collect, which retrieves the results of RDD operations. Let's create an RDD using a CSV. We'll load the data frame from the CSV, then use the RDD method to convert it to an RDD. The data is distributed across the cluster when the RDD is created. Here, we create an RDD from a CSV file and use a collect action to retrieve and display the data. As you can see, collect shows a summary of the processes that were done. It is also rather verbose to do a print statement. As you can see, collect shows a summary of the processes that were done. It is also rather verbose to do a print statement. RDDs offer a low-level interface, providing maximum flexibility. You can manipulate data at a granular level, but this flexibility comes at the cost of requiring more lines of code for even moderately complex operations. One strength of RDDs is their ability to preserve data types across operations. However, they lack the schema-aware optimizations of DataFrames, which means operations on structured data are less efficient and harder to express. While RDDs can scale to handle large datasets, they're not optimized for analytics like DataFrames. DataFrames are operated for ease of use, providing a high-level abstraction for working with data. They encapsulate complex computations, making it easier to achieve our objective with less code and fewer errors. One of the standout features of DataFrames is their SQL-like functionality. With SQL syntax, even complex transformations and analysis can be performed in just a few lines of code. DataFrames come with built-in schema awareness, meaning they contain column names and data types, just like a structured table in SQL. Here are a handful of useful functions you'll be seeing in the following exercises. Map is useful to apply a function to an RDD. This can include a lambda function or any other function defined or imported elsewhere. Collect gathers data across the cluster using the parallelization of PySpark. Let's go look at RDDs and DataFrames in practice. Welcome back. We'll now learn how Spark SQL enables us to use Python and SQL in the same PySpark environment. Let's explore Spark SQL, a powerful component of Apache Spark that integrates seamlessly with its ecosystem. It enables processing of structured and semi-structured data using SQL syntax. Why choose Spark SQL over other tools? First, it leverages Spark's distributed computing power, handling massive datasets effortlessly by distributing computations across a cluster. Second, Spark SQL simplifies querying with familiar SQL syntax, making it accessible to analysts and engineers. Third, its integration with PySpark DataFrames enables blending SQL and programmatic operations for complex workflows. In short, Spark SQL delivers the flexibility, speed, and scalability needed for working with large, diverse datasets. To work with SQL in PySpark, start by registering a data frame as a temporary view. We can use the createDataFrame method to make the data frame, or load the data from a flat file. This allows interaction with the data frame using SQL syntax through the create or replace temp view method, where you pass the view name as a string. For example, we'll create a view called people. Temporary views exist only for the current session, making them ideal for quick session-based exploration. For instance, to find people older than 30, use the spark.sql function and pass your SQL query as a string. This query retrieves the name and age columns from the people view, filtering to return only rows where age exceeds 30. The result is another data frame, which you can continue processing PySpark outside the session. Let's explore how to load data from CSV files into DataFrames, register them as temporary views, run SQL queries, and blend SQL with DataFrame commands for advanced manipulation. To query a data frame with SQL, we first load the data into a data frame using methods like spark.readCSV. After loading, we register the data frame as a temporary view, allowing SQL-based interaction while safeguarding the underlying data and data source during analysis. These views are session scoped, lasting only as long as a Spark session is active. For extended use, global temporary views or permanent tables must be created. One of the most powerful aspects of Spark SQL is its seamless integration with DataFrame operations. After running a SQL query, the results are returned as a data frame, allowing us to apply additional transformations programmatically. Here, we use SQL to filter high-earning employees and then added a bonus column using DataFrame operations. Let's go seamlessly blend SQL and PySpark in single scripts. Welcome back. Let's take a look at some complex PySpark aggregations. PySpark SQL provides a suite of built-in aggregation functions for summarizing data. Commonly used functions include sum, count, average, max, and min. These are applied using either SQL queries with spark.sql or the DataFrame toolkit. Let's see an example of calculating the total and average salary for employees in different departments using SQL syntax. PySpark allows us to mix SQL operations with the DataFrame interface for greater flexibility. For instance, we can filter and pre-process data using DataFrame operations before applying SQL aggregations. This combination leverages the strengths of both approaches. By combining these two tools, we get the best of both worlds: the expressiveness of SQL and the programmatic control of the Pandas data frame. Notice how in each step we are registering a new temporary view. This lets us easily roll back changes and catch errors before it hits our data store. While performing aggregations, data type mismatches can lead to errors or unexpected results. For instance, numerical data stored as strings might not aggregate correctly. PySpark provides functions and methods like cast to convert data types before processing. We should always validate and standardize our data types before running aggregations. This protects our pipeline from costly errors. Aggregations are a cornerstone of data and analytics, helping us summarize and gain insights from large datasets. PySpark provides powerful aggregation functions through its SQL interface and the DataFrame API. Now we'll explore some of these common PySpark SQL functions, like sum and average. While RDDs are useful for certain use cases involving scale and data movement across clusters, DataFrames are the preferred choice for most modern PySpark analytics applications due to their simplicity of syntax. RDDs, as a general rule, do not have simple code syntax for aggregation or analytics. The code we're seeing now does the same as the aggregations we saw earlier. With an RDD, the best way to do this is with a lambda function, a small transformation function with very limited scope that is targeted to our circumstance, and then we apply the new lambda function with the RDD map method. The reduced by key method applies the function previously defined to the entire data frame. It's a lot. As we can see, the verbosity of RDDs for analytics requires the writing of custom functions and multiple lines to apply it, compared to the single line application that we saw with DataFrames. Here are some best practices for PySpark aggregations. Filter early to reduce data size before performing aggregations. Ensure data is clean and correctly typed. Avoid using the entire dataset by minimizing operations like GroupBy. Choose the right tool by preferring DataFrames for most tasks due to their optimizations. Monitor performance by using the explain to inspect the execution plan and optimize accordingly. Here are some key takeaways. Let's go check out some PySpark aggregations. Welcome back. Let's talk about what happens when we use PySpark at scale. As our data grows, optimizing PySpark jobs becomes essential for managing performance, resource usage, and execution speed. In this video, we'll focus on techniques to scale PySpark workflows effectively. First, we'll explore how to interpret Spark execution plans to identify performance bottlenecks. Next, we'll discuss caching and persisting data frames, which can significantly speed up iterative queries. Finally, we'll cover best practices for optimizing PySpark jobs, ensuring we make the most of Spark's distributed computing power. Scaling PySpark is not just about faster results. It's about building workflows that are efficient, maintainable, and capable of handling large datasets with ease. Methods like broadcast will load a smaller dataset across the cluster, using all available compute. As we work more with PySpark, the more we will need to think in moderately abstract ways. A key tool for optimizing PySpark jobs is understanding Spark execution plans. Whenever we run an operation on a data frame, Spark constructs a logical plan, which is then optimizes into a physical plan. This physical plan outlines how Spark will execute the task on its distributed cluster. We can inspect the process using the explain method. It gives us a breakdown of the query's execution plan, showing the operations performed at each stage. This outputs a logical and physical plan. By analyzing these plans, we can spot inefficiencies, like redundant shuffles or unoptimized joins, and address them before running the job. The explain method details the logical and physical plans for optimization, showing what the code ran and what hardware it used. This outlines how to improve it. When working with large datasets, we often reuse intermediate results across multiple operations. Recomputing These results can be costly, especially when reading from disk. To avoid this, we have two tools that keeps data readily available: caching and persisting. The cache method stores a data frame in memory for fast use, while the persist method offers flexibility by letting us choose storage levels. Here, the dataset is read once, and subsequent operations reuse the cached version. The second option is using the persist method, which allows us greater control of storage levels. We can use disk when memory is insufficient. This is especially useful for long-running jobs on large clusters. However, caching consumes memory, so it's important to uncache data when it's no longer needed, using the unpersist method. In this example, if the data frame doesn't fit in memory, Spark writes the overflow to disk. This ensures our operations can still proceed without crashing due to resource constraints. This concept is difficult for us to demonstrate in this course, but you will encounter it as you work with PySpark in the real world. Beyond caching and persistence, here are a few best practices to optimize PySpark jobs. Use small subsections. Favor targeted functions and methods like map over whole dataset tools like GroupBy that require shuffles. Broadcast joins. For small datasets, use broadcast to load the data onto all the nodes and avoid shuffles. Lastly, avoid repeated actions. Operations like count or show trigger jobs. Store intermediate results to prevent recomputation. Let's go look at these ideas in practice. Congratulations on reaching the end of the course. You've come a long way, building up foundational skills and exploring powerful tools for big data processing with PySpark. Starting from an overview of Apache Spark's architecture, you dove into the fundamentals of distributed data processing. You learned about resilient data sets, RDDs, transformations, and actions. Key concepts that power PySpark's ability to handle massive datasets effectively. You also navigated the world of DataFrames, a critical PySpark component for handling structured data, and discovered the flexibility of PySpark SQL for SQL-like operations. With this foundation, you now understand how to filter, aggregate, and join data, making complex data wrangling tasks intuitive and scalable. In addition to these core skills, you ventured into advanced topics like user-defined functions within PySpark. These tools allow you to extend PySpark's capabilities, from applying custom transformations to building and running machine learning models on distributed datasets. However, there is still more to explore in the PySpark ecosystem. This course didn't cover topics such as advanced cluster configuration, performance optimization, big data applications, and streaming data processing with PySpark Streaming. Additionally, deep dives into Spark's machine learning pipelines and integration with cloud-based tools were beyond the scope of this course. These are advanced topics you can and should explore as you continue your PySpark journey. Whether you're a data engineer, a data scientist, or a machine learning engineer, you now have the skills to leverage PySpark for managing and analyzing big data. Thank you for joining me on this journey. I'm Benjamin Schmidt, And congratulations again on mastering the foundations of PySpark. Goodbye and good luck.
Welcome to the first video of Big Data Fundamentals via PySpark course. My name is Upendra Devishetty and I'm a science analyst at Cyverts. Let's get started. What exactly is big data? There is no single definition of big data because projects, vendors, practitioners, and business professionals use it quite differently. According to Wikipedia, big data is a term used to refer to the study and applications of datasets that are too complex for traditional data processing software. There are three V's of big data that are used to describe its characteristics. They are volume, velocity, and variety. Volume refers to the size of the data. Variety refers to the different sources and formats of data. Velocity is the speed at which data is generated and available for processing. Now let's take a look at some of the concepts and terminology of big data. Clustered computing is the pooling of resources of multiple machines to complete jobs. Parallel computing is a type of computation in which many calculations are carried out simultaneously. A distributed computing involves nodes or networked computers that run jobs in parallel. Batch processing refers to the breaking data into small pieces and running each piece on an individual machine. Real-time processing demands that information is processed and made ready immediately. There are two popular frameworks for big data processing. The first is the highly successful Hadoop MapReduce framework. Hadoop MapReduce framework is open source and scalable framework for batch data. The second is the most popular Apache Spark, which is a parallel framework for storing and processing of big data across clustered computers. It is also open source and is suited for both batch and real-time data processing. In this course, you learn about Apache Spark. Let's talk about the main features of Apache Spark. Spark distributes data and computation across multiple computers, executing complex multi-stage applications such as machine learning. Spark runs most computations in memory and thereby provides better performance for applications such as interactive data mining. Spark helps to run an application up to 100 times faster in memory and 10 times faster when running on disk. Spark is mainly written in Scala language, but also have support for Java, Python, R, and SQL. Apache Spark is a powerful alternative to Hadoop MapReduce, with rich features like machine learning, real-time stream processing, and graph computations. At the center of the ecosystem is the Spark core, which contains the basic functionality of Spark. The rest of Spark's libraries are built on top of it. First is Spark SQL, which is a library for processing structured and semi-structured data in Python, Java, and Scala. The second is MLlib, which is a library of common machine learning algorithms. The third component is GraphX, which is a collection of algorithms and tools for manipulating graphs and performing parallel graph computations. Finally, Spark Streaming is a scalable, high-throughput processing library for real-time data. In this course, you learn about Spark SQL and MLlib. Spark can be run on two modes. The first is the local mode, where you can run Spark on a single machine, such as your laptop. The local mode is very convenient for testing, debugging, and demonstration purposes. The second is the cluster mode, where Spark is run on a cluster. The cluster mode is mainly used for production. The development workflow is that you start on a local mode and transition to cluster mode. During the transition from local to cluster mode, no code change is necessary. In this course, you'll be using local mode. In the next video, you learn about PySpark, which is Python API. In the last video, you were introduced to Apache Spark, which is a fast and general-purpose framework for big data processing. Apache Spark provides high-level APIs in Scala, Java, Python, and R. In this video, you learn about PySpark, which is Spark's version of Python. Apache Spark is originally written in Scala programming language. To support Python with Spark, PySpark was developed. Unlike previous versions, the newest version of PySpark provides computation power similar to Scala. APIs in PySpark are similar to Pandas and scikit-learn Python packages. Thus, the entry-level barrier to PySpark is very low for beginners. Spark comes with interactive shells that enable ad hoc data analysis. Spark Shell is an interactive environment through which one can access Spark's functionality quickly and conveniently. Spark Shell is particularly helpful for fast, interactive prototyping before running the jobs on clusters. Unlike most other shells, Spark Shell allows you to interact with data that is distributed on disk or in memory across many machines, and Spark takes care of automatically distributing this processing. Spark provides the shell in 3 programming languages: Spark Shell for Scala, PySpark for Python, and SparkR for R. PySpark Shell is a Python-based command line tool to develop Spark's interactive applications in Python. PySpark helps data scientists interface with Spark data structures in Apache Spark and Python. Similar to Scala Shell, PySpark Shell has been augmented to support connecting to a cluster. In this course, you will use PySpark Shell. In order to interact with Spark using PySpark Shell, you need an entry point. Spark context is an entry point to interact with underlying Spark functionality. Before understanding Spark context, let's understand what an entry point is. An entry point is where control is transferred from the operating system to the provided program. In simpler terms, it's like a key to your house. Without the key, you cannot enter the house. Similarly, without an entry point, you cannot run any PySpark jobs. You can access the Spark context in the PySpark shell as a variable named sc. Now, let's take a look at some of the important attributes of Spark context. The first is the version. This attribute shows the version of Spark that you're currently running. In this example, sc.version shows that the version of Spark is 2.3.1. The second is the Python version. This attribute shows the version of Python that Spark is currently using. In this example, sc.pythonver shows that Spark is using Python version 3.6. The final attribute is the master. Master is the URL of the cluster or local string to run in local mode. In this example, sc.master returns local asterisk, meaning the Spark context acts as a master on a local node using all available threads on the computer where it is running. You can load your raw data into PySpark using Spark context by 2 different methods. The first is the Spark context parallelize method and a list. For example, here is how to create parallelized collections holding the numbers 1 to 5. The second is the Spark context text file method on a file. For example, here is a way to load a text file named test.txt using Spark context text file method. Now that you understand PySpark, let's write your first Spark code. Understanding PySpark becomes a lot easier if you understand functional programming principles in Python. In this video, let's review some of the Python functions such as lambda, map, and filter. Python supports the creation of anonymous functions, that is, functions that are not bound to a name at runtime, using a construct called the lambda. Lambda functions are very powerful, well integrated into Python, and are often used in conjugation with typical functional concepts like map and filter functions. Like def, the lambda creates a function to be called later in the program. However, it returns the function instead of assigning it to a name. This is why lambdas are known as anonymous functions. In practice, they are used as a way to inline a function definition or to defer execution of a code. Lambda functions can be used whenever function objects are required. They can have any number of arguments, but only one expression, and the expression is evaluated and returned. The general syntax of lambda function is shown here. Here is an example of lambda function. In this example, lambda x colon x asterisk 2, x is the argument and x asterisk 2 is the expression that gets evaluated and returned. This function has no name. It returns a function object which is assigned to the identifier double here. Applying the lambda function to a number such as 3 returns 6, which is the double of the original number. Let's take a look at the differences between def and lambda. Here is the Python code to illustrate cube of a number, showing the difference between normal Python function using def and anonymous function using lambda. As you can see, both def and lambda do exactly the same. The main difference is that the lambda definition does not include a return statement, and it always contains an expression which is returned. Also note that we can put a lambda definition anywhere a function is expected, and we don't have to assign it to a variable at all, unlike normal Python function using def. We use lambda functions when we require a nameless function for a short period of time. Most of the times, we use lambdas with built-in functions like map and filter. The map function is called with all the items in the list, and a new list is returned which contains items returned by that function for each item. The general syntax of map function is shown here. It takes in a function and a list. Here is an example of map function with lambda to add the number 2 to all the items in a list. The result indicates that the number 2 is added to 1, 2, 3, 4, resulting in 3, 4, 5, 6. The filter function in Python takes in a function and list as argument. The function is called with all the items in the list, and a new list is returned which contains items for which the function evaluates to true. Here is a general syntax of filter function in Python. Similar to map, it takes in a function and a list as arguments. Here is an example use of filter with lambda to filter out only odd numbers from a list. As shown in the example, filtering the items list containing numbers 1, 2, 3, 4 resulted in 1 and 3, which are the only odd numbers for the input list. Lambda functions are incredibly useful, and before going deep into PySpark, let's practice some lambda functions. In the first chapter, you have learned about the different components of Spark, namely Spark Core, Spark SQL, and Spark MLlib. In this chapter, we'll start with RDDs, which are Spark's core abstraction for working with data. Let's get started. RDD stands for Resilient Distributed Datasets. It is simply a collection of data distributed across the cluster. RDD is the fundamental and backbone data type in PySpark. When Spark starts processing data, it divides the data into partitions and distributes the data across cluster nodes, with each node containing a slice of data. Now let's take a look at the different features of RDD. The name RDD captures three important properties. Resilient, which means the ability to withstand failures and recompute missing or damaged partitions. Distributed, which means spanning the jobs across multiple nodes in the cluster for efficient computation. Datasets, which is a collection of partitioned data, example arrays, tables, tuples, or other objects. There are three different methods for creating RDDs. You have already seen two methods in the previous chapter, even though you are not aware that you are creating RDDs. The simplest method to create RDDs is to take an existing collection, example a list, an array, or a set, and pass it to Spark context parallelize method. A more common way to create RDDs is to load data from external datasets, such as files stored in UDFs or objects in Amazon S3 buckets, or from lines in a text file stored locally, and pass it to Spark context text file method. Finally, RDDs can also be created from existing RDDs, which we'll see in the next video. In the first method, RDDs are created from a list or a set using the Spark context parallelize method. Let's try and understand how RDDs are created using this method with a couple of examples. In the first example, an RDD named numRDD is created from a Python list containing numbers 1, 2, 3, and 4. In the second example, an RDD named helloRDD is created from the hello world string. You can confirm the object created is RDD using Python's type method. Creating RDDs from external datasets is by far the most common method in PySpark. In this method, RDDs are created using the Spark context text file method. In this simple example, an RDD named fileRDD is created from the lines of readme.md file stored locally on our computer. Similar to previous method, you can confirm the RDD using the type method. Data partitioning is an important concept in Spark, and understanding how Spark deals with partitions allows one to control parallelism. A partition in Spark is the division of the large dataset, with each part being stored in multiple locations across the cluster. By default, Spark partitions the data at the time of creating RDD based on several factors such as available resources, sectional datasets, etc. However, this behavior can be controlled by passing a second argument called min partitions, which define the minimum number of partitions to be created for an RDD. In the first example, we create an RDD named numRDD from the list of 10 integers using the Spark context parallelize method with 6 partitions. In the second example, we create another RDD named fileRDD using Spark context textfile method with 6 partitions. The number of partitions in an RDD can always be found by using the getNumPartitions method. In the next video, you'll see the final method of creating RDDs. For now, let's create some RDDs. In the last video, you have learned how to load your data into RDDs. In this video, you'll learn about the various operations that support RDDs in PySpark. RDDs in PySpark supports two different types of operations, transformations and actions. Transformations are operations and RDDs that return a new RDD, and actions are operations that perform some computation on the RDD. The most important feature which helps RDDs in fault tolerance and optimizing resource use is the lazy evaluation. So what is lazy evaluation? Spark creates a graph from all the operations you perform on an RDD, and execution of the graph starts only when an action is performed on RDD, as shown in this figure. This is called lazy evaluation in Spark. The RDD transformations we will look in this video are map, filter, flat map, and union. The map transformation takes in a function and applies it to each element in the RDD. Say you have an input RDD with elements 1, 2, 3, 4. The map transformation takes in a function and applies it to each element in the RDD, with the result of the function being the new value of each element in the resulting RDD. In this example, the square function is applied to each element of the RDD. Let's understand this with an example. We first create an RDD using Spark context parallelize method on a list containing elements 1, 2, 3, 4. Next, we apply map transformation for squaring each element of the RDD. The filter transformation takes in a function and returns an RDD that only has elements that pass the condition. Suppose we have an input RDD with numbers 1, 2, 3, 4, and we want to select numbers greater than 2. We can apply the filter transformation. Here is an example of the filter transformation wherein we use the same RDD as before to apply filter transformation to filter out the numbers that are greater than 2. Flat map is similar to map transformation, except it returns multiple values for each element in the source RDD. A simple usage of flat map is splitting up an input string into words. Here you have an input RDD with two elements, hello world and how are you. Applying the split function of the flat map transformation results in 5 elements in the resulting RDD, hello, world, how, are you. As you can see, even though the input RDD has 2 elements, the output RDD now contains 5 elements. In this example, we create an RDD from a list containing the words hello world and how are you. Next, we apply flat map along with the split function on the RDD to split the input string into individual words. Union transformation returns the union of one RDD with another RDD. In this figure, we are filtering the input RDD and creating two RDDs, errors RDD and warnings RDD. And next, we are combining both the RDDs using the union transformation. To illustrate this using PySpark code, let's first create an input RDD from a local file using Spark context text file method. Next, we will use two filter transformation to create two RDDs, error RDD and warnings RDD. And finally, using union transformation, we will combine them both. So far, you have seen how RDD transformations work, but after applying transformations at some point, you will want to actually do something with your dataset. This is where actions come into picture. Actions are the operations that are applied on RDDs to return a value after running a computation. The 4 basic actions that you will learn in this lesson are collect, take, reduce, and count. Collect action returns complete list of the elements from the RDD, whereas take of n prints an n number of elements from the RDD. Continuing the map transformation example, executing collect returns all elements, that is 1, 4, 9, 16 from the RDD_map RDD that you created earlier. Simply, here is an example of take of 2 action that prints the first 2 elements, that is 1 and 4 from the RDD_map RDD. Sometimes you just want to print the first element of the RDD. First action returns the first element in an RDD. It is similar to take of 1. Here is an example of the first action which prints the first element, that is 1 from the RDD_map RDD. Finally, the count action is used to return the total number of rows or elements in the RDD. Here is an example of the count action to count the number of elements in the RDD_flatMap RDD. The result here indicates that there are 5 elements in the RDD_flatMap RDD. It's time for you to practice RDD operations in the last video, you were introduced to some basic RDD operations. And in this video, you learn how to work with RDDs of key value pairs, which are a common data type required for many operations in Spark. Most of the real-world datasets are generally key value pairs. An example of this kind of dataset has the team name as key and the list of players as values. The typical pattern of this kind of dataset is each row is a key that maps to one or more values. In order to deal with this kind of dataset, PySpark provides a special data structure called pair RDDs. In pair RDDs, the key refers to the identifier, whereas the value refers to the data. There are a number of ways to create pair RDDs. The 2 most common ways are creating from a list of the key value tuple or from a regular RDD. Irrespective of the method, the first step in creating pair RDDs is to get the data into key value form. Here is an example of creating pair RDD from a list of the key value tuple that contains the name as key and age as the value using Spark context parallelize method. And here is an example of creating pair RDD from regular RDDs. In this example, a regular RDD is created from a list that contains strings using Spark context parallelize method. Next, we create a pair RDD using map function, which returns tuple with key value pairs, with key being the name and age being the value. Pair RDDs are still RDDs, and thus all the transformations available to regular RDDs. Since pair RDDs contains tuples, we need to pass functions that operate on key value pairs. A few special operations are available for this kind, such as reduce by key, group by key, sort by key, and join. Let's take a look at each of these 4 pair RDD transformations in detail now. The reduce by key transformation is the most popular pair RDD transformation, which combines values with the same key using a function. Reduce by key runs several parallel operations, one for each key in the dataset. Because datasets can have very large number of keys, reduce by key is not implemented as an action. Instead, it returns a new RDD consisting of each key and the reduced value for that key. Here is an example of reduce by transformation that uses a function to combine all the goals scored by each of the players. The result shows that the player as key and the total number of goals scored as value. Sorting of data is necessary for many downstream applications. We can sort pair RDD as long as there is an ordering defined in the key. Sort by key transformation returns an RDD sorted by key in ascending or descending order. Continuing our reduce by key example, here is an example that sorts the data based on the number of goals scored by each player. A common use case of pair RDD is grouping the data by key. For example, viewing all of the airports for a particular country together. If the data is already keyed in the way that we want, The group by key operation groups all the values with the same key in the pair RDD. Here is an example of group by key transformation that groups all the airports for a particular country from an input list that contains the list of tuples. Each tuple consists of country code and the corresponding airport code. Join transformation joins two pair RDDs based on their key. Let's demonstrate this with an example. First, we create two RDDs. RDD1 contains the list of tuples with each tuple consisting of name and age, and RDD2 contains the list of tuples with each tuple consisting of name and income. Applying the join transformation on RDD1 and RDD2 merges two RDDs together by grouping elements with the same key. Here is an example that shows the result of join transformation of RDD1 and RDD2. Now that you have learned all about pair RDDs, it's time for you. Previously, you learned about advanced RDD transformations for key value datasets. Similar to advanced RDD transformations, there are advanced RDD actions which you will see in this video. Reduce action takes in a function which operates on two elements of the same type of RDD and returns a new element of the same type. The function should be commutative and associative so that it can be computed correctly in parallel. A simple example of such a function is plus, which we can use to sum our RDD. Here is an example of reduce action that calculates the sum of all the elements in an RDD. In this example, input RDD is created using Spark context parallelize method on a list consisting of numbers 1, 3, 4, 6. Executing reduce action results in 14, which is the sum of 1, 3, 4, 6. In many cases, it's not advisable to run collect action on RDDs because of the huge size of the data. In these cases, it's common to write data out to a distributed storage system such as UDFs or Amazon S3. Save as text file action can be used to save RDD as a text file inside a particular directory. By default, save as text file saves RDD with each partition as a separate file inside a directory. Here is an example of save as text file that saves an RDD with each partition as a separate file inside a directory. However, you can change it to return a new RDD that is reduced into a single partition using the coalesce method. Here is an example of save as text file that saves RDD as a single file inside a directory. Similar to pair RDD transformations, there are also RDD actions available for pair RDDs. However, pair RDDs also attain some additional actions of PySpark, especially those that leverage the advantages of data which is of key value nature. Let's take a look at two pair RDD actions, count by key and collect as map in this video. Count by key is only available on RDDs of type key value. With the count by key operation, we can count the number of elements for each key. Here is an example of counting the number of values for each key in the dataset. In this example, we first create a pair RDD named RDD using Spark context parallelize method. Since count by key generates a dictionary, next we iterate over the dictionary to print the unique key and the number of values associated with each key as shown here. One thing to note is that count by key should only be used in a dataset whose size is small enough to fit in a memory. Collect as map returns the key value pairs in the RDD as a dictionary. Here is an example of collect as map on a pair RDD. As before, we create a pair RDD using Spark context parallelize method and next use collect as map action. Collect as map produces the key value pairs in the RDD as a dictionary which can be used for downstream analysis. Similar to count by key, this action should only be used if the resulting data is expected to be small, as all the data is loaded into the memory. Let's practice some of these advanced actions on some test data in PySpark. In the previous chapter, you looked at RDDs, which is Spark's co-abstraction for working with data. In this chapter, we will explore PySpark SQL, which is Spark's high-level API for working with structured data. PySpark SQL is a Spark library for structured data. Unlike the PySpark RDD API, PySpark SQL provides more information about the structure of the data and the computation being performed. PySpark SQL provides a programming abstraction called DataFrames. A DataFrame is an immutable distributed collection of data with named columns. It is similar to a table in SQL. DataFrames are designed to process a large collection of structured data such as relational database and semi-structured data such as JSON or JavaScript object notation. DataFrame API currently supports several languages such as Python, R, Scala, and Java. DataFrames allow PySpark to query data using SQL, for example, select asterisk from table, or using the expression method, for example, df.select. Previously, you have learned about Spark context, which is the main entry point for creating RDDs. Similarly, SparkSession provides a single point of entry to interact with underlying Spark functionality and allows programming Spark with DataFrame API. The SparkSession does for DataFrames what the Spark context does for RDDs. A SparkSession can be used to create DataFrame, register DataFrame as tables, execute SQL over tables, cache tables, etc. Similar to Spark context, SparkSession is exposed to the PySpark shell as variable Spark. DataFrames in PySpark can be created in two main ways. From an existing RDD using SparkSession's create DataFrame method, and from different data sources such as CSV, JSON, text using SparkSession's read method. Before going into the details of creating DataFrames, let's understand what schema is. Schema is the structure of data in DataFrames and helps Spark to optimize queries on the data more efficiently. A schema provides informational details such as the column name, the type of data in that column, and whether null or empty values are allowed in the column. To create a data frame from an RDD, we will need to pass an RDD and a schema into SparkSession's create data frame method. In this example, we will first create an RDD named iPhones_RDD from a list of iPhones using Spark context parallelize method. Next, we will create a data frame using SparkSession's create data frame method using iPhones_RDD and the list of column names such as model, year, height, width, and weight as schema. The type of object created can be confirmed using type method, which shows that it is a PySpark data frame. A thing to note here is when the schema is a list of column names, the type of each column will be inferred from data as shown above. However, when the schema is none, it will try to infer the schema from the data. To create a data frame from CSV, JSON, text, txt files, we will make use of the SparkSession's spark.read property. Here is an example of create df_csv data frame from people.csv file using spark.read.csv method. Similarly, here is an example for creating df_json data frame from people.json file using spark.read.csv JSON method. Finally, here is an example for creating df_txt data frame from people.txt file using spark.read.txt method. Irrespective of the file type, this method requires the path to the file and two optional parameters. The first optional parameter, header equals to true, may be passed to make sure that the method treats the first row as column names. The second optional parameter, infer schema equals to true, may be passed to instruct the data frame reader to infer the schema from the data, and by doing so, it will attempt to assign the right data type to each column based on the content. Now let's practice creating some data frames. Just like RDDs, data frames also support both transformations and actions. In this video, you learned some data frame operations in PySpark. Similar to RDD operations, the data frame operations in PySpark can be divided into transformations and actions. PySpark data frame provides operations to filter, group, or compute aggregates and can be used with PySpark SQL. Let's explore some of the most common data frame transformations such as select, filter, group by, order by, drop duplicates with column renamed, and some common data frame actions such as print schema, show, count, columns, and describe in this video. Let's start with select and show operations. The select transformation is used to extract one or more columns from a data frame. We need to pass the column name inside select operation. As an example, let's select A's column from a test data frame. Select is a transformation, and so it creates a new data frame, and in order to print the rows from df_id_A's data frame, we need to execute an action. Show is an action that prints the first 20 rows by default. Let's apply show of 3 on df_id_A's data frame and print the first 3 rows as shown in this example. Unlike select, the filter transformation selects only rows that pass the condition specified. The parameter you specified is the column name and the value of what you want to filter that column on. For example, if you want to filter out the rows with A's greater than 21, we pass the column expression new_df.A's and the condition greater than 21 as shown in here. We can use show of 3 action to print out the first 3 rows from the new data frame. The GroupBy transformation groups the data frame using the specified columns, so we can run aggregations on them. To better understand, we will first group the A's column and create another data frame. Then we will use count action that returns the total number of rows in the data frame, and finally use show of 3 operation to print the first 3 rows in the data frame. The result is a table that shows the first 3 A's groups and the corresponding number of members in each group. Order by transformation returns a data frame sorted by the given columns. Let's sort the test_df_A's_group.count that we obtained in the previous example based on A's column and print out the first 3 rows of the data frame using the show of 3 action. As you can see, the A's group has been sorted in ascending order now. The drop duplicate transformation returns a new data frame with duplicate rows removed. Here is an example where drop duplicate transformation is used to remove duplicate rows in user_id, A's, and gender columns, and finally creating a new data frame. You can execute count action on this new data frame to print the number of non-duplicate rows. The with column rename transformation returns a new data frame by renaming an existing column. It takes 2 arguments, the name of the old and new columns. In this example, we rename the column name gender to sex and create a test_df_sex. We can use show of 3 action to print out the first 3 rows from the new data frame. To check the type of columns in the data frame, we can use the print schema action. Here is an example of print schema action on test_df data frame that we used previously. Print schema prints out the schema in tree format as shown here and helps to spot the issues with the schema of the data. As an example, product ID is shown as string even though it is supposed to be an integer. The column operation returns the names of all the columns in the data frame as an array of string. Let's print the column names in test_df data frame. In this example, the test_df data frame has 3 columns: user ID, gender, and A's. Describe operation is used to calculate the summary statistics of the numerical columns in the data frame. If you don't specify the name of columns, it will calculate summary statistics for all numerical columns present in the data frame as shown in this example. Now that you are familiar with data frame operations, let's practice using some of these operations on real. Previously, you have seen how to interact with PySpark SQL using DataFrame API. In this video, you learn how to interact with PySpark SQL using SQL query. In addition to DataFrame API, PySpark SQL allows you to manipulate data frames with SQL queries. What you can do using a DataFrame API can be done using SQL queries and vice versa. So what are the differences between DataFrame API and SQL queries? The DataFrame API provides a programmatic interface, basically a domain-specific language or DSL for interacting with data. DataFrame queries are much more easier to construct programmatically. Plain SQL queries can be significantly more concise and easier to understand. They are also portable and can be used without any modifications with every supported language. Many of the data frame operations that you have seen in the previous chapter can be done using SQL queries. The SparkSession provides a method called SQL, which can be used to execute a SQL query. The SQL method takes a SQL statement as an argument and returns a data frame representing the result of the given query. Unfortunately, SQL queries cannot be run directly against a data frame. To issue SQL queries against an existing data frame, we can leverage the create or replace temp view function to build a temporary table as shown in this example. After creating the temporary table, we can simply use the SQL method, which allows us to write SQL code to manipulate the data within a data frame. In this example, we simply extract two columns, field 1 and field 2, from the table using select. Since the result is a data frame, you can run data frame actions such as collect, first, show, etc. An example of collect action is shown here. In the previous lesson, you have seen how to use select operation to subset the data from a data frame. Here is an example of how you can do the same with a SQL query. In this example, we will first construct the query for selecting the product ID column from the temporary table. Next, we will pass the query to the SparkSession's SQL method to create a new data frame. Because the result of SQL query returns a data frame, all the usual data frame operations are available. Here we can use show of 5 action to print the first 5 rows of the data frame. The SQL queries are not limited to extracting data as seen in the previous slide. We can also create SQL queries to run aggregations. In this example, we first construct a query for selecting A's and purchase columns, then aggregate the total of all the purchases, the maximum per age group. We can then provide the query to SparkSession's SQL method and use show of 5 action to print out the first 5 rows as shown in here. In addition to extracting and summarizing the data, Spark SQL queries can also be constructed for filtering the rows from a data frame. Suppose you want to filter out the rows of age, purchase, and gender columns where the gender is female and the purchase is greater than 20,000. You can construct a query as shown in this example. You can confirm whether or not query worked by providing the query to the SparkSession's SQL method and using show of 5 action to print out the first 5 rows as shown in this example. Let's practice some SQL within PySpark. Visualization is an essential part of data analysis. In this video, we will explore some visualization methods that can help us make sense of our data in PySpark DataFrames. Data visualization is the way of representing your data in the form of graphs or charts. It is considered a crucial component of exploratory data analysis. Several open source tools exist to aid visualization in Python such as Matplotlib, Seaborn, Bokeh, etc. However, none of these visualization tools can be used directly with PySpark's data frames. Currently, there are 3 different methods available to create charts using PySpark data frames: PySpark Dist Explore library, 2Pandas method, and HandySpark library. Let's understand each of these methods with examples. PySpark Dist Explore is a plotting library to get quick insights and data in PySpark data frames. There are 3 functions available in PySpark Dist Explore to create Matplotlib graphs while minimizing the amount of computation needed: hist, distplot, and pandas_histogram. Here is an example of creating a histogram using PySpark Dist Explore package on the test_df data. First, the CSV file is loaded into Spark DataFrame using the SparkSession's read.csv method. Then we select the age column from the test_df data frame using the select operation. Finally, we use the hist function of the PySpark Dist Explore package to plot a histogram of age in the test_df_age dataset. The second method of creating charts is by using 2Pandas on PySpark data frames, which converts the PySpark data frame into Pandas data frame. After conversion, it's easy to create charts from Pandas data frames using Matplotlib or Seaborn plotting libraries. In this example, first, the CSV is loaded in Spark DataFrame using the read.csv method. Next, using 2Pandas method, we will convert the Spark DataFrame into Pandas DataFrame. Finally, we will create a histogram of the A's column using Matplotlib's hist method. Before we look at the third method, let's take a look at the differences between Pandas versus Spark DataFrames. Pandas won't work in every case. It is a single machine tool and constrained by single machine limits. So the size is limited by your server memory and you will process them with the power of single server. In contrast, operations on PySpark DataFrames run parallel on different nodes in the cluster. In Pandas DataFrames, we get the result as soon as we apply any operation, whereas operations in PySpark DataFrames are lazy in nature. You can change a Pandas DataFrame using methods. We can't change a PySpark DataFrame due to its immutable property. Finally, the Pandas API supports more operations than PySpark DataFrames. The final method of creating charts is using the HandySpark library, which is relatively a new package. HandySpark is designed to improve PySpark user experience, especially when it comes to exploratory data analysis, including visualization capabilities. It makes fetching data or computing statistics for columns really easy, returning Pandas objects straight away. It brings the long missing capability of plotting data while retaining the advantages of performing the distributed computation. Here is an example of HandySpark method for creating a histogram. Just like before, we load the CSV into a PySpark DataFrame using the SparkSession's read.csv method. After creating the DataFrame, we convert the DataFrame to a HandySpark DataFrame using the toHandy method. Finally, we create a histogram of the A's column using the hist function of HandySpark library. We have learned 3 exciting methods of visualizing PySpark DataFrames, and let's practice creating some charts with them now on real world. In the last chapter, you learned about PySpark SQL, which is one of the high-level API built on top of Spark Core for structured data. In this chapter, you learn about PySpark MLlib, which is a built-in library for scalable machine learning. Before diving deep into PySpark MLlib, let's quickly define what machine learning is. According to Wikipedia, machine learning is a scientific discipline that explores the construction and study of algorithms that can learn from data. PySpark MLlib is a machine learning library. Its goal is to make practical machine learning scalable and easy. At a high level, PySpark MLlib provides tools such as machine learning algorithms, which include collaborative filtering, classification and regression, and clustering. Featureization, which include feature extraction, transformation, dimensionality reduction, and selection. Pipelines, which include constructing, evaluating, and tuning machine learning pipelines. In this chapter, we will explore machine learning algorithms, collaborative filtering, classification, and clustering. Many of you have heard about scikit-learn, which is a very popular and easy to use Python library for machine learning. Then what is the need for PySpark MLlib? Scikit-learn algorithms work well for small to medium-sized datasets that can be processed on a single machine, but not for large datasets that require the power of parallel processing. On the other hand, PySpark MLlib only contains algorithms in which operations can be applied in parallel across nodes in a cluster. Unlike scikit-learn, MLlib supports several other high-level languages such as Scala, Java, and R in addition to Python. MLlib also provides a high-level API to build machine learning pipelines. A machine learning pipeline is a complete workflow combining multiple machine learning algorithms together. PySpark is good for iterative algorithms, and using iterative algorithms, many machine learning algorithms have been implemented in PySpark MLlib. PySpark currently supports various methods for binary classification, multi-class classification, and regression analysis. Some of the algorithms include linear SVMs, logistic regression, decision trees, random forests, gradient boosted trees, naive Bayes, linear least squares, lasso, ridge regression, isotonic regression. Collaborative filtering is commonly used for recommender systems, and PySpark MLlib uses the alternative least squares or ALS algorithm for collaborative filtering. Clustering algorithm consists of k-means, Gaussian mixture, power iteration clustering, bisecting k-means, and streaming k-means. While PySpark MLlib includes several machine learning algorithms, we will specifically focus on three key areas, often referred to as the 3 C's of machine learning: collaborative filtering, classification, and clustering. Collaborative filtering produces recommendations based on past behavior, preferences, or similarities to known entities or users. Classification is the problem of identifying to which of a set of categories a new observation belongs. Clustering is grouping of data into clusters based on similar characteristics. We will go in more details in the next few lessons. Now that you learned the 3 C's of machine learning, let's quickly understand how we can import these PySpark MLlib libraries in the PySpark shell environment. Let's start with PySpark's collaborative filtering, which is available in pyspark.mllib.recommendation submodule. Here is how you import the ALS or alternative least square class in PySpark shell. For binary classification, here is an example of how you import logistic regression with LBFGS class in the pyspark.mllib.classification submodule inside the PySpark shell. Similarly, for clustering, here is an example of importing the k-means class in PySpark shell using the pyspark.mllib.clustering submodule. Let's practice how well you understand the different machine learning algorithms by importing them. In the previous video, you have been introduced with the 3 C's of machine learning. In this video, we'll start with the first C, which is collaborative filtering, and gain a basic understanding of recommender systems in Spark. Let's get started. Collaborative filtering is a method of making automatic predictions about the interests of a user by collecting preferences or taste information from many users. Collaborative filtering is one of the most commonly used algorithms in recommender systems. Collaborative filtering has two approaches: the user-user approach and item-item approach. The user-user approach finds users that are similar to the target user and uses the collaborative ratings to make recommendations for the target user. The item-item approach finds and recommends items that are similar or related to items associated with the target user. Now let's take a look at different components that are needed to build a recommendation system in PySpark. The rating class in pyspark.mllib.recommendation submodule is a wrapper around tuple of user, product, and rating. The rating class is useful for parsing the RDD and creating a tuple of user, product, and rating. Here is a simple example of how you can create an instance of rating class R with the values of user equals to 1, product equals to 2, and rating equals to 5.0. Once the rating class is created, you can extract the user, product, and rating value using the index of R instance. In this example, R of 0, R of 1, and R of 2 shows the user ID, product ID, and ratings for the R instance. Splitting the data into training and testing sets is an integral part of machine learning. The training portion will be used to train the model, while the testing data is used to evaluate the model's performance. Typically, a large portion of the data is assigned for training and a small portion for testing. PySpark's random split function can be used to randomly split the data with the provided weights and return multiple RDDs. In this example, we first create an RDD which consists of numbers 1 to 10, and using random split function, we create two RDDs with 60 to 40 ratio. The output of the random split function shows training RDDs contain 6 elements, whereas the test RDD contains 4 elements. The alternating least squares or ALS algorithm available in spark.mllib helps to find products that the customers might like based on their previous purchases or ratings. The ALS.train method requires that we represent rating objects as user ID, items ID, rating tuples, along with the training parameters, rank, and iterations. Rank represents the number of features. Iterations represent the number of iterations to run the least square computation. Here is an example of running the ALS model. First, We create an RDD from a list of rating objects and print out the contents of the RDD using collect action. Next, we use als.train to train the training data as shown in this example. After training the model, the next step is predicting the ratings for the user ID and product pairs. The predictAll method takes an RDD of user ID and product ID pairs and returns a prediction for each pair. In order to get the example to work, let's create an RDD from a list of tuples containing user ID and product ID using Spark context parallelize method. Next, we apply the predictAll method on the unrated underscore RDD. Running collect action and prediction shows a list of predicted ratings generated by ALS model for the user ID 1 and product IDs 1 and 2. For evaluating the model trained using ALS, we can use the mean squared error or MSE. The MSE measures the average of the squares of the errors between what is estimated and the existing data. Continuing on our previous example, we'll first organize our ratings and predictions data to make user product the rating. Next, we will join the ratings RDD with the prediction RDD and the result looks as follows. Finally, we apply a square difference function to the map transformation of the rates underscore preds RDD and then use the mean to get the MSE. Now, it's your turn to try your hand at collaborative filtering. In the previous video, you learned about collaborative filtering, which is the first C of machine learning algorithms in PySpark MLlib. In this video, you learn about the second C of machine learning, which is classification. Classification is a popular machine learning algorithm that identifies which category an item belongs to. For example, whether an email is spam or non-spam based on labeled examples of other items. Classification takes a set of data with known labels and predetermined features and learns how to label new records based on that information. That is why classification comes under a supervised learning technique. Classifications can be divided into two different types, binary classification and multi-class classification. In binary classification, we want to classify entities into two distinct categories, for example, determining whether a cancer type is malignant or not. PySpark MLlib supports various methods for binary classification such as linear SVMs, logistic regression, decision trees, random forests, gradient boosted trees, naive Bayes. In multi-class classification, we want to classify entities into more than two categories, for example, determining what category a news article belongs to. PySpark MLlib supports various methods for multi-class classification such as logistic regression, decision trees, random forest, naive Bayes. Let's focus on logistic regression, which is the most popular supervised machine learning method. Logistic regression is a classification method to predict a binary response given some independent variable. It measures the relationship between the label on the y-axis and features on the x-axis using a logistic function as shown in this figure. In logistic regression, the output must be 0 or 1. The convention is if the probability is greater than 50%, then the logistic regression output is 1, otherwise it is 0. PySpark MLlib contains a few specific data types such as vectors and labeled point. Let's understand each of these data types. Vectors in PySpark MLlib comes in two flavors, dense and sparse. Dense vectors store all their entries in an array of floating point numbers. For example, a vector of 100 will contain 100 double values. In contrast, sparse vector stores only the non-zero values and their indices. Here is an example of creating a dense vector of 1, 2, 3 using vectors dense method. And here is an example of creating a sparse vector with the size of the vector equals to 4 and non-zero entities 1, 1.0, 3, 5.5 as a dictionary using vectors sparse method. A labeled point is a wrapper around the input features and the predicted value. Labeled point includes a label and a feature vector. The label is a floating point value, and in the case of binary classification, it is either 1, positive, or 0, negative. This example shows a positive label point with label 1 and a feature vector 1.0, 0.0, 3.0, and a negative label point with label 0 and feature vector 2.0, 1.0, 1.0. PySpark MLlib has an algorithm called hashing TF that computes a term frequency vector of a given size from a document. Let's illustrate this with an example. In this simple example, first we will split the sentence "Hello, hello world" into a list of words using the split method, and we will create vectors of size 10,000. Finally, we compute the term frequency vector by using TF's transform method on the words. As you can see, the sentence is turned into a sparse vector holding feature number and the occurrences of each word. Among several algorithms, the popular algorithm available for logistic regression is PySpark MLlib is LBFGS. The minimum requirement for logistic regression with LBFGS is an RDD of labeled point. To understand how logistic regression works, let's see a simple example. We first create a list of labeled points with labels 0 and 1, and then using Spark context parallelize method, we will create an RDD. Then we will use logistic regression with lbfgs.train method to train a logistic regression model on the RDD. Once the model is trained from logistic regression with lbfgs algorithm, the predict method computes a score between 0 and 1 for each point as shown here. Now it's your turn to practice classification using. In the previous video, you learned about classification, a type of supervised learning method. But what if we want to make sense of unlabeled data? In this video, you learn about clustering, which is a type of unsupervised learning method to group unlabeled data together. So what exactly is clustering? Clustering is the unsupervised learning task that involves grouping objects into clusters of high similarity with no labels. Unlike the supervised learning methods that you have seen before, such as collaborative filtering and classification where data is labeled, clustering can be used to make sense of unlabeled data. PySpark MLlib library offers a handful of clustering models such as k-means clustering, Gaussian mixture clustering, power iteration clustering, bisecting k-means clustering, and streaming k-means clustering. In this video, we will focus on k-means clustering because of its simplicity and popularity. K-means is an unsupervised method that takes data points in an input data and will identify which data points belong to each one of the clusters. As shown in the left side of the figure, we can provide n data points and a predefined number of k clusters. The k-means algorithm, through a series of iterations, create clusters as shown on the right side of the figure. The k-means clustering minimally requires that the data is a set of numerical features and that we specify the target number of k clusters ahead. The first step in implementing the k-means clustering algorithm using PySpark MLlib is loading the numerical data into an RDD and then parsing the data based on a delimiter. Here is an example of how you load a CSV file into an RDD using Spark context text file method, then parsing the RDD based on a comma delimiter, and finally converting the floats to integers. The contents of the first 5 lines of RDD can be printed using take of 5. As you can see, the dataset contains 2 columns, each column indicating a feature loaded into an RDD. Like other algorithms, you invoke k-means by calling k-means.train method, which takes an RDD, the number of clusters we expect, and the maximum number of iterations allowed. Continuing our previous example, first we can import the k-means class from pyspark.mllib.clustering submodule. Next, we call k-means.train method on RDD and the 2 parameters k equals to 2 and the maximum iterations equals to 10. K-means.train returns a k-means model that lets you access the cluster centers using the model.clusterCenters method. An example of cluster centers for k equals to 2 is shown here. The next step in k-means clustering is to evaluate the model by computing the error function. Unfortunately, PySpark k-means algorithm doesn't have a method already, so we have to write a function by ourselves as shown here. We will next apply the error function on the RDD and calculate within set sum of squared error. Continuing our previous example, we apply map transformation of error function to our input RDD to calculate within set sum of squared error, which is 77.96 in this example. An optional but highly recommended step in k-means clustering is cluster visualization. Continuing from a previous example, let's first create a scatter plot of the two feature columns in the sample data. Next, overlay it with the cluster centers from the k-means model, which are indicated by the colored X's in this figure. The purple and yellow colors here represent the labels created from the model based on k, which is 2 in this example. As you can see, the overlaid scatter plot shows a reasonable clustering with the two centroids or cluster centers placed in the center of each of the cluster. Now, let's quickly take a look at the code to generate the previous plot. As seen previously, plotting libraries doesn't work that directly on RDDs and DataFrames. As shown here, we first convert RDD to Spark DataFrame and then to Pandas DataFrame. We also convert the cluster centers from k-means model into a Pandas DataFrame. Finally, we use PLT function in matplotlib library to create an overlaid scatter plot as shown in this previous slide. Let's use a real-world data and generate some nice clusters using PySpark MLlib k-means cluster. Congratulations on successfully completing Fundamentals of Big Data via PySpark course. Our goal through this course was to equip you with a basic understanding of big data and show how Apache Spark can be used to perform powerful data analysis at scale. Let's quickly review what you have learned so far in this course and recommend you a few courses that you can take next. Analyzing big data is equivalent to conducting both descriptive and inferential analysis using distributed computing techniques such as Spark, with the hope that the volume, velocity, variety of big data that makes distributed computing necessary will lead into deeper or more targeted insights. Chapter 1 started with the fundamentals of big data and introduced Apache Spark as an open source distributed big data processing engine, as well as its different components, namely Spark Core, Spark SQL, Spark MLlib, Graphics, and Spark Streaming. Because Python is one of the most popular languages for data science, we looked specifically at how you might use PySpark, which is Spark's Python API, to execute Spark jobs, and PySpark Shell to develop Spark's interactive applications in Python. Finally, you learned about the two different modes of running Spark, namely local mode and cluster mode. Chapter 2 introduced PySpark RDD, which is the main API in Spark Core for processing unstructured data. We learned about the different features of RDDs, different methods of creating RDDs, and finally RDD operations, namely transformations and actions. Chapter 3 explored PySpark SQL, which is Spark's high-level API for working with structured data. PySpark SQL creates DataFrames, which provides more information about the structure of data and the computation being performed. We looked at the different methods of creating DataFrames, DataFrame operations, namely transformations and actions, and finally different methods of visualizing big data using DataFrames. Chapter 4 delved deep into PySpark MLlib, Spark's built-in library for machine learning, and discussed how PySpark MLlib makes practical machine learning scalable and easy. This chapter also introduced the 3 C's of MLlib: collaborative filtering, classification, and clustering. The ecosystem of Apache Spark is vast and ever-expanding, but throughout the course, we have discussed the essential underlying concepts. Where you choose to go from here, whether that be experimenting and applying some of these tools and patterns on your own, or investigating Spark components such as Spark SQL or Spark MLlib more deeply, is up to you. But we hope that the concepts, tools, and techniques that we are introduced in this course have provided a well-informed starting point and continue to serve as a basis for you to refer back to throughout your distributed data analysis journey. With this general understanding of PySpark, we would encourage you to look at other DataCamp PySpark courses focused on feature engineering and recommended engines to further.
Welcome to Data Cleaning in Apache Spark with Python. My name is Mike Metzger. I'm a data engineering consultant, and I will be your instructor for this course. We will cover what data cleaning is, why it's important, and how to implement it with Spark and Python. Let's get started. In this course, we'll define data cleaning as preparing raw data for use in processing pipelines. We'll discuss what a pipeline is later on, but for now it's sufficient to say that data cleaning is a necessary part of any production data system. If your data isn't clean, it's not trustworthy and could cause problems later on. There are many tasks that could fall under the data cleaning umbrella. A few of these include reformatting or replacing text, performing calculations based on the data, and removing garbage or incomplete data. Most data cleaning systems have two big problems: optimizing performance and organizing the flow of data. A typical programming language, such as Perl, C++, or even standard SQL, may be able to clean data when you have small quantities of data. But consider what happens when you have millions or even billions of pieces of data. Those languages wouldn't be able to process that amount of information in a timely manner. Spark lets you scale your data processing capacity as your requirements evolve. Beyond the performance issues, dealing with large quantities of data requires a process or pipeline of steps. Spark allows management of many complex tasks within a single framework. Here's an example of cleaning a small data set. We're given a table of names, age in years, and a city. Our requirements are for a data frame with first and last name in separate columns, the age in months, and which state the city is in. We also want to remove any rows where the data is out of the ordinary. Using Spark transformations, we can create a data frame with these properties and continue processing afterwards. A primary function of data cleaning is to verify all data is in the expected format. Spark provides a built-in ability to validate datasets with schemas. You may have used schemas before with databases or XML. Spark is similar. A schema defines and validates the number and types of columns for a given data frame. A schema can contain many different types of data: integers, floats, dates, strings, and even arrays or mapping structures. A defined schema allows Spark to filter out data that doesn't conform during read, ensuring expected correctness. In addition, schemas also have performance benefits. Normally, a data import will try to infer a schema on read. This requires reading the data twice. Defining a schema limits this to a single read operation. Here's an example schema to import the data from our previous example. First, we'll import the PySpark.sql.types library. Next, we'll define the actual struct type list of struct fields, containing an entry for each field in the data. Each struct field consists of a field name, data type, and whether the data can be null. Once our schema is defined, we can add it into our spark.read.format.load call and process it against our data. The load method takes two arguments, the file name and a schema. This is where we apply our schema to the data being loaded. We've gone over a lot of information regarding data cleaning and the importance of DataFrame schemas. Let's put that information to use and practice. Welcome back. We've had a quick discussion about data cleaning, data types, and schemas. Let's move on to some further Spark concepts: immutability and lazy processing. Normally in Python and most other languages, variables are fully mutable. The values can be changed at any given time, assuming the scope of the variable is valid. While very flexible, this does present problems anytime there are multiple concurrent components trying to modify the same data. Most languages work around these issues using constructs like mutexes and semaphores, etc. This can add complexity, especially with non-trivial programs. Unlike typical Python variables, Spark data frames are immutable. While not strictly required, immutability is often a component of functional programming. We won't go into everything that implies here, but understand that Spark is designed to use immutable objects. Practically, this means Spark data frames are defined once and are not modifiable after initialization. If the variable name is reused, the original data is removed, assuming it's not in use elsewhere, and the variable name is reassigned to the new data. While this seems inefficient, it actually allows Spark to share data between all cluster components. It can do so without worry about concurrent data objects. This is a quick example of the immutability of data frames in Spark. It's okay if you don't understand the actual code. This example is more about the concepts of what happens. First, we create a data frame from a CSV file called voterdata.csv. This creates a new data frame definition and assigns it to the variable name voter_df. Once created, we want to do two further operations. The first is to create a full year column by using a 2-digit year present in the dataset and adding 2000 to each entry. This does not actually change the data frame at all. It copies the original definition, adds the transformation, and assigns it to the voter_df variable name. Our second operation is similar. Now we want to drop the original year column from the data frame. Again, this copies the definition, adds a transformation, and reassigns the variable name to this new object. The original objects are destroyed. Please note that the original year column is now permanently gone from this instance, though not from the underlying data. For example, you could simply reload it into a new data frame if desired. You may be wondering how Spark does this so quickly, especially on large datasets. Spark can do this because of something called lazy processing. Lazy processing in Spark is the idea that very little actually happens until an action is performed. In our previous example, we read a CSV file, added a new column, and deleted another. The trick is that no data was actually read, added, or modified. We only updated the instructions, aka transformations, for what we wanted Spark to do. This functionality allows Spark to perform the most efficient set of operations to get the desired result. The code example is the same as the previous slide, but with the added count method call. This classifies as an action in Spark and will process all the transformation operations. These concepts can be a little tricky to grasp without some examples. Let's practice these ideas in the coming exercises. Welcome back. As we've seen, Spark can read in text and CSV files. While this gives us access to many data sources, it's not always the most convenient format to work with. Let's take a look at a few problems with CSV files. Some common issues with CSV files include: the schema is not defined. There are no data types included, nor column names beyond a header row. Using content containing a comma or another delimiter requires escaping. Using the escape character within the content requires even further escaping. The available encoding formats are limited depending on the language used. In addition to the issues with CSV files in general, Spark has some specific problems processing CSV data. CSV files are quite slow to import and parse. The files cannot be shared between workers during the import process. If no schema is defined, all data must be read before a schema can be inferred. Spark has a feature known as predicate pushdown. Basically, this is the idea of ordering tasks to do the least amount of work. Filtering data prior to processing is one of the primary optimizations of predicate pushdown. This drastically reduces the amount of information that must be processed in large datasets. Unfortunately, you cannot filter the CSV data via predicate pushdown. Finally, Spark processes are often multi-step and may utilize an intermediate file representation. These representations allow data to be used later without regenerating the data from source. Using CSV would instead require a significant amount of extra work defining schemas, encoding formats, etc. Parquet is a compressed columnar data format developed for use in any Hadoop-based system. This includes Spark, Hadoop, Apache Impala, and so forth. The Parquet format is structured with data accessible in chunks, allowing efficient read-write operations without processing the entire file. This structured format supports Spark's predicate pushdown functionality, providing significant performance improvement. Finally, Parquet files automatically include schema information and handle data encoding. This is perfect for intermediary or on-disk representation of processed data. Note that Parquet files are a binary file format and can only be used with the proper tools. This is in contrast to CSV files, which can be edited with any text editor. Interacting with Parquet files is very straightforward. To read a Parquet file into a data frame, you have two options. The first is using the spark.read.format method we've seen previously. The data frame, df equals spark.read.format parquet.load filename.parquet. The second option is the shortcut version. The DataFrame df equals spark.read.parquet filename.parquet. Typically, the shortcut version is the easiest to use, but you can use them interchangeably. Writing Parquet files is similar, using either df.write.format parquet.save filename.parquet or df.write.parquet filename.parquet. The long-form versions of each permit extra option flags, such as when overwriting an existing Parquet file. Parquet files have various uses within Spark. We've discussed using them as an intermediate data format, but they are also perfect for performing SQL operations. To perform a SQL query against a Parquet file, we first need to create a data frame via the spark.read.parquet method. Once we have the data frame, we can use the create or replace temp view method to add an alias of the Parquet data as a SQL table. Finally, we run our query using normal SQL syntax and the spark.sql method. In this case, we're looking for all flights with a duration under 100 minutes. Because we're using Parquet as the backing store, we get all the performance benefits we've discussed previously, primarily defined schemas and the available use of predicate pushdown. You've seen a bit about what a Parquet file is and why we'd want to use them. Now let's practice working with Parquet files. Welcome back. In the first chapter, we've spent some time discussing the basics of Spark data and file handling. Let's now take a look at how to use Spark column operations to clean data. Before we discuss manipulating data frames in depth, let's talk about some of their features. Data frames are made up of rows and columns, and are generally analogous to a database table. Data frames are immutable. Any change to the structure or content of the data creates a new data frame. Data frames are modified through the use of transformations. An example is the filter command to only return rows where the name starts with the letter M. Another operation is select, in this case returning only the name and position fields. There are many different transformations for use on a data frame. They vary depending on what you'd like to do. Some common transformations include the filter clause, which includes only rows that satisfy the requirement defined in the argument. This is analogous to the where clause in SQL. Spark includes a where alias you can use in place of filter if desired. This call returns only rows where the vote occurred after January 1st, 2019. Another common option is the select method, which returns the columns requested from the data frame. The with column method creates a new column in the data frame. The first argument is the name of the column, and the second is the command to create it. In this case, we create a column called year with just the year information. We can also use the drop method to remove a column from a data frame. Among the most common operations used when cleaning a data frame, filtering lets us use only the data matching our desired result. We can use filter for many tasks, such as removing null values, removing odd entries, anything that doesn't fit our desired format. We can also split a data frame containing combined data, such as a syslog file. As mentioned previously, use the filter method to return only rows that meet the specified criteria. The contains function takes a string argument that the column must have to return true. You can negate these results using the tilde character. Some of the most common operations used in data cleaning are modifying and converting strings. You will typically apply these to each column as a transformation. Many of these functions are in the spark.sql.functions library. For brevity, we'll import it as the alias f. We use the with column function to create a new column called upper using PySpark.sql.functions.upper on the name column. The upper column will contain uppercase versions of all names. We can create intermediary columns that are only for processing. This is useful to clarify complex transformations requiring multiple steps. In this instance, we call the split function with the name of the column and the space character to split on. This returns a list of words in a column called splits. A very common operation is converting string data to a different type, such as converting a string column to an integer. we use the cast function to perform the conversion to an integer type. While performing data cleaning with Spark, you may need to interact with array type columns. These are analogous to lists in normal Python environments. One function we will use is size, which returns the number of items present in the specified array type argument. Another commonly used function for array types is getItem. It takes an index argument and returns the item present at that index in the list column. Spark has many more transformations and utility functions available. When using Spark in production, make sure to reference the documentation for available options. We've discussed some of the common operations used on Spark DataFrame columns. Let's practice some of these now. We've looked at some of the power available when using Spark's functions to filter and modify our data frames. Let's spend some time with some more advanced options. The data frame transformations we've covered thus far are blanket transformations, meaning they're applied regardless of the data. Often, you'll want to conditionally change some aspect of the contents. Spark provides some built-in conditional clauses which act similar to an if-then-else statement in a traditional programming environment. While it is possible to perform a traditional if-then-else style statement in Spark, it can lead to serious performance degradation as each row of a data frame would be evaluated independently. Using the optimized built-in conditionals alleviates this. There are two components to the conditional clauses, when and the optional otherwise. Let's look at them in more depth. The when clause is a method available from the PySpark.sql.functions library that is looking for two components, the if condition and what to do if it evaluates to true. This is best seen from an example. Consider a data frame with the name and age columns. We can actually add an extra argument to our select method when using the when clause. We select the df.name and df.age as usual. For the third argument, we'll define a when conditional. If the age column is 18 or up, we'll add the string adult. If the clause doesn't match, nothing is returned. Note that our returned data frame contains an unnamed column we didn't define using withColumn. The select function can create columns dynamically based on the arguments provided. Let's look at some more examples. You can chain multiple when statements together, similar to an if-else-if structure. In this case, we define two when clauses and return adult or minor based on the age column. You can chain as many when clauses together as required. In addition to when is the otherwise clause. Otherwise is analogous to the else statement. It takes a single argument, which is what to return in case the when clause or clauses do not evaluate as true. In this example, we return adult when the age column is 18 or higher. Otherwise, we return minor. The resulting data frame is the same, but the method is different. While you can have multiple when statements chained together, you can only have a single otherwise per when chain. Let's try a couple of examples of using when and otherwise to modify some data frames. We've looked at the built-in functions in Spark, and I've had great results using these. But let's consider what you would do if you needed to apply some custom logic to your data cleaning processes. A user-defined function, or UDF, is a Python method that the user writes to perform a specific bit of logic. Once written, the method is called via the PySpark.sql.functions.udf method. The result is stored as a variable and can be called as a normal Spark function. Let's look at a couple examples. Here's a fairly trivial example to illustrate how a UDF is defined. First, we define a Python function. We'll call our function reverseString with an argument called myStir. We'll use some Python shorthand to reverse the string and return it. Don't worry about understanding how the return statement works, only that it will reverse the lettering of whatever is fed into it. For example, help becomes PLEH. The next step is to wrap the function and store it in a variable for later use. We'll use the PySpark.sql.functions.udf method. It takes two arguments, the name of the method you just defined and the Spark data type it will return. This can be any of the options in PySpark.sql.types and can even be a more complex type, including a fully defined schema object. Most often, you'll return either a simple object type or perhaps an array type. We'll call UDF with our new method name and use the string type, then store this as UDF reverse string. Finally, we use our new UDF to add a column to the userdf DataFrame within the withColumn method. Note that we pass the column we're interested in as the argument to UDF reverse string. The UDF function is called for each row of the DataFrame. Under the hood, the UDF function takes the value stored for the specified column, per row, and passes it to the Python method. The result is fed back to the resulting DataFrame. Another quick example is using a function that does not require an argument. We're defining our sorting cap function to return one of the letters G, H, R, or S at random. We still create our UDF wrap function and define the return type as string type. The primary difference is calling the function, this time without passing in an argument as it is not required. As always, the best way to learn is practice. Let's create some user-defined functions. Welcome back to our discussion about modifying and cleaning data frames. We've discussed various transformations and methods to modify our data, but we haven't covered much about how Spark actually processes the data. Let's look at that now. Spark breaks data frames into partitions, or chunks of data. These partitions can be automatically defined, enlarged, shrunk, and can differ greatly based on the type of Spark cluster being used. The size of the partition does vary, but generally try to keep your partition sizes equal. We'll discuss more about optimizing partitioning and cluster details later on. For now, let's assume that each partition is handled independently. This is part of what provides the performance levels and horizontal scaling ability in Spark. If a Spark node doesn't need to compete for resources nor consult with other Spark nodes for answers, it can reliably schedule the processing for the best performance. In Spark, any transformation operation is lazy. It's more like a recipe than a command. It defines what should be done with a data frame rather than actually doing it. Most operations at Spark are actually transformations, including withColumn, select, filter, and so forth. The set of transformations you define are only executed when you run a Spark action. This includes count, write, etc., anything that requires the transformations to be run to properly obtain an answer. Spark can reorder transformations for the best performance. Usually this isn't noticeable, but can occasionally cause unexpected behavior, such as IDs not being added until after other transformations have completed. This doesn't actually cause a problem, but the data can look unusual if you don't know what to expect. Relational databases tend to have a field used to identify the row, whether it is for an actual relationship reference or just for data identification. These IDs are typically an integer that increases in value, is sequential, and most importantly, unique. The problem with these IDs is they're not very parallel in nature. Given that the values are given out sequentially, if there are multiple workers, they must all refer to a common source for the next entry. This is okay in a single server environment, but in a distributed platform such as Spark, it creates some undue bottlenecks. Let's take a look at how to generate IDs in Spark. Spark has a built-in function called monotonically increasing ID, designed to provide an integer ID that increases in value and is unique. These IDs are not necessarily sequential. There can be gaps, often quite large, between values. Unlike a normal relational ID, Spark's is completely parallel. Each partition is allocated up to 8 billion IDs that can be assigned. Notice that the ID fields in the sample table are integers, increasing in value, but are not sequential. It's a little out of scope, but the IDs are a 64-bit number effectively split into groups based on the Spark partition. Each group contains 8.4 billion IDs, and there are 2.1 billion possible groups, none of which overlap. There's a lot of nuance to how partitions and the monotonically increasing IDs work. Remembering that Spark is lazy, it often helps in troubleshooting what can happen. Operations are often out of order, especially if joins are involved. It's best to test your transformations. We've discussed a lot of detail in this lesson. Let's now take a look at a few exercises that will help solidify how everything works. Now that we've discussed some data cleaning tasks using Spark, let's look at how to improve the performance of running those tasks using caching. Caching in Spark refers to storing the results of a data frame in memory or on disk of the processing nodes in a cluster. Caching improves the speed for subsequent transformations or actions, as the data likely no longer needs to be retrieved from the original data source. Using caching reduces the resource utilization of the cluster. There's less need to access the storage, networking, and CPU of the Spark nodes as the data is likely already present. There are a few disadvantages of caching you should be aware of. Very large datasets may not fit in the memory reserved for cached data frames. Depending on the later transformations requested, the cache may not do anything to help performance. If a dataset does not stay cached in memory, it may be persisted to disk. Depending on the disk configuration of a Spark cluster, this may not be a large performance improvement. If you're reading from a local network resource and have slow local disk I/O, it may be better to avoid caching the objects. Finally, the lifetime of a cached object is not guaranteed. Spark handles regenerating data frames for you automatically, but this can cause delays in processing. Caching is incredibly useful, but only if you plan to use the data frame again. If you only need it for a single task, it's not worth caching. The best way to gauge performance with caching is to test various configurations. Try caching your data frames at various points in the processing cycle and check if it improves your processing time. Try to cache in memory or fast NVMe or SSD storage. While still slower than main memory, modern SSD-based storage is drastically faster than spinning disk. Local spinning hard drives can still be useful if you are processing large data frames that require a lot of steps to generate or must be accessed over the internet. Testing this is crucial. If normal caching doesn't seem to work, try creating intermediate Parquet representations like we did in Chapter 1. These can provide a checkpoint in case a job fails mid-task and can still be used with caching to further improve performance. Finally, you can manually stop caching a data frame when you're finished with it. This frees up cache resources for other data frames. Implementing caching in Spark is simple. The primary way is to call the function cache on a data frame object prior to a given action. It requires no arguments. One example is creating a data frame from some original CSV data. Prior to running a count on the data, we call cache to tell Spark to store it in cache. Another option is to call cache separately. Here we create an ID in one transformation, then we call cache on the data frame. When we call the show action, the voter DF data frame will be cached. If you're following closely, this means that cache is a Spark transformation. Nothing is actually cached until an action is called. A couple other options are available with caching in Spark. To check if a data frame is cached, use the isCached Boolean property, which returns true, as in this case, or false. To uncache a data frame, we call unPersist with no arguments. This removes the object from the cache. We've discussed caching in depth. Let's practice how to use it. We've discussed the benefits of caching when working with Spark data frames. Let's look at how to improve the speed when getting data into a data frame. Spark clusters consist of two types of processes, one driver process and as many worker processes as required. The driver handles task assignments and consolidation of the data results from the workers. The workers typically handle the actual transformation action steps of a Spark job. Once assigned tasks, they operate fairly independently and report results back to the driver. It is possible to have a single node Spark cluster. This is what we're using for this course, but you'll rarely see this in a production environment. There are different ways to run Spark clusters. The method used depends on your specific environment. When importing data to Spark data frames, it's important to understand how the cluster implements the job. The process varies depending on the type of task, but it's safe to assume that the more import objects available, the better the cluster can divvy up the job. This may not matter on a single node cluster, but with larger clusters, each worker can take part in the import process. In clearer terms, one large file will perform considerably worse than many smaller ones. Depending on the configuration of your cluster, you may not be able to process larger files, but could easily handle the same amount of data split between smaller files. Note, you can define a single import statement even if there are multiple files. You can use any form of standard wildcard symbol when defining the import file name. While less important, if objects are about the same size, the cluster will perform better than having a mix of very large and very small objects. If you remember from Chapter 1, we discussed the importance of Spark schemas. Well-defined schemas in Spark drastically improve import performance. Without a schema defined, import tasks require reading the data multiple times to infer structure. This is very slow when you have a lot of data. Spark may not define the objects in the data the same as you would. Spark schemas also provide validation on import. This can save steps with data cleaning jobs and improve the overall processing time. There are various effective ways to split an object, files mostly, into more smaller objects. The first is to use built-in OS utilities such as split, cut, or awk. An example using split uses the -l argument with the number of lines to have per file, 10,000 in this case. The -d argument tells split to use numeric suffixes. The last two arguments are the name of the file to be split and the prefix to be used. Assuming large file has 10 million records, we would have files named chunk-0000 through chunk9999. Another method is to use Python or any other language to split the objects up as we see fit. Sometimes you may not have the tools available to split a large file. If you're going to be working with the DataFrame often, a simple method is to read in the single file, then write it back out as Parquet. We've done this in previous examples, and it works well for later analysis, even if the initial import is slow. It's important to note that if you're hitting limitations due to cluster sizing, try to do as little processing as possible before writing to Parquet. Let's practice some of the import tricks we've discussed now. We've just finished working with improving import performance in Spark. Let's take a look at cluster configurations. Spark has many available configuration settings controlling all aspects of the installation. These configurations can be modified to best match the specific needs for the cluster. The configurations are available in the configuration files, via the Spark web interface, and via the runtime code. Our test cluster is only accessible via command shell, so we'll use the last option. To read a configuration setting, call spark.conf.get with the name of the setting as the argument. To write a configuration setting, call spark.conf.set with the name of the setting and the actual value as the function arguments. Spark deployments can vary depending on the exact needs of the users. One component of a deployment is the cluster management mechanism. Spark clusters can be single-node clusters, deploying all components on a single system, physical, VM, or container. Standalone clusters, with dedicated machines as the driver and workers. Or managed clusters, meaning that the cluster components are handled by a third-party cluster manager such as Yarn, Mesos, or Kubernetes. In this course, we're using a single-node cluster. Your production environment can vary wildly, but we'll discuss standalone clusters as the concepts flow across all management types. If you recall, there is one driver per Spark cluster. The driver is responsible for several things, including the following: handling task assignment to the various nodes or processes in the cluster. The driver monitors the state of all processes and tasks and handles any task retries. The driver is also responsible for consolidating results from the other processes in the cluster. The driver handles any access to shared data and verifies each worker process has the necessary resources, code, data, etc. Given the importance of the driver, it is often worth increasing the specifications of the node compared to the other systems. Doubling the memory compared to the other nodes is recommended. This is useful for task monitoring and data consolidation tasks. As with all Spark systems, fast local storage is useful for running Spark in an ideal setup. The Spark worker handles running tasks assigned by the driver and communicates those results back to the driver. Ideally, the worker has a copy of all code, data, and access to the necessary resources required to complete a given task. If any of these are unavailable, the worker must pause to obtain the resources. When sizing a cluster, there are a few recommendations. Depending on the type of task, more worker nodes is often better than larger nodes. This can be especially obvious during import and export operations, as there are more machines available to do the work. As with everything in Spark, test various configurations to find the correct balance for your workload. Assuming a cloud environment, 16 worker nodes may complete a job in an hour and cost $50 in resources. An 8-worker configuration might take 1.25 hours, but cost only half as much. Finally, workers can make use of fast local storage, SSD or NVMe, for caching intermediate files, etc. Now that we've discussed cluster sizing and configuration, let's practice working with these options. We've discussed Spark clusters and improving import performance. Let's look at how to improve the performance of Spark tasks in general. To understand performance implications of Spark, you must be able to see what it's doing under the hood. The easiest way to do this is to use the explain function on a DataFrame. This example is taken from an earlier exercise, simply requesting a single column and running distinct against it. The result is the estimated plan that will be run to generate the results from the DataFrame. Don't worry about the specifics of the plan yet, just remember how to view it if needed. Spark distributes data amongst the various nodes in the cluster. A side effect of this is what is known as shuffling. Shuffling is the moving of data fragments to various workers as required to complete certain tasks. Shuffling is useful and hides overall complexity from the user. The user doesn't have to know which nodes have what data. That being said, it can be slow to complete the necessary transfers, especially if a few nodes require all the data. Shuffling lowers the overall throughput of the cluster as the workers must spend time waiting for the data to transfer. This limits the amount of available workers for the remaining tasks in the system. Shuffling is often a necessary component, but it's helpful to try to minimize it as much as possible. It can be tricky to remove shuffling operations entirely, but there are a few things that can limit it. The DataFrame repartition function takes a single argument, the number of partitions requested. We've used this in an earlier chapter to illustrate the effect of partitions with the monotonically increasing ID function. Repartitioning requires a full shuffle of data between nodes and processes, and it's quite costly. If you need to reduce the number of partitions, use the coalesce function instead. It takes a number of partitions smaller than the current one and consolidates the data without requiring a full data shuffle. Note, calling coalesce with a larger number of partitions does not actually do anything. The join function is a great use of Spark and provides a lot of power. Calling join indiscriminately can often cause shuffle operations, leading to increased cluster load and slower processing times. To avoid some of the shuffle operations when joining Spark data frames, you can use the broadcast function. I'll talk about this more in a moment. Finally, an important note about data cleaning operations is remembering to optimize for what matters. The speed of your initial code may be perfectly acceptable and time may be better spent elsewhere. Broadcasting in Spark is a method to provide a copy of an object to each worker. When each worker has its own copy of the data, there is less need for communication between nodes. This limits data shuffles, and it's more likely a node will fulfill tasks independently. Using broadcasting can drastically speed up join operations, especially if one of the data frames being joined is much smaller than the other. To implement broadcasting, you must import the broadcast function from PySpark.sql.functions. Once imported, simply call the broadcast function with the name of the data frame you wish to broadcast. Note, broadcasting can slow operations when using very small data frames, or if you broadcast the larger data frame in a join. Spark will often optimize this for you, but as usual, run tests in your environment for best performance. We've looked how to limit shuffling and implement broadcasting for data frames. Let's practice utilizing these tools now. We've spent most of this course working with individual transformations and actions to clean data in Spark. But data is rarely so simple that a couple transformations or actions can prepare it for real analysis. Let's look now at data pipelines. Data pipelines are simply the set of steps needed to move from an input data source or sources and convert it to the desired output. A data pipeline can consist of any number of steps or components and can span many systems. For our purposes, we'll be setting up a data pipeline within Spark, but realize that a full production data pipeline will likely communicate with many systems. Much like Spark in general, a data pipeline typically consists of inputs, transformations, and the outputs of those steps. In addition, there is often validation and analysis steps before delivery of the data to the next user. An input can be any of the data types we've looked at so far, including CSV, JSON, text, etc. It could be from the local file system or from web services, APIs, databases, and so on. The basic idea is to read the data into a data frame as we've done previously. Once we have the data in a data frame, we need to transform it in some fashion. You've done the individual steps several times throughout this course, adding columns, filtering rows, performing calculations as needed. In our previous examples, we've only done one or two of these steps at a time, but a pipeline can consist of as many of these steps as needed so we can format the data into our desired output. After we've defined our transformations, we need to output the data into a usable form. You've already written files out to CSV or Parquet format, but it could include multiple copies with various formats, or instead write the output to a database, a web service, etc. The last two steps vary greatly depending on your needs. We'll discuss validation in a later lesson, but the idea is to run some form of testing on the data to verify it is as expected. Analysis is often the final step before handing the data off to the next user. This can include things such as row counts, specific calculations, or pretty much anything that makes it easier for the user to consume the dataset. It's important to note that in Spark, a data pipeline is not a formally defined object, but rather a concept. This is different than if you've used the pipeline object in Spark.ml. If you haven't, don't worry, it's not needed for this course. For our purposes, a Spark pipeline is all the normal code required to complete a task. In this example, we're doing the various tasks required to define a schema, read a data file, add an ID, then write out two separate data types. The task could be much more complex, but the concept is usually the same. When you look at the components, a data pipeline in Spark is fairly simple but can be very powerful. Let's start working on a more elaborate data pipeline now. We've worked with many aspects of Spark when it comes to data cleaning operations. Let's look at how to use some of the methods we've learned to parse unconventional data. When reading data into Spark, you're rarely given a fully uniform file. Often there is content that needs to be removed or reformatted. Some common issues include incorrect data consisting of empty rows, commented lines, headers, or even rows that don't match the intended schema. Real-world data often includes nested structures, including columns that use different delimiters. This could include the primary column separated via a comma, but including some components separated via a semicolon. Real data often won't fit into a tabular format, sometimes consisting of a differing number of columns per row. There are various ways to parse data in all of these situations. The way you choose will depend on your specific needs. We are focusing on CSV data for this course, but the general scenarios described apply to other formats as well. For this chapter, we're going to use the Stanford ImageNet annotations, which focus on finding and identifying dogs in various ImageNet images. The annotations provide a list of all identified dogs in an image, including when multiple dogs are in the same image. Other metadata is included, including the folder within the ImageNet dataset, the image dimensions, and the bounding box or boxes of the dogs in the image. In the example rows, we have the folder names, the ImageNet image reference, width, and height. Then there is the image data for the type of dog or dogs in each image. Each breed column consists of the breed name and the bounding box in the image. The first row contains one Newfoundland, but notice that the second row actually has two bull mastiffs identified and an additional column defined. Spark's CSV parser can handle many common data issues via optional parameters. Blank lines are automatically removed unless specifically instructed otherwise when using the CSV parsing. Comments can be removed with an optional named argument, comment, and specifying the character that any comment line would be defined by. Note that this handles lines that begin with a specific comment. Parsing more complex comment usage requires more involved procedures. Header rows can be parsed via an optional parameter named header and set to true or false. If no schema is defined, column names will be initially set as defined by the header. If a schema is defined, the row is not used as data, but the header names are otherwise ignored. When importing CSV data into Spark, it will automatically create DataFrame columns if it can. It will split a row of text from the CSV on a defined separator argument named sep. If sep is not defined, it will default to using a comma. The CSV parser will still succeed in parsing data if the separator character is not within the string. It will store the entire row in a column named _C0 by default. Using this trick allows parsing of nested or complex data. We'll look at this more later on. Let's practice working with this data and extending our data pipeline further. Welcome back. Validation is one step of a data pipeline we haven't covered yet, but it is very important in verifying the quality of the data we're delivering. Let's look at how to implement validation steps in a data cleaning pipeline. In this context, validation is verifying that a dataset complies with an expected format. This can include verifying the number of rows and columns is as expected. For example, is the row count within 2% of the previous month's row count? Another common test is, do the data types match? If not specifically validated with a schema, does the content meet the requirements? Only 9 characters or less, etc. Finally, you can validate it against more complex rules. This includes verifying that the values of a set of sensor readings are within physically possible quantities. One technique used to validate data in Spark is using joins to verify the content of a data frame matches a known set. Validating via a join will compare data against a set of known values. This could be a list of known IDs, companies, addresses, etc. Joins make it easy to determine if data is present in a set. This could be only rows that are in one data frame, present in both, or present in neither. Joins are also comparatively fast, especially versus validating individual rows against a long list of entries. The simplest example of this is using an inner join of 2 data frames to validate the data. A new data frame, parsed.df, is loaded from a given Parquet file. The second data frame is loaded containing a list of known company names. A new data frame is created by joining parsed.df and company.df on the company name. As this is an inner join, only rows from parsed.df with company names that are present in company.df would be included in the new data frame, verified.df. This has the effect of automatically filtering out rows that don't meet any of the specified criteria. This is done without any kind of Spark filter or comparison code. Complex rule validation is the idea of using Spark components to validate logic. This may be as simple as using the various Spark calculations to verify the number of columns in an irregular data set. You've done something like this already in the previous lessons. The validation can also be applied against an external source, web service, local files, API calls. These rules are often implemented as a UDF to encapsulate the logic to one place and easily run against the content of a data frame. Let's try validating our data against our specific requirements for this dataset. Enjoy the exercises, and we'll get to the last lesson of this course. We've worked with a lot of Spark components while exploring data cleaning. Let's finish up this data cleaning pipeline with some final analysis calculations. Analysis calculations are the process of using the columns of data in a data frame to compute some useful value using Spark's functionality. We've used UDFs in previous chapters, and this version illustrates calculating an average sale price from a given list of sales. A Python function takes a sales list argument. For every sale in the sales list, the function adds the sale entry from value 2 and 3 in the sale tuple. Once complete, it calculates the actual average per row and returns it. The remaining code is what we've done previously when defining a UDF and using it within a data frame. Spark UDFs are very powerful and flexible and are sometimes the only way to handle certain types of data. Unfortunately, UDFs do come at a performance penalty compared to the built-in Spark functions, especially for certain operations. The solution is to perform calculations inline if possible. Spark columns can be defined using inline math operations, which can then be optimized for the best performance. In this case, we read in a data file and then have 2 examples of adding calculated columns. The first is a simple average computed by using 2 columns in the data frame. The second option computes a square footage by multiplying the value in the 2 columns together to create a third. The final line shows the option of mixing a UDF with an inline calculation. There's often a better way to do this, but it does illustrate Spark does not care about the source of the info, as long as it conforms to the expected input format. Let's finish up this course by performing some analysis on our data frame and add meaningful information to the data. Congratulations! You've successfully completed this course by performing data cleaning operations on several datasets using Python and Apache Spark. While we've touched on many topics, there is a great deal to learn about Spark and how best to perform data cleaning. To continue your journey with using Apache Spark, there are a few areas I'd advise you to focus on. Reading the Spark documentation is a great way to add to your knowledge and fill in gaps of understanding. Spark is constantly changing and often adds new features without a lot of fanfare. Seasoned Spark developers often find new techniques that remove a lot of complexity from existing code. Spark works on many platforms regardless of size, but it really shines when using on multi-node clusters with a lot of RAM. You'll be surprised how quickly Spark processes data when given the resources to function as designed. I've personally processed multi-billion row datasets in a few hours on a relatively modest cluster. Finally, I'd suggest working with as many different datasets as you can find. Different types of data require different techniques in Spark, and each has challenges when trying to process data in an efficient way. The datasets available within the various courses here on DataCamp are a great place to start. Thanks, and good luck on your journey using Apache Spark.
Hi, I'm John Hogue, and welcome to Feature Engineering with PySpark. Easily one of the most important aspects of applied machine learning is feature engineering. It is the process of using domain knowledge to create new features to help our models perform better. In this course, we will look at a real dataset and work our way to building a regression model in PySpark. Before we dive in, it's important to note that while the techniques you'll learn in this course are invaluable, the data science cannot be applied as a cookie cutter. You'll need to research your data and become your own expert. There's much to be said of the dangers of not understanding your data, especially where our outputs are increasingly being used to make decisions and inform policies. Before you dive into modeling, spend time to define what your goals are and how the output might be used. Take time to research your data and its limitations. Oftentimes, you may be tasked with explaining what is and isn't possible. Lastly, remember that data science is about being curious, asking questions, and applying new ways to solve problems. Every project and dataset is different. Data science is an iterative process that requires comfort with uncertainty, as at any point you may have to go backward or even start over. A good project may inspire further questions that set the goals for your next project. As we progress through this process, this course will have extra emphasis on a lot of the art sides of data science, exploring data, cleaning it, and engineering it for use in a model. Before we get started, as a cutting-edge technology, Spark changes fast and frequently. Make sure you're looking at the right version. You can always go to the latest URL by using the /latest or put the version number, major, minor, and patch to get a specific version. Programmatically, you can check your version of Spark with these commands. That way you can ensure you are looking at the right documentation and not using deprecated methods. For this course, we will be using a Parquet file. Like most data in Hadoop, the platform that Spark runs on, it is write once, read many times format. Parquet is columnar, meaning that it is organized by columns, an important feature for huge datasets as it is blazingly fast to read in only the data you need. CSVs, on the other hand, have to read and parse the whole dataset to read a single field. Another difference is Parquet fields are defined and typed, saving users from defining data types, like dates, booleans, or strings. For this reason, Parquet is relatively slow to write. Since it's not delimited by characters, it's less likely to be read in wrong if those characters exist in the data. These are just a few of the advantages that are causing the industry to adopt Parquet quickly. We have many format readers to choose from for converting various file types to a PySpark data frame. Here we will use Spark read Parquet and put the results into a variable df representing a data frame. In this video, we covered off on some important considerations when starting any data science project. We also learned about Parquet and how to load it to a Spark data frame. In the exercises, you'll verify the versioning of PySpark and Python, and finally, you'll load the data yourself. What's the point of doing an analysis if you aren't solving the right problem? In this video, we'll define our problem in the context of our data. We are going to build a model to predict how much a house sells for. This question can be interpreted multiple ways, which is why it's important to take the time to formally define it. Let's assume we are real estate tycoons looking for the next best investment opportunity. For a given house on the market with a listed price and a series of attributes describing the home, what is it likely to actually sell for, aka the sales close price? The dataset we have is a sample of homes that sold over the course of 2017. Using this sample, we are to provide a quick proof of concept of whether it's worth investing in more data for the 5.5 million homes that sold in the US in 2017. To do this, we need to understand some of the limitations of the data we have. First, we only have a small geographical area, so to apply our model to new areas poses serious risk. We know that we only have residential data, so we shouldn't expect to predict how much a business location is worth. Lastly, we only have 1 year's worth of data, which will make it hard to draw strong conclusions about the seasonality in the dataset. The original dataset has hundreds of attributes available, but in order to start simple, we've already worked with our client to identify around 50 attributes they think are likely to influence the price of a home. These attributes generally fall into these groups. For dates, we have date listed and the year the home was built. For locational data, we have the city that the home is in, its school district, and its actual postal address. We also have many different metrics to gauge the size of a home, like number of bed and bathrooms, as well as the area of living space. For prices, we have the listing price, and we wouldn't be able to predict anything without the sales price. We also have a lot of data available on the amenities that a house has, like a pool or a garage, as well as the construction materials that were used to build the house. Big data means a lot can go wrong when loading data. Make sure you have the right number of records and columns. We can use df count to get the row count, df columns to get the list of columns, and we can take the length of df columns to get the number of columns. When we used Parquet, it set the data types for all of our fields, which is a huge advantage over CSV. It's still worth checking, especially if you weren't the one defining it. Here we can use dtypes on our data frame to create a list of tuples containing a column name and its corresponding data type. In this video, we learned about the dataset we will be using and the problem we will be trying to solve. Additionally, we learned how to check to see if our data loaded properly by checking rows, columns, and data types. Now it's your turn to apply what you've learned in the exercises to verify our data got loaded correctly. Data comes in all shapes and sizes. In the field, you will be tasked with using less than perfect data. This means you'll need to understand its strengths, weaknesses, and limitations to leverage it effectively. To get started with understanding your data, take a peek at each column to see what they contain. The describe function provides some bare-bone basics of count, mean, standard deviation, min, and max. You can run it on the whole data frame, a single column, or a list of columns. Remember to add show at the end if you wish to immediately display the results. To further help us understand our data, PySpark has many built-in descriptive functions available. Mean function is considered an aggregate function, and as such, it needs to be passed to the agg method, along with the column to run it on as a dictionary. To force it to return results immediately, use collect. Covariance is a function that lets us see how two variables vary together. This function is applied to a data frame and takes two numeric columns and returns a value. An excellent way to explore your data is through statistical plotting. Seaborn is a Python data visualization library designed specifically for this. We will look at a few plotting examples, but there are many, many more for you to follow up on. We can plot data using non-Spark libraries like Seaborn, but they require converting your PySpark data frame to a Pandas data frame. Be aware that converting large datasets can cause Pandas to crash. This is because PySpark is made for massive datasets, whereas Pandas is not. The sample function can help us get a smaller dataset to plot. Here, we will keep sampling with replacement off, take 50% of the data, and set a random seed for reproducibility. Using count shows us the number of records has changed. We will leverage Seaborn's dis plot, which will show us the distribution of our dependent variable, sales close price. Please note there are many optional parameters which aren't covered here. Here we will import Seaborn, then filter the Spark data frame down to the sales close price column, and then sample it. Then we convert it to a Pandas data frame so we can use it with Seaborn. Lastly, call this plot function with pandas_df to plot. After plotting, we can see that most of the data is pushed to the left, something that may need to be remedied depending on the model type we choose. We will cover one option, log scaling, in adjusting data later in this course. Another great plot to use is LM-plot. LM is short for linear model and allows us to quickly see if there is a linear relationship between two variables. For this example, we will look at how sales close price changes depending on square footage above ground. To do this, we will import Seaborn, filter our dataset to the two columns, sample it, and convert it to a Pandas data frame. Lastly, use the SNS LM plot function with our X and Y columns and the data frame. Here we can see that there's what looks to be a strong relationship between the size of a home and the price it sells for. Therefore, we might make the assumption that square footage above ground is a good variable to consider in the predicting of house prices. In this video, we explored our data with numerical summaries and visualizations. Now it's your turn to try them out. More data is better, right? Not if it's bad data. The saying garbage in, garbage out is doubly true in data science. Data has a lot of places where it can get messed up. Data may be recorded incorrectly or contain extreme events. Inconsistent formatting, such as mixing numeric and text data, can make a field hard to use. Duplications can add redundant observations. Missing data can cause your analysis to have blind spots. Lastly, sometimes the data is just not relevant to the analysis. Failure to account for bad data can set your analysis up to fail. Please be careful. Inspecting our data, we see there are some columns that are not worth including in our analysis. No is just the record number. Unit number is the apartment or house number, and class is completely constant. Dropping the columns requires entering a single column name or passing a list of columns to drop. Here we pass a list called calls to drop to the function and then drop them. Please note the star, which tells the function to unpack the list and feed them to the function one by one. A common task in cleaning your data will be filtering it. Here we will filter records that contain specific text values. Where applies the filter to the data frame records. Like creates a true-false condition for the records. The tilde provides a way to take the opposite, or a not. The PySpark code reads, filter the data frame where the potential short sale field is not like the string not disclosed. For initial pass at the model, it might be helpful to remove large outliers. One definition of an outlier for near normally distributed data is something that occurs more than 3 standard deviations from the mean. Only 0.3% of the data should be filtered. Remember that outliers occur on both sides, so filter on both sides of the mean. Here we will filter extreme values from the list price column. To start, we will use the aggregate functions standard deviation and mean. Then use collect to force the calculation to run, and use the 00 index to access the values. Lastly, we created a multi-conditional filter, which is just 2 Boolean statements ANDed together. It reads, filter where the list price is less than the high bound and more than the low bound. Dealing with missing data is something we will cover later, as dropping data is usually a naive approach. Nevertheless, it's important to sometimes take shortcuts to quickly prove out the basis for further work. Drop NA does what you'd expect it to do. In its basic form, it will remove a record where there's any null value in any column. You can get more specific as we'll see on the next slide. In the first example, we'll drop any record that contains a null value. The second example will look at only 2 columns, and if both are null, Then we will remove the record. Lastly, we can apply a threshold across all the columns and say, if more than 2 columns contain null values, remove the entire record. Duplicates occur when 2 or more records contain the exact same information. Often this can happen after you drop columns or join datasets. Drop duplicates will drop the first duplicate it finds. Since Spark is distributed, which one it finds may or may not be in the order of how your file was loaded. If you want to be more picky about where you're looking for duplicates, you can specify a list of column names to look for them there specifically. In this video, we learned why we might have bad data and several ways to remove it so it doesn't adversely impact our analysis. Let's see you take a shot at removing some data in the exercises. Jeff Hooper of Bell Labs once said, "Data does not give up its secrets easily. It must be tortured to confess." This lesson will arm you with the tools to get your data to behave. Real data is ugly and rarely comes ready to be analyzed. Many algorithms and statistical methods have assumptions that a variable conforms to. If our data doesn't fit these criteria, all hope isn't lost yet. We can try mathematical operations to adjust the data to become the beautiful butterflies our methods require. One common transformation is scaling. For many algorithms like KNN or regression, you need to ensure all your variables are on the same scale. One variable can't be from -1,000 to 5,000, and another between 0.01 and 0.02. These algorithms will try to reduce the errors in the first variable much more than the second. We can avoid this by scaling each feature between 0 and 1. This is called min-max scaling and doesn't change the shape of the distribution, only its range. To min-max scale, take the variable to be scaled, subtract the minimum value, and divide by the difference between the max and the min. To scale our data, we need to first find the min and max values of the column we want to scale. Here we are using aggregate functions min and max. We will use collect to force the calculation to run and use the 00 index to access the values. To create a new column, we will use with column that creates a new column based off of some sort of transformation to an existing one, in this case, days on market. Lastly, we can see that our values are now between 0 and 1. Another common restriction is that data must closely follow the standard normal distribution. Standardization, or z-transforming, is the process of shifting and scaling your data to better resemble a standard normal distribution, which has a mean of 0 and a standard deviation of 1. In the image, you can see how the original data in blue shifts to green where it has a mean of 0, and then the final step scales to the standard normal distribution in red. To z-transform our data, we calculate the aggregate functions mean and standard deviation of the column we are transforming. Since we want to use the values in the next step, we will use collect to immediately calculate them and use the index values of 00 to access the return values. We can then apply the standardization formula to our column and put the results into a new column, z-transdays, by using with column. Lastly, we can verify the transformed data does have approximate mean of 0 and standard deviation of 1. Our data for sales close price is pushed to the left. This is called positive skew. One potential way to treat skewed data is to apply a log transformation on the data. This has the impact of making our data look more like a normal distribution. To apply a log transformation, you will need to import the log function from PySpark SQL functions. We can then create a new column, log sales close price, based on the application of the log function on sales close price. In this video, you learn why and how to apply transformations to your data. Now it's time for you to adjust some data. Missing data is frustrating. In this lesson, we will touch on a few ways to handle it. How does data go missing in the digital age? Sensors can fail, surveys can miss people, or new ways to measure things can cause gaps in data sets. Data storage rules can force data that doesn't fit the specified type to be null. For example, dates in different formats, abbreviations, or a currency with a comma instead of a period. Joining datasets can enrich your model, but can induce missing values if they are not captured at the same granularity. If you combine daily data with monthly data, it will create gaps for all the days where the monthly data was not captured. Lastly, data can be missing intentionally. Attributes used in combination might be enough to compromise privacy. This can be seen in government datasets like the census, where they will omit data if there is a concern. Understanding why your data is missing is important. Missing completely at random occurs when the data is missing with no pattern. Your data is likely still representative of the whole population. Missing at random occurs when the probability of missing data on the y variable is unrelated to the value of y. For example, suppose males are less likely to answer a depression survey. This has no relationship with their level of depression after accounting for maleness. Missing not at random is when the value that is missing is related to the reason why it's missing. Supposing that people with severe health problems do not answer a question asking them to rank their health would indicate missing not at random. Earlier we showed how to use the function dropNA, but we didn't talk about when to use it. If your data only has a few missing values and they are missing completely at random, it may be fine to remove the rows. But how can we check to see how many missing values we have in our dataset? We can use the isNull function. It returns true if the condition is true. Here we use it to filter our data to records where they are null and then count them. We can also use Seaborn to help us visualize missing values by leveraging the heatmap function. Using the same steps as before, we sample our data, convert it, and then use Seaborn to plot the heat map. Note we use the Pandas DataFrame isNull to convert the DataFrame to a true-false for its null values. Here we can see the missing values as white spaces on the chart. Another way to handle missing values is to replace them. The replacement value might be based on business rules, such as missing sales means there were no sales, and replace them with 0. If the missing data is missing completely at random, it may make sense to impute them using the mean or the median. Another option could be to use interpolation, creating another model to predict their values. Replacing values shouldn't be done without some serious considerations. Make sure you research the appropriateness. To replace missing values, we will use PySpark's fillNA, which takes the value to use for replacement as well as a list of column names. Here, we will replace values with 0. We can also replace values with the mean by calculating it using an aggregate function as we have done before. Then the mean only needs to be placed in the fillNA function. In this video, you learned about the types of missing data, how to assess missing values, and some methods to treat them. Take some time to do the exercises and try out what you've learned. The world of big data means having access to much more information to include in our analysis. In this video, we will cover how to connect additional data to our dataset. External data is a wonderful way to boost model performance, but there are pros and cons to choosing to include it. Adding external data may add excellent predictors for a model, but adding too many features may impact the performance of the model. There is serious risk of spurious correlations between variables in the world of big data. External data can be a great way to replace missing or aggregated values with a better feature. Adding data comes at the risk of inducing data leakage. If we wish to include local crime information, we will have to ensure that buyers would also have access to that information at the time of purchasing a home. To include data available later is leaking information from the future. Another consideration is how cheap and easy it is to obtain. Today we have many more datasets easily available to us, but it may come at the cost of needing to become the subject matter experts to know the meaning and credibility of our sources. To understand the different kinds of joins, we'll need to orient ourselves. We'll call the original dataset we started with the left, and the one we wish to incorporate our right. There are many ways to join data together. Most commonly, the inner or left joins depending on your goals. For us, we want to make sure we always keep the full left dataset and add data where available from the right. This means we will be using a left join. Joins can be done one of two ways in PySpark. First is the DataFrame join method. The DataFrame that calls the join is the left DataFrame. Other is the right data frame, in this case, the new data set. On is the pair of column conditions we will match on. How is the type of join to perform. Suppose we want to see the impact of homes sold on bank holidays. We can join the data frames together by creating a join condition where df off market date equals hdf dt. We can then put this condition into our join function and use left to make sure we keep all the original records in df. Lastly, count holiday sales by using the tilde to take the not of isNull. Not surprisingly, no houses are sold on bank holidays. Perhaps later we can check to see if a holiday week impacts sales. The second way we can join data frames together is to use Spark SQL, which allows us to apply SQL statements directly to data frames. This may be your preferred method if you are familiar with SQL or attempting to do complicated joins or filters. To do this, we need to register the data frame as a temp table and give it a name. Once that's done, we can use Spark SQL to execute a query and return it back in the form of a data frame. In this one, we are using select star to get all of the columns available, using from df to create our starting table, left join hdf as the table we'd like to join with, and using on df off market date equals hdf dt to create the join condition. In this video, we learned that combining datasets can be powerful but requires some caution. We also learned how to join data in two different ways. In the exercises, we will build on these and learn some things to watch out for. In this video, we will learn a lot about the nuts and bolts of feature engineering. Just because it's called machine learning doesn't mean it can figure out everything on its own. So we will use some tricks to help it out by creating new features that will better capture patterns in the data. This video will cover feature generation and show you how using the new features can improve a model. Why generate new features if the information is already available in the dataset? Combining features together can capture subtle dependent effects between them that impact the outcome variable. These can be represented by multiplying, summing, differencing, or dividing two or more variables. To see the impact of generating these features, let's suppose you have two attributes, length and width, and then the price of a single-story home. If these are your only two features, how can you best create a model to predict price? They certainly don't look to be very strong features as is. Taking the previous example a step further, we can think about how a person might buy a home. If we use some intuition that people often consider the area of a home, we can create a new feature, total square footage, by multiplying the width and length. The results are much better with an R² of 0.81. Applying your reasoning and understanding to the problem can help you build powerful predictors. Our dataset doesn't include width and length because no one would ever actually look for a house that way. However, we don't have a total square footage calculated, but we can create it using width column and by adding square footage below ground and square footage above ground together. We can build another feature, price per square footage, using our previous feature, square footage. This is now the combination of three independent variables. There isn't a limit to how deep you can go, but the interpretability of what it means starts to become difficult after 3. We can create days on market as a difference between list date and off market date. We will cover how to get list date and off market date into the date time format in the next section, but for now, know that new features can be generated many ways. There's a major push in the data science community to automate some of the generation of features. If this is of interest to you, I'd recommend you check out the Python libraries, feature tools, and TS-Fresh. I will caution you that simply multiplying each feature pairwise will square your number of features. This can cause an explosion of features that can be unwieldy to model or could potentially overfit your model by pure coincidence. Many of the features may convey similar information and won't be needed. Lastly, there is no limit to how many features you can combine, but the interpretability certainly takes a steep dive after 3. Beyond this is the realm of deep feature generation, a topic for another course. In this video, you learned that you can generate new, powerful features to represent complex relationships between them. Lastly, you saw that feature combinations are everywhere and that many are already in our dataset. It's your turn to take what you've learned and build and evaluate new features generated from what's available. In this video, we will talk about using time in our models, since it isn't as easy as throwing it into our models as a continuous variable. Things repeat, each day has a noon, each week has a Monday, and each year has a January. We want to help our model by building features that help it associate cyclical events with changes in our outcome variable, such as summer having a higher volume of homes sold than in winter. Building the right time features is important. The high variation in daily number of homes sold makes this pattern hard for us to see and the model to understand. If we change the aggregation to look at grouping by month, we can see the pattern much more clearly. Choosing the right level to build out time-related features is important, as too granular and they are too noisy for our model. Too broad and our model misses trends. To work with dates, we need them to be of the Spark date type. We can do the conversion with toDate function that takes a single column. If you wish to keep the time components, use toTimestamp instead. With our data typed correctly, we can use built-ins to get various time components. One popular way to handle dates is to convert them into ordinal features like year or month using the functions year and month respectively. We can also extract more complicated things like day number in the month with day of month, or the week number in the year with week of year to further build out our features. Many more functions can be found in the PySpark SQL functions docs online. One simple time-based metric is the number of days a property remains unsold from the date it was listed. Days on market is an important feature to buyers. They may perceive that a house that has been on the market for a while has something wrong with it, or that the seller may be more willing to give them a discount. We can create this metric by applying the dateDiff function to off-market date and list date columns. Lagging time features is a common approach to add propagation time for a variable's effect to impact the outcome variable. This is similar to how a drop creates waves that take time to hit the edge of our glass. To capture this, we will shift values forwards or backwards until the timings line up. To create a lagged feature, we will need a few new functions. First, the window function. Window allows you to return a value for each record based on some calculation against a group of records, such as rank or moving average. The second function is lag, a window function that returns a value that is offset by rows before the current row. It takes a DataFrame column as an input. Count is how many periods you wish to lag. Let's see it in action. For this example, we will look at lagging weekly mortgage rates, as it often takes time for people to adjust the price of their homes. To begin, we will need to import our new functions. Then we will create a window which will group things by our ordered date column, making our window weekly. Once that is done, we can create a new column using the lag function, telling it to lag mortgage rate 30 US by 1 period. The over function takes the window W so that the lag knows how to compare to the current record. Now it's your turn to create some of your own time-related features with built-in datetime functions, as well as more complex ones using the window function. Datasets frequently have rich features trapped in messy combination fields, lists, or even free-form text. In this video, we'll go over how to wrangle columns into useful information for machine learning. We can see that within this roof column, there are many useful features. For instance, an old roof is very expensive to replace, and knowing that might impact the price of the house. The age in this dataset is either over 8 years or less. This would be better as a Boolean variable, 0 or 1, something that we can calculate on. To create a Boolean column, we will use the when function to create an if-then. The when function evaluates the Boolean condition and then does something. In this case, our Boolean conditions are find over 8 and find under 8, which use the like function to return true/false depending on if the string is found. You might notice that we use the %sign before and after the string we are looking for. These are wildcards that allow any number of characters before or after the string. Now that we have these conditions created, we can put them into the when function. When find over 8 is true, assign 1. When find under 8 is true, assign 0. If neither is true, the otherwise function allows us to assign none, so they are null. We can see that the roof age has now been created into a new Boolean variable. Let's look at the roof column again. You'll notice that if there is a value in roof, it seems to be a list starting with the type of materials it was made out of. If we know the pattern, we can split this into its own column called roof material. To split a column, we need to introduce a new function from the PySpark SQL functions module, split, which takes a column to split and a character to split on. In our example, we will split on df roof and use the comma as the delimiter between the values. Once we have that created, we can use our familiar with column to create a new column from the first value with split get item 0. Get item 0 takes the 0 index position of the split column and returns the value. Here we can verify our code performed as expected, splitting the roof column and putting the first value into a new column, roof material. What if the order of the listed values in a column is not guaranteed, and we want to extract out all of the values to their own columns? To do this is a two-step process. The first step is called exploding, changing a compound field so that each value has a separate record, with everything else repeated. The second step is to pivot these repeated fields into columns. You'll notice how we have columns for each possible value in the compound field we started with. To do this, in PySpark, we need to import several functions: split, explode, lit, coalesce, and first. Then we need to split our roof column into an array column. Now we can explode our roof list to create a new record for each value. Next, we'll create a constant column to help our pivot. The pivot function will group by our record ID so that only one row is returned for pivoting X roof list. Since pivot is an aggregate function, we will use a constant value column with coalesce to ignore nulls and first to take the first value. In this video, we learned how to salvage some messy fields into machine learnable features. Now it's your turn to wrangle some features on your own. This video will cover the basics of binarizing, bucketing, and encoding with PySpark with Spark ML transformers. These methods are great ways to get the most out of your features. Binarization of data is a helpful way to collapse some of the nuance in your model to just a yes-no. Homeowners often use yes-no filters to narrow their search for homes. For example, they may only consider homes that have a fireplace, but not care about how many fireplaces as long as it's more than one. Binarization takes values below or equal to a threshold and replaces them by 0, values above it by 1. For this example, we will leverage the Spark ML feature transformer, Binarizer. Introduction of PySpark showcased transformers in detail, so we'll spend time just using them. After importing Binarizer, we need to make sure the column we want to apply it on is of type double. We need to create a transformation called bin with the Binarizer class. Setting the threshold to 0 so that anything over 0 will be converted to 1. Then set our input call to fireplaces and our output to fireplace T. To apply the transformation, we apply transform with our DataFrame. We can see the transformation worked as expected below. If you're a homeowner, you might want to know that a house has 1, 2, 3, or more bathrooms. But once you hit a certain point, you don't really care whether the house has 7 or 8 bathrooms. Bucketing, also known as binning, is a way to create ordinal variables. Like the binarizer, we will import bucketizer. Then we need to define our splits for buckets of values. We want 0 to 1 map to 1, greater than 1 to 2 map to 2, greater than 2 to 3 map to 3, and lastly, anything more than 4 map to 4, using the infinity value float INF for the upper bound. Then we can create the transformer buck with our splits, the input column and the output column. We can then apply the transformer to our data frame with transform. As you can see, the transformation created buckets for our values correctly. Some algorithms cannot handle categorical data like the text field city, and it must be converted to a numeric format like the ones to the right to be evaluated correctly. One method to handle this is called one-hot encoding, where you pivot each categorical variable to a true-false column of its own. Keep in mind, for columns with lots of different values, this can create potentially hundreds or thousands of new columns. To apply one hot encoder transformer, we need to do it in 2 steps. First, we need the string indexer transformer. The string indexer takes a string in and maps each word to a number. Then we can use the fit and transform methods to perform the mapping and transform the strings to numbers. Now we can apply the one hot encoder transformer on our index city values and output all the encoded indexes to a single column of type vector, which is more efficient than storing them all as individual columns. Another thing to note is that the last category is not included by default because it is linearly dependent on the other columns and is not needed. In this video, we learned how to group values together as well as how to convert categorical values to numeric. You will apply these transformers in the following examples. Good luck! PySpark has many different machine learning algorithms available to choose from. While this makes our ability to predict, classify, or cluster on enormous datasets easier, the onus is on us to choose the correct one. This flowchart can help us navigate what's available in PySpark's machine learning library for DataFrames, ML. Recall that we are going to predict the price of a home. This price is a quantity, in this case of dollars, and it is continuous. That takes us to the regression archetype, which predicts continuous values. Lastly, we can see that algorithms for solving our problem can be found within the ML regression module. ML regression provides us with many different algorithms we could use. These first methods differ mostly in how they regularize, which is how they prevent themselves from finding overly complex solutions that are likely to overfit the data. While these methods can be powerful if used correctly, they require a lot of upfront work to ensure their assumptions are met. ML regression also contains tree-based methods, which have the ability to easily handle things like missing and categorical variables right out of the box. Decision trees are easy to interpret, but a lot of work needs to go in to prevent overfitting. So now we are down to 2 algorithms, random forest and GBT regression, which differ mostly in how they handle error reduction. We will choose to evaluate both random forests as well as gradient boosted trees, or GBT regression. Both random forest and gradient boosted tree models are examples of ensemble models. They combine many smaller models together to create a more powerful model. In the diagram, you can see that we have many decision trees, each only trained on a sample of the data to prevent overfitting. When it comes time to predict, a new value runs through the decision trees and they merge their answers together to create a prediction. If you've had some exposure to machine learning, you may have seen the crucial step of splitting your data into test and training sets, which needs to be done before applying feature transformations. Commonly, data is split randomly. Ours contains a time component, so splitting randomly would leak information about what happens in the future. To prevent this, you can split your data sequentially and train your model on the first sequences and then test it with the last. The size of your sets depend on how far out you need to forecast. Doing incremental testing is called step-forward optimization. Here, we will create just one of the sequential test-train splits. With some added logic, you could build out walk-forward optimization seen previously. First, we'll dynamically set our time variables. It's important as when your dataset refreshes, you don't have to remember to change them. To start, we'll calculate the min and max of off-market dates. Then we can put them into our dateDiff function to get the number of days our data spans. To create an 80-20 split, we can multiply it by 0.8 and add it to our min date with dateAdd to get the date value. We can create our train and test sets by using a where function on df off-market date to filter them. An extra where is needed on list date to ensure it contains items listed as of the split date. In this video, we saw how to navigate PySpark ML and a few considerations in the algorithm selection process. Lastly, you learned how to create test and training sets for time series. Let's see you try. Each machine learning algorithm has its own assumptions you need to take into account for it to work appropriately. In this video, we will cover what the assumptions are for random forest regression, what features we have in our final dataset, and lastly, how to get them ready for building a model. The lack of assumptions needed for random forest regression make it and its related methods some of the most popular choices for predicting continuous values. For example, random forests are able to work with non-normally distributed data or data that is unscaled. Missing and categorical data can be handled very easily with value replacements. Adding in external datasets is one of my personal favorite parts of modeling. It's where I find that you can often make huge improvements in your model relatively easily. Here are a few that I added. 30-year mortgage rate to see how much people are willing to pay depending on their rate. City data to see how unique a house is in the area or if it's exceptionally cheap or expensive. Transportation metrics can help us understand how much people are willing to pay for a convenient location. Lastly, I included bank holidays to see if that impacted how or when houses were sold. By all means, this is not an exhaustive list of datasets to include, but just some I chose. Even though we were able to avoid a lot of the onerous pre-processing steps by using random forest regression, there's still plenty of work to do with engineering features. Time components like month or week that a holiday falls on are needed to help attribute seasonal effects. Valuable but often the hardest to create features are rates, ratios, and other generated features that need either business or personal context to create. Lastly, choosing whether or not to expand compound fields is ultimately a judgment call and may be something to consider in the second iteration of your modeling. Since PySpark DataFrames don't have a shape attribute, we'll have to print our own to inspect the final set of information. PySpark ML algorithms require all of the features to be provided in a single column of type vector. We will need to convert our columns for random forest regression to work. To do this, we need to import vector assembler transformer to use it later. Sadly, while random forest regression can handle missing values, vectors cannot. Due to the nature of how tree-based machine learning partitions data, we can just assign missings a value that is outside the range of the variable and replace the nulls with it. But first, we need to know which columns to convert. We can take a list of column names and remove our dependent variable so the vector contains only features. To create a vector assembler, we need to supply it with our list of columns and a name for output. Applying the transformation is done via the transform method. Lastly, we need to create a new data frame with just the columns that matter: sales close price and features. Finally, we are ready for machine learning. Our features have been created and prepared for the algorithm that we are running. Now it's your turn to convert the columns to vectors and get ready for applying random forest regression. We've covered all the necessary steps to prepare ourselves for modeling. In this video, we will cover training, predicting, and evaluating a random forest regression model. The PySpark random forest regressor method has a ton of optional parameters and a few hyperparameters used for tuning. To have a minimally viable model, you will need to set only a handful. First up is features call, which tells the model which column is the vector we created with the vector assembler that now represents all of our feature data. Since we named the column features, we will use that to set features call. Next up is label call, which sets the dependent variable for the model. Ours is named sales close price. Then we need to name our output column by setting prediction call. I find it helpful to be explicit rather than leaving it the default value, so I've named it prediction price. Last of the basic parameters is seed, which by setting this to a value, we can ensure that subsequent runs return the same model. Without it, the random forest would be slightly different. I've set mine to 42 for good luck, but the specific number isn't important. Enough talking, let's build our model. To start, we need to import the random forest regressor from PySpark's ML module. Once that's done, we can initialize random forest regressor with the appropriate columns to use for training and predicting. Again, setting the seed is crucial for repeatability. Lastly, we create a variable to hold our trained model, uninspiredly called model, and train the random forest regressor, RF, by calling fit with our training data frame trainDF. Congratulations, you've created a model. Wait, you want to predict new values with it? Predicting house prices with the model we just trained is straightforward. To do so, we can call transform with the data withheld from training, the test set testDF. If you had new listings of homes and wanted to predict their prices, you'd merely have to pre-process it in the same manner as testDF before using the model to predict prices. Given that testDF has the actual home sale prices, we can inspect them side by side by using the select to grab only the columns we care about and displaying them with show. Predicting values is great, but if we don't know how good we are at it, then what's the point? To evaluate the model, we need to import Regression Evaluator, which allows us to calculate various metrics to gauge model performance. To initialize it, we need to provide the actual values, in this case, sales close price, and the predicted values, which we named prediction price when we created the model. Once we have the instance of evaluator created, we can call it with our predictions data frame and a dictionary of the metric type we wish to evaluate it with. Which metric you choose to optimize is an important decision to make. We can see that our model's RMSE returns a value in the thousands, while our R-squared is less than 1. R-squared is easy to interpret regardless of what you are predicting. If it's 0, you are no better than random chance. If it's 1, you are predicting perfectly. On the other hand, RMSE provides an absolute number of unexplained variance in our model. It's even in the same units as our prediction, US dollars. So even though our R-squared is really high, RMSE indicates that we have $22,000 of unexplained variance on average. This video showed you little code is needed to train, predict, and evaluate a model with PySpark. Now it's your turn to build some models on your own. In this video, we will go over how to interpret the model and then how to save and load it for later use. Now that we've evaluated our model, we will want to understand what features are important in predicting a home selling price. To do this, we will need to import the Pandas library to manipulate this tiny array easier. To use Spark on this would be using a sledgehammer for a delicate task. We will create a DataFrame FIDF to hold our feature importances. These feature importances can be accessed by calling feature importances on the model and then converting them to an array with toArray. Since this is just an array of numbers, we will need to name the new column in the DataFrame importance. Now we just have a single column DataFrame. We will want to create another column using the list of feature names we fed into the vector assembler earlier. We can convert this list into a series by wrapping it with PD series. Next, since we have over 100 features, we only want to look at the most important ones, so we will use Pandas sort values to sort the column importances in descending order. Now it's as simple as displaying out the results to the screen. Here we can see the biggest predictor of how much your house will sell for is how much you listed it for. Intuitively, this makes a lot of sense. Realtors are skilled in setting the value of the house, and it has the effect of anchoring the price, meaning it will likely only marginally increase or decrease from that value. Last but not least, it's important to know how to save and load the model. Luckily, this is very simple now. To save it, just call save on your model and give it a model name. Note that the model isn't a single file, but a directory containing many files defining your model. To load your data, you need to import Random Forest Regression Model from PySpark MLregression and provide it the location and the name of your model. In this video, we learned how to interpret results and save and load a model for later use. Let's see you give it a try. Thank you for making it to the end of this course. Let's take a minute to review what we've learned. In this course, you learned many ways to inspect your data visually and statistically, data manipulation techniques such as dropping rows and columns, scaling and adjusting data, and handling missing values. You also learned how to enrich your data sets by joining external data sets, generating features, extracting variables from messy fields, and various encoding techniques. Lastly, you learned a bit about how all this ties into modeling by training and evaluating a model and interpreting the results. That sure was a lot of stuff we covered in a short amount of time. I hope you will be able to take what you've learned here and apply it to real-world problems and make the world a better place with data science. John Hogue out.
Hi, Welcome to the course on machine learning with Apache Spark, in which you will learn how to build machine learning models on large datasets using distributed computing techniques. Let's start with some fundamental concepts. Suppose you wanted to teach a computer how to make waffles. You could find a good recipe and then give the computer explicit instructions about ingredients and proportions. Alternatively, you could present the computer with a selection of different waffle recipes and let it figure out the ingredients and proportions for the best recipe. The second approach is how machine learning works. The computer literally learns from examples. Machine learning problems are generally less esoteric than finding the perfect waffle recipe. The most common problems apply either regression or classification. A regression model learns to predict a number. For example, when making waffles, how much flour should be used for a particular amount of sugar. A classification model, on the other hand, predicts a discrete or categorical value. For example, is a recipe calling for a particular amount of sugar and salt more likely to be for waffles or cupcakes? The performance of a machine learning model depends on data. In general, more data is a good thing. If an algorithm is able to train on a larger set of data, then its ability to generalize to new data will inevitably improve. However, there are some practical constraints. If the data can fit entirely into RAM, then the algorithm can operate efficiently. What happens when those data no longer fit into memory? The computer will start to use virtual memory, and data will be paged back and forth between RAM and disk. Relative to RAM access, retrieving data from disk is slow. As the size of the data grows, paging becomes more intense and the computer begins to spend more and more time waiting for data. Performance plummets. How then do we deal with truly large datasets? One option is to distribute the problem across multiple computers in a cluster. Rather than trying to handle a large dataset on a single machine, it's divided up into partitions, which are processed separately. Ideally, each data partition can fit into RAM on a single computer in the cluster. This is the approach used by Spark. Spark is a general-purpose framework for cluster computing. It is popular for two main reasons. It's generally much faster than other big data technologies like Hadoop because it does most processing in memory. And it has a developer-friendly interface which hides much of the complexity of distributed computing. Let's review the components of a Spark cluster. The cluster itself consists of one or more nodes. Each node is a computer with CPU, RAM, and physical storage. A cluster manager allocates resources and coordinates activity across the cluster. Every application running on the Spark cluster has a driver program. Using the Spark API, the driver communicates with the cluster manager, which in turn distributes work to the nodes. On each node, Spark launches an executor process, which persists for the duration of the application. Work is divided up into tasks, which are simply units of computation. The executors run tasks in multiple threads across the cores in a node. When working with Spark, you normally don't need to worry too much about the details of the cluster. Spark sets up all of that infrastructure for you and handles all interactions within the cluster. However, it's still useful to know how it works under the hood. You now have a basic understanding of the principles of machine learning and distributed computing with Spark. Next, we'll learn how to connect to a Spark cluster. The previous lesson was high-level overviews of machine learning and Spark. In this lesson, you'll review the process of connecting to Spark. The connection with Spark is established by the driver, which can be written in either Java, Scala, Python, or R. Each of these languages has advantages and disadvantages. Java is relatively verbose, requiring a lot of code to accomplish even simple tasks. By contrast, Scala, Python, and R are high-level languages which can accomplish much with only a small amount of code. They also offer a REPL or read, evaluate, print loop, which is crucial for interactive development. You'll be using Python. Python doesn't talk natively to Spark, so we'll kick off by importing the PySpark module, which makes Spark functionality available in the Python interpreter. Spark is under vigorous development. Because the interface is evolving, it's important to know what version you're working with. We'll be using version 2.4.1, which was released in March 2019. In addition to the main PySpark module, there are a few submodules which implement different aspects of the Spark interface. There are two versions of Spark machine learning: MLlib, which uses an unstructured representation of data in RDDs and has been deprecated, and ML, which is based on a structured, tabular representation of data in DataFrames. We'll be using the latter. With the PySpark module loaded, you're able to connect to Spark. The next thing you need to do is tell Spark where the cluster is located. Here there are two options. You can either connect to a remote cluster, in which case you need to specify a Spark URL, which gives the network location of the cluster's master node. The URL is composed of an IP address or DNS name and a port number. The default port for Spark is 7077, but this must still be explicitly specified. When you're figuring out how Spark works, the infrastructure of a distributed cluster can get in the way. That's why it's useful to create a local cluster where everything happens on a single computer. This is the setup that you're going to use throughout this course. For a local cluster, you need only specify local and, optionally, the number of cores to use. By default, a local cluster will run on a single core. Alternatively, you can give a specific number of cores or simply use the wildcard to choose all available cores. You connect to Spark by creating a SparkSession object. The SparkSession class is found in the PySpark.SQL submodule. You specify the location of the cluster using the master method. Optionally, you can assign a name to the application using the appName method. Finally, you call the get or create method, which will either create a new session object or return an existing object. Once the session has been created, you're able to interact with Spark. Finally, although it's possible for multiple Spark sessions to coexist, it's good practice to stop the Spark session when you're done. Great. Let's connect to Spark. In this lesson, you'll look at how to read data into Spark. Spark represents tabular data using the DataFrame class. The data are captured as rows or records, each of which is broken down into one or more columns or fields. Every column has a name and a specific data type. Some selected methods and attributes of the DataFrame class are listed here. The count method gives the number of rows. The show method will display a subset of rows. The print schema method and the dtypes attribute give different views on column types. This is really scratching the surface of what's possible with a data frame. You can find out more by consulting the extensive documentation. CSV is a common format for storing tabular data. For illustration, we'll be using a CSV file with characteristics for a selection of motor vehicles. Each line in a CSV file is a new record, and within each record, fields are separated by a delimiter character, which is normally a comma. The first line is an optional header record, which gives column names. Our session object has a read attribute, which in turn has a CSV method, which reads data from a CSV file and returns a data frame. The CSV method has one mandatory argument, the path to the CSV file. There are a number of optional arguments. We'll take a quick look at some of the most important ones. The header argument specifies whether or not there is a header record. The sep argument gives the field separator, which is a comma by default. There are two arguments which pertain to column data types, schema and infer schema. Finally, the null value argument gives the placeholder used to indicate missing data. Let's take a look at the data we've just loaded. Using the show method, we can take a look at a slice of the data frame. The CSV method has split the data into rows and columns and picked up the column names from the header record. Looks great, doesn't it? Unfortunately, there's a small snag. Before we unravel that snag, it's important to note that the first value in the cylinder column is not a number. It's the string NA, which indicates missing data. If you check the column data types, then you'll find that they are all strings. That doesn't make sense since the last 6 columns are clearly numbers. However, this is the expected behavior. The CSV method treats all columns as strings by default. You need to do a little more work to get the correct column types. There are 2 ways that you can do this: infer the column types from the data, or manually specify the types. It's possible to reasonably deduce the column types by setting the infer schema argument to true. There is a price to pay though. Spark needs to make an extra pass over the data to figure out the column types before reading the data. If the data file is big, then this will increase the load time notably. Using this approach, all of the column types are correctly identified, except for cylinder. Why? The first value in this column is in A, so Spark thinks that the column contains strings. Missing data in CSV files are normally represented by a placeholder, like the NA string. We can use the null value argument to specify the placeholder. It's always a good idea to explicitly define the missing data placeholder. The null value argument is case sensitive, so it's important to provide it in exactly the same form as it appears in the data file. If inferring column type is not successful, then you have the option of specifying the type of each column in an explicit schema. This also makes it possible to choose alternative column names. This is what the final car's data look like. Note that the missing value at the top of the cylinders column is indicated by the special null constant. You're ready to use what you've learned to load data from CSV files. In this lesson, you're going to learn how to prepare data for building a machine learning model. You'll be working with the car's data again. This is what the data look like at present. There are columns for the maker and model. the origin, either USA or non-USA, the type, number of cylinders, engine size, weight, length, RPM, and fuel consumption. The models that you'll be building will depend on the physical characteristics of the cars, rather than the model names or manufacturers, so you'll remove the corresponding columns from the data. There are two approaches to doing this. Either you can drop the columns that you don't want, or you can select the fields which you do want to retain. Either way, the resulting data does not include those columns. Earlier, you saw that there is a missing value in the cylinders column. Let's check to see how many other missing values there are. You'll use the filter method and provide a logical predicate using SQL syntax, which identifies null values. Then, the count method tells you how many records there are remaining. Just one. In this case, it makes sense to simply remove the record with the missing value. There are a couple of ways that you could do this. You could use the filter method again with a different predicate. Or you could take a more aggressive approach and use the drop_NA method to drop all records with missing values in any column. However, this should be done with care because it could result in the loss of a lot of otherwise useful data. You've now stripped down the data to what's needed to build the model. At present, the weight and length columns are in units of pounds and inches respectively. You'll use the width column method to create a new mass column in units of kilograms. The round function is used to limit the precision of the result. You can also use the width column method to replace the existing length column with values in meters. You now have mass and length in metric units. The type column consists of strings which represent 6 categories of vehicle type. You'll need to transform those strings into numbers. You do this using an instance of the string indexer class. In the constructor, you provide the name of the string input column and a name for the new output column to be created. The indexer is first fit to the data, creating a string indexer model. During the fitting process, the distinct string values are identified and an index is assigned to each value. The model is then used to transform the data, creating a new column with the index values. By default, the index values are assigned according to the descending relative frequency of each of the string values. Midsize is the most common, so it gets an index of 0. Small is the next most common, so its index is 1, and so on. It's possible to choose different strategies for assigning index values by specifying the string order type argument. Rather than using frequency of occurrence, strings can be ordered alphabetically. It's also possible to choose between ascending and descending order. You'll be building a classifier to predict whether or not a car was manufactured in the USA. So the origin column also needs to be converted from strings into numbers. The final step in preparing the car's data is to consolidate the various input columns into a single column. This is necessary because the machine learning algorithms in Spark operate on a single vector of predictors, although each element in that vector may consist of multiple values. To illustrate the process, you'll start with just a pair of features, cylinders and size. First, you create an instance of the vector assembler class, providing it with the names of the columns that you want to consolidate and the name of the new output column. The assembler is then used to transform the data. Taking a look at the relevant columns, you see that the new features column consists of values from the cylinders and size columns, consolidated into a vector. Ultimately, you're going to assemble all of the predictors into a single column. Let's try out what we've learned on the SMS and flights data. Your first machine learning model will be a decision tree. This is probably the most intuitive model, so it seems like a good place to start. A decision tree is constructed using an algorithm called recursive partitioning. Consider a hypothetical example in which you build a decision tree to divide data into two classes, green and blue. You start by putting all of the records into the root node. Suppose that there are more green records than blue, in which case this node will be labeled green. Now, from amongst the predictors in the data, you need to choose the one that will result in the most informative split of the data into two groups. Ideally, you want the groups to be as homogeneous or pure as possible. One should be mostly green and the other should be mostly blue. Once you've identified the most informative predictor, you split the data into two sets labeled green or blue according to the dominant class. And this is where the recursion kicks in. You then apply exactly the same procedure on each of the child nodes, selecting the most informative predictor and splitting again. So, for example, the green node on the left could be split again into two groups, and the resulting green node could once again be split. The depth of each branch of the tree need not be the same. There are a variety of stopping criteria which can cause splitting to stop along a branch. For example, if the number of records in a node falls below a threshold, or the purity of a node is above a threshold, then you might stop splitting. Once you have built the decision tree, you can use it to make predictions for new data by following the splits from the root node along to the tip of a branch. The label for the final node would then be the prediction for the new data. Let's make this more concrete by looking at the cars data. You've transformed the country of origin column into a numeric index called label, with 0 corresponding to cars manufactured in the USA and 1 for everything else. The remaining columns have all been consolidated into a column called features. You want to build a decision tree which will use features to predict label. An important aspect of building a machine learning model is being able to assess how well it works. In order to do this, we use the random split method to randomly split our data into two sets, a training set and a testing set. The proportions may vary, but generally you're looking at something like an 80-20 split, which means that the training set ends up having around 4 times as many records as the testing set. Finally, the moment has come. You're going to build a decision tree. You start by creating a decision tree classifier object. The next step is to fit the model to the training data by calling the fit method. Now that you've trained the model, you can assess how effective it is by making predictions on the test set and comparing the predictions to the known values. The transform method adds new columns to the data frame. The prediction column gives the class assigned by the model. You can compare this directly to the known labels in the testing data. Although the model gets the first example wrong, it's correct for the following 4 examples. There's also a probability column, which gives the probabilities assigned to each of the outcome classes. For the first example, the model predicts that the outcome is 0 with probability 96%. A good way to understand the performance of a model is to create a confusion matrix, which gives a breakdown of the model predictions versus the known labels. The confusion matrix consists of 4 counts, which are labeled as follows: Positive indicates a prediction of 1, while negative indicates a prediction of 0, and true corresponds to a correct prediction, while false designates an incorrect prediction. In this case, the true positives and true negatives dominate, but the model still makes a number of incorrect predictions. These counts can be used to calculate the accuracy, which is the proportion of correct predictions. For our model, the accuracy is 74%. So, now that you know how to build a decision tree model with Spark, you can try that out on the flight data. You've learned to build a decision tree, but it's good to have options. Logistic regression is another commonly used classification model. It uses a logistic function to model a binary target, where the target states are usually denoted by 1 and 0, or true and false. The maths of the model are outside the scope of this course, but this is what the logistic function looks like. For a logistic regression model, the x-axis is a linear combination of predictive variables, and the y-axis is the output of the model. Since the value of the logistic function is a number between 0 and 1, it's often thought of as a probability. In order to translate the number into one or other of the target states, it's compared to a threshold, which is normally set at 1/2. If the number is above the threshold, then the predicted state is 1. Conversely, if it's below the threshold, then the predicted state is 0. The model derives coefficients for each of the numerical predictors. Those coefficients might shift the curve to the right or to the left. They might make the transition between states more gradual or more rapid. These characteristics are all extracted from the training data and will vary from one set of data to another. Let's make this more concrete by returning to the cars data. You'll focus on the numerical predictors for the moment and return to the categorical predictors later on. As before, you prepare the data by consolidating the predictors into a single column and then randomly splitting the data into training and testing sets. To build a logistic regression model, you first need to import the associated class and then create a classifier object. This is then fit to the training data using the fit method. With the trained model, you're able to make predictions on the testing data. As you saw with the decision tree, the transform method adds the prediction and probability columns. The probability column gives the predicted probability of each class, while the prediction column reflects the predicted label, which is derived from the probabilities by applying the threshold mentioned earlier. You can assess the quality of the predictions by forming a confusion matrix. The quantities in the cells of the matrix can then be used to form some informative ratios. Recall that a positive prediction indicates that a car is manufactured outside of the US, and that the predictions are considered to be true or false depending on whether they are correct or not. Precision is the proportion of positive predictions which are correct. For your model, 2/3 of predictions for cars manufactured outside of the US are correct. Recall is the proportion of positive targets which are correctly predicted. Your model also identifies 80% of cars which are actually manufactured outside of the US. Bear in mind that these metrics are based on a relatively small testing set. Another way of looking at these ratios is to weight them across the positive and negative predictions. You can do this by creating an evaluator object and then calling the evaluate method. This method accepts an argument which specifies the required metric. It's possible to request the weighted precision and recall as well as the overall accuracy. It's also possible to get the F1 metric the harmonic mean of precision and recall, which is generally more robust than the accuracy. All of these metrics have assumed a threshold of 1/2. What happens if you vary that threshold? A threshold is used to decide whether the number returned by the logistic regression model translates into either the positive or the negative class. By default, that threshold is set at 1/2. However, this is not the only choice. Choosing a larger or smaller value for the threshold will affect the performance of the model. The ROC curve plots the true positive rate versus the false positive rate as the threshold increases from 0, top right, to 1, bottom left. The AUC summarizes the ROC curve in a single number. It's literally the area under the ROC curve. AUC indicates how well a model performs across all values of the threshold. An ideal model that performs perfectly regardless of the threshold would have AUC of 1. In an exercise, we'll see how to use another evaluator to calculate the AUC. You now know how to build a logistic regression model and assess the performance of that model using various metrics. Let's give this a try. It's said that 80% of machine learning is data preparation. As we'll see in this lesson, this is particularly true for text data. Before you can use machine learning algorithms, you need to take unstructured text data and create structure, ultimately transforming the data into a table. We start with a collection of documents. These documents might be anything from a short snippet of text, like an SMS or email, to a lengthy report or book. Each document will become a record in the table. The text in each document will be mapped to columns in the table. First, the text is split into words or tokens. You then remove short or common words that do not convey too much information. The table will then indicate the number of times that each of the remaining words occurred in the text. This table is also known as a term document matrix. There are some nuances to the process, but that's the central idea. Suppose that your documents are the names of children's books. The raw data might look like this. Your job will be to transform these data into a table with one row per document and a column for each of the words. You're interested in words, not punctuation. You'll use regular expressions, or regex, a mini language for pattern matching, to remove the punctuation symbols. Regular expressions is another big topic and outside the scope of this course, but basically you're giving a list of symbols or text pattern to match. The hyphen is escaped by the backslashes because it has another meaning in the context of regular expressions. By escaping it, you tell Spark to interpret the hyphen literally. You need to specify a column name, books.txt, a pattern to be matched, stored in the variable regex, and the replacement text, which is simply a space. You now have some double spaces, but you can use regex to clean those up too. Next, you split the text into words or tokens. You create a tokenizer object, giving it the name of the input column containing the text and the output column, which will contain the tokens. The tokenizer is then applied to the text using the transform method. In the results, you see a new column in which each document has been transformed into a list of words. As a side effect, the words have all been reduced to lowercase. Some words occur frequently in all of the documents. These common or stop words convey very little information, so you will also remove them using an instance of the stopwords remover class. This contains a list of stopwords which can be customized if necessary. Since you didn't give the input and output column names earlier, you specify them now and then apply the transform method. You could also have given these names when you created the remover. Your documents might contain a large variety of words, so in principle, our table could end up with an enormous number of columns, many of which would be only sparsely populated. It would also be handy to convert the words into numbers. Enter the hashing trick, which in simple terms converts words into numbers. You create an instance of the hashing TF class, providing the names of the input and output columns. You also give the number of features, which is effectively the largest number that will be produced by the hashing trick. This needs to be sufficiently big to capture the diversity in the words. The output in the hash column is presented in sparse format, which we will talk about more later on. For the moment, though, it's enough to note that there are two lists. The first list contains the hashed values, and the second list indicates how many times each of those values occurs. For example, in the first document, the word long has a hash of 8 and occurs twice. Similarly, the word 5 has a hash of 6 and occurs once in each of the last two documents. The final step is to account for some words occurring frequently across many documents. If a word appears in many documents, then it's probably going to be less useful for building a classifier. We want to weight the number of counts for a word in a particular document against how frequently that word occurs across all documents. To do this, you reduce the effective count for more common words, giving what is known as the inverse document frequency. The word 5, for example, occurs in multiple documents, so its effective frequency is reduced. Conversely, the word long only occurs in one document, so its effective frequency is increased. Inverse document frequency is generated by the IDF class. The inverse document frequencies are precisely what we need for building a machine learning model. Let's do that with the SMS data. In the last chapter, you saw how to use categorical variables in a model by simply converting them to indexed numerical values. In general, this is not sufficient for a regression model. Let's see why. In the cars data, the type column is categorical with 6 levels: midsize, small, compact, sporty, large, and van. Here you can see the number of times that each of those levels occurs in the data. You used a string indexer to assign a numerical index to each level. However, there's a problem with the index. The numbers don't have any objective meaning. The index for sporty is 3. Does it make sense to do arithmetic on that index? No. For example, it wouldn't be meaningful to add the index for sporty to the index for compact. Nor would it be valid to compare those indexes and say that sporty is larger or smaller than compact. However, a regression model works by doing precisely this: arithmetic on predictive variables. You need to convert the indexed values into a format in which you can perform meaningful mathematical operations. The first step is to create a column for each of the levels. Effectively, you then place a check in the column corresponding to the value in each row. So, for example, a record with the type of sporty would have a check in the sporty column. These new columns are known as dummy variables. However, rather than having checks in the dummy variable columns, it makes more sense to use binary values, where a 1 indicates the presence of the corresponding level. It might occur to you that the volume of data has exploded. You've gone from a single column of categorical variables to 6 binary encoded dummy variables. If there were more levels, then you'd have even more columns. This could get out of hand. However, the majority of the cells in the new columns contain zeros. The non-zero values, which actually encode the information, are relatively infrequent. This effect becomes even more pronounced if there are more levels. You can exploit this by converting the data into a sparse format. Rather than recording the individual values, the sparse representation simply records the column numbers and the value for the non-zero values. You can take this one step further. Since the categorical levels are mutually exclusive, you can drop one of the columns. If type is not midsize, small, compact, sporty, or large, then it must be van. The process of creating dummy variables is called one-hot encoding, because only one of the columns created is ever active or hot. Let's see how this is done in Spark. As you might expect, there's a class for doing one-hot encoding. Import the one-hot encoder estimator class from the feature submodule. When instantiating the class, you need to specify the names of the input and output columns. For car type, the input column is the index we defined earlier. Choose type dummy as the output column name. Note that these arguments are given as lists, so it's possible to specify multiple columns if necessary. Next, fit the encoder to the data. Check how many category levels have been identified. 6, as expected. Now that the encoder is set up, it can be applied to the data by calling the transform method. Let's take a look at the results. There's now a type dummy column, which captures the dummy variables. As mentioned earlier, the final level is treated differently. No column is assigned to type van, because if a vehicle isn't one of the other types, then it must be a van. To have a separate dummy variable for van would be redundant. The sparse format used to represent dummy variables looks a little complicated. Let's take a moment to dig into dense versus sparse formats. Suppose that you want to store a vector which consists mostly of zeros. You could store it as a dense vector in which each of the elements of the vector is stored explicitly. This is wasteful though, because most of those elements are zeros. A sparse representation is a much better alternative. To create a sparse vector, you need to specify the size of the vector, in this case 8, the positions which are non-zero, in this case positions 0 and 5, noting that we start counting at 0, and the values for each of those positions, 1 and 7. Sparse representation is essential for effective one-hot encoding on large datasets. Let's try out one-hot encoding on the flights data. In the previous lesson, you learned how to one-hot encode categorical features, which is essential for building regression models. In this lesson, you'll find out how to build a regression model to predict numerical values. Returning to the cars data, suppose you wanted to predict fuel consumption using vehicle mass. A scatter plot is a good way to visualize the relationship between those two variables. Only a subset of the data are included in this plot, but it's clear that consumption increases with mass. However, the relationship is not perfectly linear. There's scatter for individual points. A model should describe the average relationship of consumption to mass without necessarily passing through individual points. This line, for example, might describe the underlying trend in the data. But there are other lines which could equally well describe that trend. How do you choose the line which best describes the relationship? First, we need to define the concept of residuals. The residual is the difference between the observed value and the corresponding modeled value. The residuals are indicated in the plot as the vertical lines between the data points and the model line. The best model would somehow make these residuals as small as possible. Out of all possible models, the best model is found by minimizing a loss function, which is an equation that describes how well the model fits the data. This is the equation for the mean squared error loss function. Let's quickly break it down. You've got the observed values y sub I and the modeled values y hat sub I. The difference between these is the residual. The residuals are squared and then summed together, before finally dividing through by the number of data points to give the mean or average. By minimizing the loss function, you're effectively minimizing the average residual, or the average distance between the observed and modeled values. If this looks a little complicated, don't worry, Spark will do all of the maths for you. Let's build a regression model to predict fuel consumption using 3 predictors: mass, number of cylinders, and vehicle type, where the last is a categorical which we've already one-hot encoded. As before, the first step towards building a model is to take our predictors and assemble them into a single column called features. The data are then randomly split into training and testing sets. The model is created using the linear regression class, which is imported from the regression module. By default, this class expects to find the target data in a column called label. Since you are aiming to predict the consumption column, you need to explicitly specify the name of the label column when creating a regression object. Next, train the model on the training data using the fit method. The trained model can then be used to make predictions on the testing data using the transform method. Comparing the predicted values to the known values from the testing data, you'll see that there is reasonable agreement. It's hard to tell from a table though. A plot gives a clearer picture. The dashed diagonal line represents perfect prediction. Most of the points lie close to this line, which is good. It's useful to have a single number which summarizes the performance of a model. For classifiers, there are a variety of such metrics. The root mean squared error is often used for regression models. It's the square root of the mean squared error, which you've already encountered, and it corresponds to the standard deviation of the residuals. The metrics for a classifier, like accuracy, precision, and recall, are measured on an absolute scale, where it's possible to immediately identify values that are good or bad. Values of root mean squared error are relative to the scale of the value that you're aiming to predict, so interpretation is a little more challenging. A smaller root mean squared error, however, always indicates better predictions. Let's examine the model. The intercept is the value predicted by the model when all predictors are 0. On the plot, this is the point where the model line intersects the vertical dashed line. You can find this value for the model using the intercept attribute. This is the predicted fuel consumption when both mass and number of cylinders are 0, and the vehicle type is van. Of course, this is an entirely hypothetical scenario. No vehicle could have 0 mass. There's a slope associated with each of the predictors too, which represents how rapidly the model changes when that predictor changes. The coefficients attribute gives you access to those values. There's a coefficient for each of the predictors. The coefficients for mass and number of cylinders are positive, indicating that heavier cars with more cylinders consume more fuel. These coefficients also represent the rate of change for the corresponding predictor. For example, the coefficient for mass indicates the change in fuel consumption when mass increases by 1 unit. Remember that there's no dummy variable for van. The coefficients for the type dummy variables are relative to vans. These coefficients should also be interpreted with care. If you are going to compare the values for different vehicle types, then this needs to be done for fixed mass and number of cylinders. Since all of the type dummy coefficients are negative, the model indicates that, for a specific mass and number of cylinders, all other vehicle types consume less fuel than a van. Large vehicles have the most negative coefficient, so it's possible to say that for a specific mass and number of cylinders, large vehicles are the most fuel efficient. You've covered a lot of ground in this lesson. Let's apply what you've learned to the flights data. The largest improvements in machine learning model performance are often achieved by carefully manipulating features. In this lesson, you'll be learning about a few approaches to doing this. Let's start with bucketing. It's often convenient to convert a continuous variable like age or height into discrete values. This can be done by assigning values to buckets or bins with well-defined boundaries. The buckets might have uniform or variable width. Let's make this more concrete by thinking about observations of people's heights. If you plot the heights on a histogram, then it seems reasonable to divide the heights up into ranges. To each of these ranges, you assign a label. Then, you create a new column in the data with the appropriate labels. The resulting categorical variable is often a more powerful predictor than the original continuous variable. Let's apply this to the cars data. Looking at the distribution of values for RPM, you see that the majority lie in the range between 4,500 and 6,000. There are a few either below or above this range. This suggests that it would make sense to bucket these values according to those boundaries. You create a bucketizer object, specifying the bin boundaries as the splits argument, and also providing the names of the input and output columns. You then apply this object to the data by calling the transform method. The result has a new column with the discrete bucket values. The three buckets have been assigned indexed values 0, 1, and 2, corresponding to the low, medium, and high ranges for RPM. As you saw earlier, before you can use these index values in a regression model, they first need to be one-hot encoded. The low and medium RPM ranges are mapped to a distinct dummy variable, while the high range is the reference level and does not get a separate dummy variable. Let's look at the intercept and coefficients for a model which predicts fuel consumption based on bucketed RPM data. The intercept tells us what the fuel consumption is for the reference level, which is the high RPM bucket. To get the consumption for the low RPM bucket, you add the first coefficient to the intercept. Similarly, to find the consumption for the medium RPM bucket, you add the second coefficient to the intercept. There are many other approaches to engineering new features. It's common to apply arithmetic operations to one or more columns to create new features. Returning to the heights data, suppose that we also had data for mass. Then, it might be perfectly reasonable to engineer a new column for BMI. Potentially, BMI might be a more powerful predictor than either height or mass in isolation. Let's apply this idea to the cars data. You have columns for mass and length. Perhaps some combination of the two might be even more meaningful. You can create different forms of density by dividing the mass through by the first 3 powers of length. Since you only have the length of the vehicle, but not their width or height, the length has been used as a proxy for these missing dimensions. In so doing, you create 3 new predictors. The first density represents how mass changes with vehicle length. The second and third densities approximate how mass varies with the area and volume of the vehicle. Which of these will be meaningful for our model? Right now, you don't know, you're just trying things out. Powerful new features are often discovered through trial and error. In the next lesson, you'll learn about a technique for selecting only the relevant predictors in a regression model. Right now, though, let's apply what you've learned to the flights data. The regression models that you've built up until now have blindly included all of the provided features. Next, you're going to learn about a more sophisticated model, which effectively selects only the most useful features. A linear regression model attempts to derive a coefficient for each feature in the data. The coefficients quantify the effects of the corresponding features. More features imply more coefficients. This works well when your dataset has a few columns and many rows. You need to derive a few coefficients and you have plenty of data. The converse situation, many columns and few rows, is much more challenging. Now, you need to calculate values for numerous coefficients, but you don't have much data to do it. Even if you do manage to derive values for all of those coefficients, your model will end up being very complicated and difficult to interpret. Ideally, you want to create a parsimonious model, one that has just the minimum required number of predictors. It will be as simple as possible, yet still able to make robust predictions. The obvious solution is to simply select the best subset of columns. But how to choose that subset? There are a variety of approaches to this feature selection problem. In this lesson, we'll be exploring one such approach to feature selection known as penalized regression. The basic idea is that the model is penalized or punished for having too many coefficients. Recall that the conventional regression algorithm chooses coefficients to minimize the loss function, which is the average of the squared residuals. A good model will result in low mean squared error because its predictions will be close to the observed values. With penalized regression, an additional regularization or shrinkage term is added to the loss function. Rather than depending on the data, this term is a function of the model coefficients. There are two standard forms for the regularization term. Lasso regression uses a term which is proportional to the absolute value of the coefficients, while ridge regression uses the square of the coefficients. In both cases, this extra term in the loss function penalizes models with too many coefficients. There's a subtle distinction between lasso and ridge regression. Both will shrink the coefficients of unimportant predictors. However, whereas ridge will result in those coefficients being close to zero, lasso will actually force them to zero precisely. It's also possible to have a mix of lasso and ridge. The strength of the regularization is determined by a parameter, which is generally denoted by the Greek symbol lambda. When lambda is 0, there is no regularization. And when lambda is large, regularization completely dominates. Ideally, you want to choose a value for lambda between these two extremes. Let's make this more concrete by returning to the cars data. We've assembled the mass, cylinders, and type columns along with the freshly engineered density columns. We've effectively got 10 predictors available for the model. As usual, we'll split these data into training and testing sets. Let's start by fitting a standard linear regression model to the training data. You can then make predictions on the testing data and calculate the root mean squared error. When you look at the model coefficients, you find that all predictors have been assigned non-zero values. This means that every predictor is contributing to the model. This is certainly possible, but it's unlikely that all of the features are equally important for predicting consumption. Now, let's fit a ridge regression model to the same data. You get a ridge regression model by giving a value of 0 for the elastic net parameter. An arbitrary value of 0.1 has been chosen for the regularization strength. Later, you'll learn a way to choose good values for this parameter based on the data. When you calculate the root mean squared error on the testing data, you find that it has increased slightly, but not enough to cause concern. Looking at the coefficients, you see that they are all smaller than the coefficients for the standard linear regression model. They have been shrunk. Finally, let's build a lasso regression model by setting elastic net param to 1. Again, you find that the testing root mean squared error has increased, but not by a significant degree. Turning to the coefficients, though, you see that something important has happened. All but 2 of the coefficients are now 0. There are effectively only 2 predictors left in the model: the dummy variable for a small type car and the linear density. Lasso regression has identified the most important predictors and set the coefficients for the rest to 0. This tells us that we can get a good model by simply knowing whether or not a car is small and its linear density. A simpler model with no significant loss in performance. Let's try out regularization on our flight duration model. Welcome back! So far, you've learned how to build classifier and regression models using Spark. In this chapter, you'll learn how to make those models better. You'll start by taking a look at pipelines, which will seriously streamline your workflow. They will also help to ensure that training and testing data are treated consistently and that no leakage of information between these two sets takes place. What do I mean by leakage? Most of the actions you've been using involve both a fit and a transform method. Those methods have been applied in a fairly relaxed way, but to get really robust results, you need to be careful only to apply the fit method to training data. Why? Because if a fit method is applied to any of the testing data, then the model will effectively have seen those data during the training phase. So, the results of testing will no longer be objective. The transform method, on the other hand, can be applied to both training and testing data, since it does not result in any changes in the underlying model. A figure should make this clearer. Leakage occurs whenever a fit method is applied to testing data. Suppose that you fit a model using both the training and testing data. The model will then already have seen the testing data, so using those data to test the model would not be fair. Of course, the model will perform well on data, which has been used for training. This sounds obvious, but care must be taken not to fall into this trap. Remember that there are normally multiple stages in building a model, and if the fit method in any of those stages is applied to the testing data, then the model is compromised. However, if you are careful to only apply fit to the training data, then your model will be in good shape. When it comes to testing, it will not have seen any of the testing data, and the test results will be completely objective. Luckily, a pipeline will make it easier to avoid leakage because it simplifies the training and testing process. A pipeline is a mechanism to combine a series of steps. Rather than applying each of the steps individually, they are all grouped together and applied as a single unit. Let's return to our cars regression model. Recall that there were a number of steps involved. Using a string indexer to convert the type column to indexed values, applying a one-hot encoder to convert those indexed values into dummy variables, then assembling a set of predictors into a single features column, and finally, building a regression model. Let's map out the process of applying those steps. First, you fit the indexer to the training data. Then you call the transform method on the training data to add the indexed column. Then you call the transform method on the testing data to add the indexed column there too. Note that the testing data was not used to fit the indexer. Next, you do the same things for the one-hot encoder, fitting to the training data, and then using the fitted encoder to update the training and testing datasets. The assembler is next. In this case, there is no fit method, so you simply apply the transform method to the training and testing data. Finally, the data are ready. You fit the regression model to the training data, and then use the model to make predictions on the testing data. Throughout the process, you've been careful to keep the testing data out of the training process. But this is hard work, and it's easy enough to slip up. A pipeline makes training and testing a complicated model a lot easier. The pipeline class lives in the ML submodule. You create a pipeline by specifying a sequence of stages, where each stage corresponds to a step in the model building process. The stages are executed in order. Now, rather than calling the fit and transform methods for each stage, you simply call the fit method for the pipeline on the training data. Each of the stages in the pipeline is then automatically applied to the training data in turn. This will systematically apply the fit and transform methods for each stage in the pipeline. The trained pipeline can then be used to make predictions on the testing data by calling its transform method. The pipeline transform method will only call the transform method for each of the stages in the pipeline. Isn't that simple? You can access the stages in the pipeline by using the stages attribute, which is a list. You pick out individual stages by indexing into the list. For example, to access the regression component of the pipeline, you'd use an index of 3. Having access to that component makes it possible to get the intercept and coefficients for the trained linear regression model. Pipelines make your code easier to read and maintain. Let's try them out with our flights model. Up until now, you've been testing models using a rather simple technique, randomly splitting the data into training and testing sets, training the model on the training data, and then evaluating its performance on the testing set. There's one major drawback to this approach. You only get one estimate of model performance. You would have a more robust idea of how well a model works if you were able to test it multiple times. This is precisely the idea behind cross-validation. You start out with the full set of data. You still split these data into a training set and a testing set. Remember that before splitting, it's important to first randomize the data so that the distributions in the training and testing data are similar. You then split the training data into a number of partitions or folds. The number of folds normally factors into the name of the technique. For example, if you split into 5 folds, then you'd talk about 5-fold cross-validation. Once the training data have been split into folds, you can start cross-validating. First, keep aside the data in the first fold. Train a model on the remaining 4 folds, then evaluate that model on the data from the first fold. This will give you the first value for the evaluation metric. Next, you move on to the second fold, where the same process is repeated. Data in the second fold are set aside for testing, while the remaining 4 folds are used to train a model. That model is tested on the second fold data, yielding the second value for the evaluation metric. You repeat the process for the remaining folds. Each of the folds is used in turn as testing data, and you end up with as many values for the evaluation metric as there are folds. At this point, you're in a position to calculate the average of the evaluation metric over all the folds, which is a much more robust measure of model performance than a single value. Let's see how this works in practice. Remember the cars data? Of course you do. You're going to build a cross-validated regression model to predict consumption. Here are the first 2 ingredients which you need to perform cross-validation. An estimator, which builds the model and is often a pipeline, and an evaluator, which quantifies how well a model works on testing data. We've seen both of these a few times already. Now the final ingredients. You'll need 2 new classes, cross-validator and param grid builder, both from the tuning submodule. You'll create a parameter grid, which you'll leave empty for the moment, but will return to in detail during the next lesson. Finally, you have everything required to create a cross-validator object, an estimator, which is the linear regression model, an empty grid of parameters for the estimator, and an evaluator, which will calculate the root mean squared error. You can optionally specify the number of folds, which defaults to 3, and a random number seed for repeatability. The cross-validator has a fit method, which will apply the cross-validation procedure to the training data. You can then look at the average root mean squared error calculated across all of the folds. This is a more robust measure of model performance because it is based on multiple train-test splits. Note that the average metric is returned as a list. You'll see why in the next lesson. The trained cross-validator object acts just like any other model. It has a transform method which can be used to make predictions on new data. If we evaluate the predictions on the original testing data, then we find a smaller value for the root mean squared error than we obtained using cross-validation. This means that a simple train-test split would have given an overly optimistic view on model performance. Let's give cross-validation a try on our flights model. So far, you've been using the default parameters for almost everything. You've built some decent models, but they could probably be improved by choosing better model parameters. There is no universal best set of parameters for a particular model. The optimal choice of parameters will depend on the data and the modeling goal. The idea is relatively simple. You build a selection of models, one for each set of model parameters. Then you evaluate those models and choose the best one. You'll be looking at the fuel consumption regression model again. You'll start by doing something simple, comparing a linear regression model with an intercept to one that passes through the origin. By default, a linear regression model will always fit an intercept, but you're going to be explicit and specify the fit intercept parameter as true. You fit the model to the training data and then calculate the root mean squared error for the testing data. Next, you repeat the process, but specify false for the fit intercept parameter. Now you are creating a model which passes through the origin. When you evaluate this model, you find that the root mean squared error is higher. So, comparing these two models, you'd naturally choose the first one, because it has a lower root mean squared error. However, there's a problem with this approach. Just getting a single estimate of root mean squared error is not very robust. It'd be better to make this comparison using cross-validation. You also have to manually build the models for the two different parameter values. It'd be great if that were automated. You can systematically evaluate a model across a grid of parameter values using a technique known as grid search. To do this, you need to set up a parameter grid. You actually saw this in the previous lesson, where you simply created an empty grid. Now you're going to add points to the grid. First, you create a grid builder, and then you add one or more grids. At present, there's just one grid, which takes two values for the fit intercept parameter. Call the build method to construct the grid. A separate model will be built for each point in the grid. You can check how many models this corresponds to, and of course, this is just 2. Now, you create a cross-validator object and fit it to the training data. This builds a bunch of models, one model for each fold and point in the parameter grid. Since there are 2 points in the grid and 10 folds, this translates into 20 models. The cross-validator is going to loop through each of the points in the parameter grid, and for each point, it will create a cross-validated model using the corresponding parameter values. When you take a look at the average metrics attribute, you can see why the metric is given as a list. You get one average value for each point in the grid. The values confirm what you observed before. The model that includes an intercept is superior to the model without an intercept. Our goal was to get the best model for the data. You retrieve this using the appropriately named best model attribute. But it's not actually necessary to work with this directly, because the cross-validator object will behave like the best model. So you can use it directly to make predictions on the testing data. Of course, you want to know what the best parameter value is, and you can retrieve this using the explain param method. As expected, the best value for the fit intercept parameter is true. You can see this after the word current in the output. It's possible to add more parameters to the grid. Here, in addition to whether or not to include an intercept, you're also considering a selection of values for the regularization parameter and the elastic net parameter. Of course, the more parameters and values you add to the grid, the more models you have to evaluate. Because each of these models will be evaluated using cross-validation, this might take a little while. But it will be time well spent because the model that you get back will in principle be much better than what you would have obtained by just using the default parameters. Let's apply grid search on the flights and SMS models. You now know how to choose a good set of parameters for any model using cross-validation and grid search. In the final lesson, you're going to learn about how models can be combined to form a collection or ensemble, which is more powerful than each of the individual models alone. Simply put, an ensemble model is just a collection of models. An ensemble model combines the results from multiple models to produce better predictions than any one of those models acting alone. The concept is based on the idea of the wisdom of the crowd, which implies that the aggregated opinion of a group is better than the opinions of the individuals in that group, even if the individuals are experts. As the quote suggests, for this idea to be true, there must be diversity and independence in the crowd. This applies to models too. A successful ensemble requires diverse models. It does not help if all of the models in the ensemble are similar or exactly the same. Ideally, each of the models in the ensemble should be different. A random forest, as the name implies, is a collection of trees. To ensure that each of those trees is different, the decision tree algorithm is modified slightly. Each tree is trained on a different random subset of the data, and within each tree, a random subset of features is used for splitting at each node. The result is a collection of trees where no two trees are the same. Within the random forest model, all of the trees operate in parallel. Let's go back to the cars classifier yet again. You create a random forest model using the random forest classifier class from the classification submodule. You can select the number of trees in the forest using the numTrees parameter. By default, this is 20, but we'll drop that down to 5 so that the results are easier to interpret. As is the case with any other model, the random forest is fit to the training data. Once the model is trained, it's possible to access the individual trees in the forest using the trees attribute. You would not normally do this, but it's useful for illustrative purposes. There are precisely 5 trees in the forest, as specified. The trees are all different, as can be seen from the varying number of nodes in each tree. You can then make predictions using each tree individually. Here are the predictions of individual trees on a subset of the testing data. Each row represents predictions from each of the 5 trees for a specific record. In some cases, all of the trees agree, but there is often some dissent amongst the models. This is precisely where the random forest works best, where the prediction is not clear-cut. The random forest model creates a consensus prediction by aggregating the predictions across all of the individual trees. You don't need to worry about these details though, because the transform method will automatically generate a consensus prediction column. It also creates a probability column, which assigns aggregate probabilities to each of the outcomes. It's possible to get an idea of the relative importance of the features in the model by looking at the feature importances attribute. An importance is assigned to each feature, where a larger importance indicates a feature which makes a larger contribution to the model. Looking carefully at the importances, we see that feature 4, RPM, is the most important, while feature 0, the number of cylinders, is the least important. The second ensemble model you'll be looking at is gradient boosted trees. Again, the aim is to build a collection of diverse models, but the approach is slightly different. Rather than building a set of trees that operate in parallel, now we build trees which work in series. The boosting algorithm works iteratively. First, build a decision tree and add to the ensemble. Then, use the ensemble to make predictions on the training data. Compare the predicted labels to the known labels. Now, identify training instances where the predictions were incorrect. Return to the start and train another tree which focuses on improving the incorrect predictions. As trees are added to the ensemble, its predictions improve because each new tree focuses on correcting the shortcomings of the preceding trees. The class for the gradient boosted tree classifier is also found in the classification submodule. After creating an instance of the class, you fit it to the training data. You can make an objective comparison between a plain decision tree and the two ensemble methods by looking at the values of AUC obtained by each of them on the testing data. Both of the ensemble methods score better than the decision tree. This is not too surprising since they are significantly more powerful models. It's also worth noting that these results are based on the default parameters for these models. It should be possible to get even better performance by tuning those parameters using cross-validation. In the final set of exercises, you'll try out ensemble methods on the flights data. Congratulations on completing this course on machine learning with Apache Spark. You have covered a lot of ground, reviewing some machine learning fundamentals and seeing how they can be applied to large datasets using Spark for distributed computing. You learned how to load data into Spark and then perform a variety of operations on those data. Specifically, you learned basic column manipulation on DataFrames, how to deal with text data, bucketing continuous data, and one-hot encoding categorical data. You then delved into two types of classifiers, decision trees and logistic regression. In the process, building a robust spam classifier. You also learned about partitioning your data and how to use testing data and a selection of metrics to evaluate a model. Next, you learned about regression, starting with a simple linear regression model and progressing to penalized regression, which allowed you to build a model using only the most relevant predictors. You learned about pipelines and how they can make your Spark code cleaner and easier to maintain. This led naturally into using cross-validation and grid search to derive more robust model metrics and use them to select good model parameters. Finally, you encountered two forms of ensemble models. Of course, there are many topics that were not covered in this course. If you want to dig deeper, then consult the excellent and extensive online documentation. Importantly, you can find instructions for setting up and securing a Spark cluster. Now, go and use what you've learned to solve challenging and interesting big data problems in the real world.
Hi, welcome to this course on building recommendation engines using alternating least squares, or ALS, in PySpark. You're probably already familiar with the output of these types of recommendation engines, where a website tells you something along the lines of, if you like that, then you'll probably like this. You've likely seen these types of recommendations on your favorite retail or media streaming websites. These recommendations are generated through different types of data that you as a user provide either directly or indirectly. When you purchase something online, or watch a movie, or even read an article, you're often given a chance to rate that item on a scale of 1 to 5 stars, a thumbs up or thumbs down, or some other type of rating scale. Based on your feedback from these types of rating systems, companies can learn a lot about your preferences and offer you recommendations based on preferences of users that are similar to you. For example, if your movie streaming service sees that you liked The Dark Knight and Iron Man and did not like Tangled, and it also sees other users that also liked The Dark Knight and Iron Man and also did not like Tangled, the ALS algorithm would see that you and these other users have similar tastes. It would then look at the movies that you have not yet seen and see which ones are the highest rated among those similar users, and offer them as recommendations to you. This is why websites will often say things like, because you like that movie, we think you'll like this movie, or users like you also watched this movie. These types of rating systems are extremely powerful. In fact, an article published by McKinsey & Company in October of 2013 stated that 35% of what customers buy on Amazon and 75% of what they watch on Netflix come from product recommendations based on algorithms such as the one you are going to be learning in this course. That's a powerful use of data, and with this course you will learn how to do this. In addition to this, there are alternate uses of recommendation algorithms that can be extremely useful for purposes as broad as feature space reduction, image compression, mathematical user and product grouping, latent feature discovery, and you're going to learn some of these in this course. This tutorial is intended for those that have experience with Spark and Python and understand the fundamentals of machine learning. If needed, some good introductory resources are DataCamp's Introduction to PySpark course, their Intermediate Python for Data Science course, and their Supervised Machine Learning with Python's Scikit-learn course. Let's jump in. In the world of recommendation engines, there are two basic types: collaborative filtering engines and content-based filtering engines. Both aim to offer meaningful recommendations, but they do so in slightly different ways. Content-based filtering, as the name suggests, tries to understand the content or features of the items and makes recommendations based on your preferences for those specific features. For example, a movie streaming service might go to great lengths to add descriptive tags to their movies, such as the genre, whether it's animated or not, the language spoken in the movie, the decade it was filmed, and which actors were in it. So when a user like you gives 5 stars to a really dramatic Portuguese movie with specific actors from a specific decade, they can infer that you like movies like this and will also like other dramatic movies in Portuguese with those same actors, and recommend those movies to you. Collaborative filtering is a little bit different. As explained in the previous video, collaborative filtering is based on user similarity. However, unlike content-based filtering, manually created tags are not necessary. The features and groupings are created mathematically from patterns in the ratings provided by users. When you provide ratings for a product or item, whether it be a thumbs up or thumbs down, or even if you just watch a video without even giving it a rating, you are providing meaningful insight about your preferences. From this behavior, the ALS algorithm can mathematically group you with similar users, predict your behavior, and help you have a more effective customer experience. While ALS can have content-based applications, this course will focus on its application to collaborative filtering. But many of the principles of collaborative filtering can be applied to content-based applications. Now let's talk about ratings. In the realm of recommendation engines, there are two main types of ratings: explicit ratings and implicit ratings. Explicit ratings are pretty straightforward. Examples of these are when you input a number of stars or something like a thumbs up or thumbs down. These are explicit ratings because users explicitly state how much they like or dislike something. Implicit ratings are a little bit different. They are based on the passive tracking of your behavior, like the number of movies you've seen in different genres. Fundamentally, implicit ratings are generated from the frequency of your actions. For example, if you watch 30 movies, and of those 30 movies, 22 are action movies, and only one is a comedy, the low number of comedy views will be converted into low confidence that you like comedies, and the high number of action movies will be converted into a high confidence that you like action movies. These confidence scores are then used as ratings. The logic behind this is, in essence, the more you carry out a behavior, the higher the likelihood that you like it, and thus a higher rating. Additionally, in some cases you may not have access to user behavior counts like this. A simpler form of ratings that still works with the ALS algorithm is the use of simple binary ratings. Rather than having a count of user actions, binary ratings just show whether a user has done something like watched a comedy, represented by a 1, or not watched a comedy, represented by a 0. These types of ratings aren't nearly as rich, but they still can provide meaningful insight and still work perfectly fine with the ALS algorithm. Now let's look at some actual data. So far, we've only considered recommendations as a use case for the ALS algorithm, but there are other applications that are also useful. These include latent feature discovery, item grouping, dimensionality reduction, and image compression. In this course, we'll only talk about some of these. First, let's talk about latent features. As mentioned earlier, people will go to great lengths to effectively categorize items, but some products span various categories, making them difficult to organize. Movies are often like this. For example, horror movies can be comedies, dramas can be satires, documentaries can be romances or even mysteries. Because of this, they can sometimes be difficult to market. If we had a better understanding of how consumers categorize movies based on their experience watching them, we could add more power to marketing strategies. ALS can help with this. When we have a matrix that contains users and movie ratings, ALS will factor that matrix into two matrices, one containing user information and the other containing product information, or in this case, movie information. Each matrix takes the respective labeled axis from the original matrix and is given another axis that is unlabeled. The unlabeled axes contain what's called latent features. The number of latent features is referred to as the rank of these matrices. In this case, the rank chosen is 3. You as a data scientist get to choose how many of these ALS will create. These latent features represent groups that are created from patterns in the original ratings matrix, and the values in these columns represent how much each item falls into these groups. For example, in the original ratings matrix, there might be a lot of people who like horror movies and don't like dramas. They would rate horror movies high and dramas low. Likewise, other people might like dramas and not like horror movies, and would rate dramas high and horror films low. ALS can see this and determine that these are different types of movies. And if we were to look at the movie factor matrix, we would likely see that in one of the latent feature rows, the dramas would score high and the horror movies would score low, while in another latent feature column, we might see the opposite. Knowing a little about these movies, we could determine that those latent features reflect those two genres. This allows us to mathematically see how users experience these movies and to what degree users feel each movie falls into each respective category. This concept goes a bit deeper though. For example, if we look at a movie matrix, we might see in one latent feature column that several movies have scored very high, but they don't seem to have anything in common. If they're all popular movies, we might want to research what's going on here to see if there's a business opportunity. Digging deeper, we find that these movies are all adaptations of Shakespeare plays, and that there seems to be a strong customer group that likes these types of movies. Now that we know this, we can use this information to inform how we choose what movies to make and hopefully give our customers more of what they want. It's worth reiterating that in the original dataset there was no column anywhere called Shakespeare adaptations. It's also worth noting that many or all of these customers may not even know that this is something that draws them to these movies. This is the type of powerful information that ALS can help us uncover. Now let's try to actually use this. As you've probably realized, matrix operations are fundamental to the ALS algorithm. We're going to review matrix multiplication and matrix factorization. Let's start with matrix multiplication. Here we have two square matrices. In order to multiply them together, we make specific pairs of the values from the two matrices and add the products of those pairs. We start at the top left-hand corner of each matrix and create pairs moving to the right on the first matrix and moving down on the second matrix one at a time. Each pair is multiplied and the products from all pairs are added together. The final sum will make up one number of the resulting matrix. That's a lot to digest, so let's walk through an example. Starting at the top left number of each matrix, we have a pair of numbers, 1 and 9. We will multiply those numbers together. Then moving to the right on the first matrix and down on the second matrix, we have 2 and 6. Then, moving right again on the first matrix and down again on the second matrix, we have 3 and 3. We have completed the first set of pairs, so let's add their products together. 1 times 9 plus 2 times 6 plus 3 times 3 is 9 plus 12 plus 9, which gives us 30. 30 is the first number in our final matrix. From here, we stay on the first row of the first matrix, but move on to the second column of the second matrix. These pairs give us 1 and 8, 2 and 5, and 3 and 2. 1 times 8 plus 2 times 5 plus 3 times 2 is equal to 8 plus 10 plus 6, which is 24. Moving to the next set of pairs, we multiply 1 and 7, 2 and 4, and 3 and 1. Their products are 7, 8, and 3, which makes 18. Once we've multiplied the first row of the first matrix by all columns of the second matrix, we then go through the same process for the second row of the first matrix with all columns of the second matrix, and so on, until all the rows of the first matrix have been multiplied by all columns of the second matrix. In this example, we multiplied two square matrices of the same dimensions. In reality, you can multiply any two matrices as long as the number of columns of the first matrix matches the number of rows of the second matrix. If they don't, then some values in one of the matrices won't be paired and multiplication can't be completed. Let's look at some examples and practice matrix multiplication. Matrix factorization, or matrix decomposition, is essentially the opposite of matrix multiplication. Rather than multiplying two matrices together to get one new matrix, matrix factorization splits a matrix into two or more matrices which, when multiplied back together, produce an approximation of the original matrix. There are several different mathematical approaches for this, each of which has a different application. We aren't going to go into any of that here. We are simply going to review the factorization that ALS performs. Used in the context of collaborative filtering, ALS uses a factorization called non-negative matrix factorization. Because matrix factorization generally returns only approximations of the original matrix, in some cases they can return negative values in the factor matrices, even when attempting to predict positive values. When predicting what rating a user will give to an item, negative values don't really make sense. Neither do they make sense in the context of latent features. For this reason, the version of ALS that we will be using will require that the factorization return only positive values. Let's look at some sample factorizations. Here's a sample matrix of possible item ratings. There are 5 rows and 5 columns. And here's one factorization of that matrix called the LU factorization. Notice that the factor matrices are the same dimensions or rank as the original matrix. Also notice that some of the values in this factorization are negative. Using this type of factorization could result in negative predictions that wouldn't make sense in our context. Here's another factorization. In this case, all the values are positive, meaning that the resulting product of these factor matrices is guaranteed to be positive. This is closer to what we need for our purposes. Notice here that the dimensions of the factor matrices are such that the first factor matrix has the same number of rows as the original matrix, but a different number of columns. Also, the second factor matrix has the same number of columns as the original matrix, but a different number of rows. The dimensions of the factor matrices that don't match the original matrix are called the rank, or the number of latent features. In this case, we have chosen the rank of the factor matrices to be 3. What that means is that the number of latent features of the factor matrices is 3. Remember that as a data scientist, when doing these types of factorizations, you get to choose the rank, or the number of latent features the factor matrices will have. Now look at this matrix. Not all the cells have numbers in them. Despite this, we can still factor the values in the matrix. Also notice that because there is at least one value in every row and at least one value in every column, that each of the factor matrices are totally full. Because of this, factoring a sparse matrix into 2 factor matrices gives us the means to not only approximate the original values that existed in the matrix to begin with, but also provide predictions for the cells that were originally blank. And because the factorization is based on the values that existed previously, the blank cells are filled in based on those already existing patterns. So when we do this with user ratings, the blanks are filled in with values that reflect the individual user behavior and the behavior of users similar to them. This is why this method is called collaborative filtering. Let's look at some real-life examples. Now that we've covered matrix multiplication and matrix factorization, we're ready to begin exploring how ALS uses non-negative matrix factorization to predict how users will rate movies they haven't yet seen. Let's start at the beginning. Here's a portion of a matrix of users and their movie ratings. In total, there are 671 users and 9,066 movies. Of the 6.1 million possible ratings we could have in this matrix with this many users and movies, we only have about 100,000. That means that 98% of the matrix is totally blank. This makes sense because 9,066 movies are far too many movies for any normal person to watch in their lifetime. One of the benefits of ALS is that it works well with sparse matrices like this. Now, the first thing ALS does with a matrix like this is factor it into 2 different matrices as you see here. Remember that factorizations like this produce 2 matrices which, when multiplied back together, produce an approximation of the original matrix. In order to get the closest approximation of the original matrix R, ALS first fills in the factor matrices with random numbers, and then makes slight adjustments to the matrices one at a time until it has the best approximation possible. In other words, ALS holds the matrix R and the matrix U constant and makes adjustments to the matrix P. It then multiplies the 2 factor matrices together to see how far the predictions are from the original matrix using the root mean squared error, or RMSE, as an error metric. The RMSE basically tells you on average how far off your predictions are from the actual values. We'll talk more about this later in the course. But note that in calculating the RMSE, only the values that existed in the original matrix are considered. The missing values are not considered. ALS then holds P and R constant and adjusts values in the matrix U. The RMSE is calculated again, and ALS again switches and calculates the RMSE again. ALS will continue to iterate until instructed to stop, at which point ALS has the best possible approximation of the original matrix R. The beauty of all this is that when the RMSE is fully minimized, ALS simply multiplies the matrices back together, and the blank cells are filled in with predictions. In other words, when we take a sparse matrix and factor it into 2 matrices, every rating in the original matrix must have a respective row and column full of values in the respective factor matrices that can be multiplied back together to approximate that original value. And since there is at least one rating in every row and at least one rating in every column of the original matrix, when ALS creates the 2 respective factor matrices, there are values in every cell of the 2 factor matrices, which allows us to then create predictions for the previously blank spaces. So when ALS iterates to make sure that its resulting product is as close to those original cells as possible, the result is that the previously blank cells are now filled in with values that are based on how each user has behaved in the past relative to the behavior of similar users. Let's jump into some examples and see how this is done in real life. Let's talk about data preparation. Data preparation will consist of two things: correct DataFrame format and correct schema. First, DataFrame format. Most DataFrames you've seen probably look like this, with user IDs in one column, all the features in the remaining columns, and the values of those features making up the contents of those columns. However, many PySpark algorithms, ALS included, require your data to be in row-based format like this. The data is the same. The first column contains user IDs, but rather than a different feature in each column, column 2 contains feature names, and column 3 contains the value of that feature for that user. So a user's data can be spread across several rows, and rows contain no null values. Depending on your data, you may need to convert it to this format. Now let's talk about creating the right schema. As you see, our user ID column and our generically named column of movie titles are strings. PySpark's implementation of ALS can only consume user IDs and movie IDs as integers. So again, you might need to convert your data to integers. Let's walk through an example of how to do all of this. Here's a conventional data frame. To convert it to a long or dense matrix, we will need to use a user-defined function called wide to long. We won't go into the detail of how it works here, but it turns the conventional data frame into a row-based data frame like this. If you'd like access to this function directly, a link will be provided at the end of the course. So we have the right data frame format. Let's get the right schema. In order to have integer user and movie IDs, we need to assign unique integers to the user IDs and to the movie IDs. To do this, we will follow 3 steps. Extract unique user IDs and movie IDs, assign each one an integer ID, and rejoin these unique integer IDs back to the ratings data. Let's start with user IDs. Let's first run this query to get all the distinct user IDs into one data frame and call it users. Then we'll import a method called monotonically increasing ID, which will assign a unique integer to each row of our user's data frame. We need to be careful when using this because it will treat each partition of data independently, meaning the same integer could be used in different partitions. In order to get around this, we'll convert our data into one partition using the coalesce method. Also note that while the integers will be increasing by a value of 1 over each row, they may not necessarily start at 1. That's not super important here. What's really important is that they are unique. So now we can create a new column in our user's data frame called user_int_id, set it to monotonically increasing ID, and we will have our new user integer IDs. Note that the monotonically increasing ID method can be a bit tricky, as the values it provides can change as you do different things to your dataset. For this reason, we've called the persist method to tell Spark to keep these values the same across all subsequent DataFrame operations. We'll do the same thing with the movie IDs, and now we have 2 data frames, one with our user IDs and one with our movie IDs. So let's join them together along with our original data frame on our user ID and variable columns using the join method, specifying a left join. We can be even more thorough by creating a new data frame with only the columns ALS needs and renaming our columns using the .alias method, which renames the column on which it is called, like this. Now let's prepare some data. As with many other algorithms, ALS has arguments that we give it and hyperparameters which must be tuned in order to generate the best predictions. Here's what a built-out ALS model looks like. Let's review each argument and hyperparameter. The user call, item call, and rating call are straightforward. They simply tell Spark which columns in your data frame contain the respective user IDs, item IDs, and ratings. The first ALS hyperparameter is the rank. As you already know, ALS will take a matrix of ratings and it will factor that matrix into two different matrices, one representing the users and the other representing the products or items, or in our case, movies. In the process of doing this, latent features are uncovered. ALS allows you to choose the number of latent features that are created, which is referred to as the rank hyperparameter, often represented by the letter K. Your objective with the data will determine the rank. If you're trying to find meaningful groupings or categories of movies to see how similar or different movies are, you may want to experiment with different numbers of latent features. If you have too few or too many latent features, the groupings might be difficult to understand, so you want to look at different numbers of latent features and manually identify what makes the most sense. For purposes of recommendations, however, the best number of latent features will be found through cross-validation. The number of iterations, or max iter, simply tells ALS how many times to iterate back and forth between the factor matrices, adjusting the values to reduce the RMSE. Obviously, the higher number of iterations, the longer it will take to complete, and the fewer number of iterations, the higher the risk of not fully reducing the error, so you'll have to determine what works best for you. Many other machine learning algorithms have a regularization parameter, often called a lambda. A lambda is simply a number that is added to an error metric to keep the algorithm from converging too quickly and overfitting to the training data. The lambda for ALS in PySpark is referred to as the reg param. We'll talk about alpha later in the course, but suffice it to say that alpha is only used when using implicit ratings and not used when using explicit ratings. Let's talk about the ALS arguments. As mentioned previously, there are several different factorizations that can be used to factor a matrix. The one that we are interested in is the non-negative matrix factorization. So we set the non-negative argument to true. You might be familiar with the term cold start strategy already. In the context of ALS, when splitting data into test and train sets, it's possible for a user to have all of their ratings inadvertently put into the test set, leaving nothing in the train set to be used for making a prediction. In this case, ALS can't make meaningful predictions for that user or calculate an error metric. To avoid this, we set the cold start strategy to drop, which tells Spark that when these situations arise to not use them to calculate the RMSE, and to only use users that have ratings in both the test and training sets. We also need to tell Spark whether our ratings are implicit or explicit. We do this by setting the implicit prefs argument to true or false. Once we have a built-out model like you see here, we can fit it to training data, and then generate test predictions to see how well it performs. We can do this by calling the fit and transform methods as you see here. You'll do this yourself in subsequent exercises. Now it's your turn to build some models. Up until now, we've only been using sample datasets. Now we're going to begin using actual data using the MovieLens dataset. This dataset is made available by the good people at grouplens.org and contains roughly 20 million ratings for over 138,000 users and more than 27,000 movies. In order to provide you with a better learning experience, we will achieve shorter runtimes by using a subset of the original dataset, including 100,000 ratings. In addition to the ratings data, grouplens.org also provides additional data files that include information on movie genres and other types of tags that movie watchers have provided for them. We'll take what you've learned from the previous chapters and explore the data, prepare the data, build out a cross-validated ALS model, generate predictions, and assess the model's performance. First, we'll view the data using the .show and .columns methods, as well as some other methods to understand the nature of the dataset. Then we'll calculate its sparsity using this sparsity formula, and then we'll assess whether further preparation is needed in order to adequately prepare it for ALS. If you're not familiar with the term sparsity, it simply provides a measure of how empty a matrix is, or what percentage of the matrix is empty. In essence, this formula is simply the number of ratings that a matrix contains divided by the number of ratings it could contain given the number of users and movies in the matrix. The code to calculate sparsity is pretty straightforward. We'll simply get the numerator by counting the number of ratings in the ratings data frame. Then we'll get the number of distinct users and the number of distinct items or movies. We'll then multiply the number of users and the number of movies together to get the denominator, and simply divide the numerator by the denominator and subtract the result from 1. Because division in Python will return an integer, we multiply the numerator by 1.0 to ensure a decimal or float is returned. Let's go over some other techniques that may or may not be new to you. As you may already know, the distinct method simply returns all the unique values in a column. For example, if you want to know how many unique users there are in a table, you could simply select the user column from the data frame, then run the distinct and count methods like you see here. The GroupBy method organizes data by the unique values of a specific column to return subtotals for those unique values. For example, if you wanted to look at total number of ratings each user has provided, you would first need to group by user ID as you see here, then call the count method as you see here. With this, you could then get the min, or max, or average of that same column. The filter method allows you to filter out any data that doesn't meet your specified criteria. For example, if you wanted to only consider users that have rated at least 20 movies, you would simply apply the same GroupBy and count methods, and then add a filter method specifying that the count column should only include values greater than 20. Let's apply what you've learned to a real dataset. Remember from the last chapter, you built out a model on the ratings dataset, and the code looked like this. Now the RMSE that you got was lower than the 1.45 shown here, but what if you went through this whole process and got an error metric that you weren't satisfied with, like this RMSE of 1.45? You might want to try other combinations of hyperparameter values to try and reduce that. Spark makes it easy to do this by using two additional tools called the Param Grid Builder and the Cross Validator. These tools will allow you to try many different hyperparameter values and have Spark identify the best combination. Let's talk about how to use them. The Param Grid Builder tells Spark all the hyperparameter values you want it to try. To do this, we first import the Param Grid Builder package, instantiate a Param Grid Builder, and give it a name. We'll call it Param Grid. We then add each hyperparameter name by calling the addGrid method on our ALS algorithm, and hyperparameter name as you see here. Notice the empty list to the right of the hyperparameter names. This is where we input the values we want Spark to try for each hyperparameter, like this. Once we've added all of this, we call the build method to complete the build on our Param Grid. Now let's look at the cross validator. The cross validator essentially fits a model to several different portions of our training dataset called folds, and then generates predictions for each respective holdout portion of the dataset to see how it performs. To properly use the cross validator, we first import the cross validator package, instantiate a cross validator, and give it a name. We'll call it CV here. We then tell it to use our ALS model as an estimator by setting the estimator argument equal to the name of our model, which is ALS. We'll then set the estimator param maps to our param grid that we built so that Spark knows what values to try as it works to identify the best combination of hyperparameters. Then we provide the name of our evaluator so it knows how to measure each model's performance. We do this by simply setting the evaluator argument to the name of our evaluator, which is evaluator. We finish by setting the numFolds argument to the number of times we want Spark to test each model on the training data, in this case 5 times. Let's go over how to integrate these into a full code build-out. We'll first split our data into training and test sets using the random split method, and we'll build a generic ALS model without any hyperparameters, only the model arguments as you see here. The cross validator will take care of the hyperparameters. We'll build our param grid builder so Spark knows what hyperparameter values to test. We'll create an evaluator so Spark knows how to evaluate each model. Then the cross validator will tell Spark the algorithm, the hyperparameters and values, and the evaluator to use to find the best model and the number of training set folds we want each model to be tested on. We then fit our cross-validator on the training data to have Spark try all of the combinations of hyperparameters we specified by calling the cv.fit method on the training data. Once it's finished running, we extract the best performing model by calling the best model method on our model. We'll call this our best model, and with it, we can generate predictions on the test set, print the error metric, and the respective hyperparameter values using the code you see here. And now we have our cross-validated model. Let's build a real model on a real data set. Congratulations! You just built your first cross-validated ALS model. Now let's determine whether the model suits your needs or not. The primary way to do this is to examine the error metric, in this case the RMSE. The RMSE, or root mean squared error, tells us on average how far a given prediction is from its corresponding actual value. It's pretty straightforward. If we have predictions and actual values, the RMSE subtracts the actual value from the prediction, then squares those differences to make them positive. It then sums those differences, takes the average by dividing by the number of observations, in this case n equals 4, and it then takes the square root to undo the squaring of the values that we did previously. So if we have an RMSE of 0.61, then on average our predictions are either 0.61 above or below the original rating. Another way to evaluate our model is to look at its recommendations. Remember, however, that ALS is often used to identify patterns and uncover latent features that are unobservable by humans, meaning that ALS can sometimes see things that may not initially make sense to us as humans. Bear this in mind as you move forward. To generate recommendations, we will use the native Spark function recommend for all users, which generates the top recommendations for all users. ALS recommendation output has two challenges that need to be addressed. The first is that it is in a format like this, which is perfectly usable in PySpark, but isn't very human readable. To resolve this, we save the DataFrame as a temporary table and use this SQL query to make it readable. The explode command essentially takes an array like our recommendation column and separates each item within it like this. Notice that only one movie ID and its respective recommendation value for each user is contained on each line, where previously all recommendations for a given user were contained on one line. Also notice that ALS conveniently includes the movie ID and rating column names with each value on each line. This makes it easy to separate them into different columns. Adding the lateral view to the explode function allows us to treat the exploded column as a table and extract the individual values as separate columns. We first name the lateral view, in this case we call it exploded table, and then give it a formal table name which we will call movie IDs and ratings. This allows us to select the user ID and then get the movie ID and ratings by referencing the movie IDs and ratings table in the beginning of our query. The output is now readable. And if we join it to the original movie information, we can see what's going on even better. The other challenge with these recommendations is that they include predictions for movies that have already been seen. Remember how ALS creates two-factor matrices that are multiplied together to produce an approximation of the original ratings matrix? That's essentially what the ALS output is, including all movies for all users, whether they've seen them or not. A simple way to address this is to filter out the movies that have already been seen. Since we already have our clean recommendations and the original movie ratings, we can simply join these two data frames together on user ID and movie ID using a left join. The movies that have already been seen are those that have a rating from the original movie ratings data frame. So if we simply add a filter so that the rating column of the movie ratings data frame is null, we'll only have predictions for movies that the individual users have not seen. Now let's evaluate your model. By now, you should be pretty comfortable with ALS. So far, we've only used explicit ratings. In most real-life situations, however, explicit ratings aren't available and you'll have to get creative in building these types of models. One way to get around this is to use implicit ratings. Remember that while explicit ratings are explicitly provided by users in various forms, implicit ratings are data used to infer ratings. For example, if a news website sees that in the last month you clicked on 21 geopolitical articles and only one local news article, ALS can convert these numbers into scores indicating how confident it is that you like them. This approach assumes that the more you do something, the more you prefer it. ALS can use these confidence ratings to generate recommendations, and you're going to learn how to do this. First, let's talk about the dataset you will be using. The dataset this time comes from the Million Songs dataset available from Lab Rosa at Columbia University. You're going to be using one file of this dataset called the Echo Nest Taste Profile dataset. It contains information on over 1 million users, including the number of times they've played nearly 400,000 songs. This is more data than we can use for this course, so we will only be using a portion of it. We'll first examine the data, get summary statistics, and then build and evaluate our model. One thing to note here is that because the use of implicit ratings causes ALS to calculate a level of confidence that a user likes a song based on the number of times they played it, a matrix will need to include zeros for the songs that each user has not yet listened to. In case your data doesn't already include the zeros, we'll walk through how to do this. Let's say we have a ratings data frame like this. You can use the .distinct method to extract the unique user IDs and song IDs like this. You can then perform a cross-join which joins each user to each song like this. Notice that the 3 users and 3 songs we originally had now create 9 unique pairs. Using a left join, you can take that cross-join table and join it with the original ratings to get the num plays column. Notice it joins on both user ID and song ID. And because we want zeros in place of the null values so that every user has a value for every song, we simply call the .fillNA method, telling Spark to fill the null values with 0, and you have your final product to feed to ALS. Here are those steps in a nice clean function. Let's do this with our Million Songs dataset. Now that we have an implicit ratings dataset, let's discuss these types of models. The first thing you should know is that implicit ratings models have an additional hyperparameter called alpha. Alpha is an integer value that tells Spark how much each additional song play should add to the model's confidence that a user actually likes a song. Like the other hyperparameters, this will need to be tuned through cross-validation. The challenge of these models is the evaluation. With explicit ratings, we use the RMSE. It made sense in that situation because we could match predictions back to a true measure of user preference. In the case of implicit ratings, however, we don't have a true measure of user preference. We only have the number of times a user listened to a song and a measure of how confident our model is that they like that song. These aren't the same thing, and calculating an RMSE between them doesn't make sense. However, using a test set, we can see if our model is giving high predictions to the songs that users have actually listened to. The logic here is that if our model is returning a high prediction for a song that the respective user has actually listened to, then the predictions make sense, especially if they've listened to it more than once. We can measure this using this rank order error metric, or ROEM. In essence, this metric checks to see if songs with higher numbers of plays have higher predictions. For example, here's a set of bad predictions. The %rank column has ranked the predictions for each individual user such that the lowest prediction is in the highest percentile and the highest prediction is in the lowest percentile. Notice that these bad predictions include low predictions and high predictions for songs with more than one play, indicating that the predictions may not be any better than random. If we multiply the number of plays by the %rank, we get this NP rank column. When we sum that column, we get our ROEM numerator, and the sum of the num plays column gives us our ROEM denominator. Using these, we can calculate our ROEM to be 0.556. Values close to 0.5 indicate that they aren't much better than random. If we were to look at good predictions where the model gave high predictions to songs that had more than one play, they might look like this. Notice that songs that have been played have high ratings, indicating that the predictions are better than random, which subsequently gives us an ROEM of 0.1111. This is much closer to 0, which is where we want to be. Unfortunately, Spark hasn't implemented an evaluator metric like this, so you'll need to build it manually. An ROEM function will be provided to you in subsequent exercises, and for your reference, the code to build it is provided at the end of this course. Using this function and a for loop, you can build several models as you see here, each with different hyperparameter values. You'll want to create a model for each combination of hyperparameter values that you'll want to try. You can then fit each one to the training data, extract each model's test predictions, and then calculate the ROEM for each one. This is a simplified way to do this. Full cross-validation is imperative to building good models. It is beyond the scope of this course to teach how to code a function that manually cross-validates and evaluates models like this, but doing so should be done, and code to do so is provided at the end of this course. Now let's put this into practice. So far, we've covered situations when you have explicit ratings and when you have implicit ratings from user behavior counts. Now we're going to cover the situation when you might not even have behavior counts. In some situations, you may only have binary data that tells you whether a user has or has not taken an action, with no indication of how many times they've done so. To go back to the movie example, if you know whether customers have watched certain movies, but don't have information on how many times or how much they actually liked them, you could simply feed binary data to ALS that indicates which customers have watched each movie and which ones haven't. ALS can still pull signal from this type of data and make meaningful predictions. When taking this approach, the data will look like this. Notice that all ratings are either a 1 or a 0. We must treat binary ratings like these as implicit ratings. If we treated them like explicit ratings and didn't include the zeros, the best performing model would simply predict 1 for everything and deliver a deceivingly ideal RMSE of 0. Also, as with our previous million songs model, we can't use the RMSE as a model evaluation metric. Ultimately, when our machine learning process holds out random observations in the test set, we want our model to generate high predictions for those movies that users have actually watched. For this reason, we'll use our ROEM metric again. We'll apply the same concepts we've covered previously on this binary dataset. The convenience of using the movie lens dataset is that we can see how our binary model performs against the original true preference ratings of the original movie lens dataset. One word about binary models. While it's perfectly feasible to feed binary data like this into ALS and get meaningful recommendations, the data does have sort of a class imbalance where the vast majority of ratings are zeros with a small percentage of ones. Since implicit ratings models use customized error metrics like ROEM and not RMSE, the class imbalance doesn't really pose a problem like it might in classification problems. ALS can still generate meaningful recommendations from this type of data, but there are strategies that can be taken with the data to try and improve recommendations. For example, rather than treat unseen movies purely as zeros, you can weight them higher if more people have seen them. This assumes that if many people have seen a movie, it must be a pretty good movie, and therefore should be treated with a little more weight, and vice versa. This is called item weighting. Likewise, you could weight movies by individual user behavior. For example, if a user has seen lots of movies, you could weight their unseen movies lower, assuming that if a user has seen lots of movies, they know what they like and have deliberately chosen not to view the movies they haven't seen, and therefore those movies deserve a lower weighting. While these methods are applicable, their methods haven't been implemented into the PySpark framework and therefore require a lot of manual work which is beyond the scope of this course. However, if you'd like to learn more about these types of approaches, you can read the paper referenced at the end of this course. Let's build a binary ratings model. Congratulations! You've now completed this course on building collaborative filtering recommendation engines in PySpark. We've covered a number of things from why these are important, to matrix multiplication and factorization, and latent features. But most importantly, you've learned how to build and interpret recommendation engines with 3 different types of data: explicit ratings, implicit ratings using user behavior counts, and implicit ratings using binary user behavior. With this information, you'll be well prepared to build a collaborative filtering recommendation engine with the relevant data available to you as a data scientist. Some things to bear in mind about these types of models. If users don't have a lot of ratings and ALS can't infer much about them, it's likely that ALS will make broad general recommendations that aren't really personalized. You might have seen this if you spent extra time exploring some of the recommendation output. Like all models, the more data there is, the better the model performs. While we've gone over different ways of evaluating recommendation engines, the only way to really know if your model performs well is to test it on users and see if they actually take your recommendations. It's entirely possible that a simple binary implicit ratings model provides much better recommendations for users than an explicit model, but the only way to know is to test it. Bear this in mind as you move forward. Here are some resources to help you as you continue to learn about these models and begin to build them on your own. The first is a paper published by McKinsey & Company discussing the power of recommendation engines like ALS-based models. The second is the code to build the wide to long function discussed in the section about preparing data for ALS. The third is the white paper that provides the academic background for building ALS models using implicit ratings. I highly recommend reading this paper as it provides a lot of context and insight into how these models work and alternative ways to evaluate them. The fourth is a GitHub link for code that manages the cross-validation and model evaluation for implicit ratings models using ALS and PySpark. The last resource listed here is a paper that discusses the math and intuition behind the user-based weighting and item-based weighting methodologies for addressing the class imbalance present in binary ratings models. Congratulations on completing this course, and best of luck as you move forward.